Hi, it's time for another math easy solution. Today we're going to go over infinite sequences and series and look at the end of chapter section on problems plus, which is a series of advanced math problems at the end of most chapters in my calculus book. And yeah, it's pretty intense stuff. So just note here, as always, if you don't have time to watch this whole video, you can play this video at a faster speed. There's no summary and conclusions in this particular video. And also, top secret life hack, your brain gets used to faster speed, and here's my tutorial on it. Click that link and go and check it out. And you could also download and read the notes in PDF format. Link will be in the description below, as well as the link to the article format on the Hive blockchain. And also, you could watch the video in parts, and all the timestamps of all the parts and questions will be in the description as well. So now let's just jump right in. So calculus book reference. Note that I mainly follow along the following calculus book, and this is Calculus Early Transcendentals, 7th edition by James Stewart. And note the earlier videos that I used the 6th edition. Or I'll just correct that. In the earlier videos I used the 6th edition. Just a note on there, and yeah, just got hold of the 7th edition. So anyway, let's jump right in. So infinite sequences and series problems plus. So at the end of each chapter in my calculus book, there are a series of advanced math problems called problems plus. They are a great way to fine-tune your mathematical skills. And if you can solve them, you can pretty much solve all of life, especially if you could solve them without looking at the solutions beforehand. So yes, they're pretty next level questions. So topics to cover. I've created a list of the problems and which I will use to add the video timestamps. So yeah, I just put these lists here. So first as an example, and there's problems 1 all the way to 26 right here, and I'm going to put the timestamps to each one in a video link yeah, in the description under the video. So I just put the list right here, just get that set up already. And note that there's an example. So in the calculus book has an example with a solution, and then the other problems, they don't have the solutions unless you have the solution manual, which I do. So anyways, let's jump right into the example. So the example states, find the sum of the series, and this is the summation from n equals 0 to infinity of x plus n to the power of n divided by n plus 3 factorial. Alright, so let's take a look at the solution. So the solution, the problem-solving principle that is relevant here is recognizing something familiar, and we're asked, does the given series look anything like a series that we already know? And before we look at that, let's do a quick recap on the Taylor series and so on. It's from an earlier video right there. There's a link to the Hive article and has a video embedded there on it. So recall that the Taylor series, or this one right here, the nth sum right here. Yeah, this Taylor series is equal to t sub n of x equals to the summation from n equals 0 to n. I mean from I equals 0 to n of this is the ith derivative at a divided by I factorial times by x minus a factorial, and you get this set up like that. Then when you take it to the limit as it goes to infinity, you get the series. So this is a partial sum, and this is the series. And then, yeah, you just write it like this. Summation from n equals 0 to infinity of f of the nth sum time of a divided by n factorial times x minus a to the power of n. And then you get this set up like that. And yeah, this Taylor series, yeah, you could write this where this f is a function. And so you could apply that, write that function as a Taylor series or just a series. And the theorem is if f of x is equal to the Taylor series plus the remainder, the Rn of x, where t sub n is the nth degree Taylor polynomial of f at a, or just the nth partial sum, and you have the limit as this remainder goes to 0 as n approaches infinity of Rn of x equals 0. So if this remainder is going to 0, therefore you have this right here, the radius of convergence, absolute value of x minus a is less than r. Then f is equal to the sum of its Taylor series, yeah, on the interval of the radius of convergence. So x minus a absolute value is less than r. So yeah, so you could write a function, write this as a Taylor series, and if the function is equal to this plus remainder, and the remainder goes to 0, then it's equal to its Taylor series. And note that a Maclaurin series is a special case of a Taylor series where a equals to 0. And you could write that as summation from n equals 0 to infinity of, this is of the nth derivative at 0, and then divided by n factorial times x to the power of n. So yeah, notice that there's no a there anymore. That age is 0, so you just have f of 0 plus f prime of 0 divided by 1 factorial, etc. and keeps going on. And below is a table of some functions that are equal to their corresponding Maclaurin series. Yeah, so here's some functions right here. And there's r equals 1, r equals infinity. There's a radius of convergence. We'll get to that in a bit. And just note here, e to the power of x equals the summation from n equals 0 to infinity of x to the power of n divided by n factorial. And that's pretty much exactly ours. Instead of x to the power of n, we have x plus 2. And instead of n factorial, we have n plus 3 factorial. So that looks like it. So we can actually apply that. And also recall that that r in the above table is the radius of convergence. So from my earlier video, basically if you have a power series for a given power series, there's theorem. And from my earlier video, you can click on the link over there. So for a given power series, for the summation from n equals 0 to infinity of this power series, Cn is a coefficient times x minus a to the power of n. There are only 3 possibilities. Either the series converges only when x equals to a, because then you just have a trivial setup. You just have a minus a is 0. Yes, you just have a minus a equals 0. They just all vanish. So the whole thing vanishes. Or the series converges for all x. Or there is a positive number r such that the series converges if the absolute value of x minus a is less than r, and it diverges if absolute value of x minus a is greater than r. So that's the only 3 setups we have. And yeah, the number r in case 3 is called the radius of convergence. And by convention, r equals 0 in case I, so when it's only just x equals a, and r equals to infinity for if it converges for all x, and then the other one you just write it like that. And yeah, there's some other notes on there, and the interval of convergence of the actual interval range. And actually we might as well continue reading it. So first let's go over here. So by convention, the radius of convergence is r equals 0 in case I, and r equals infinity in case I. And the interval of convergence of a power series is the interval that consists of all values of x for which the series converges. In case I, the interval consists of just a single point a. In case I, the interval is negative infinity to infinity, and then there's open bracket because you can't equal infinity. In case 3, note that the inequality x absolute value of x minus a can be rewritten as this, as a so x is between a minus r and is between a plus r. And when x is an endpoint of the interval, that is what at x equals a plus or minus r, anything can happen. The series might converge at one or both endpoints, or it might diverge at both endpoints. Thus, in case 3, there are 4 possibilities for the interval of convergence. You have a minus r and a plus r, open brackets, so it doesn't equal at that area, so it doesn't converge at the end. Or it can converge on the right side, so the closed bracket there, or you could converge on the left side at at x equals a minus r. Or it could converge at both ends there. So it converges on the left but not the right. This one converges on the right but not the left. And here's this situation illustrated in figure 3 right here, just this figure right here. So there's the radius of convergence at a. So you're also going to have it at a. And then you also have this, that's at a. Then you have convergence for absolute value of x minus a is less than r, like that. Because this is r, like that. Distance is r. And this is our x line, like that. And then it diverges beyond that. That's case 3 there. And here's this open circle, but if it converges on there, you just put a dot there. If it converges at both, you put a dot. Anyway, so that was just a quick recap. So now let's go back to our setup. So we have to see what compares with this right here. And in fact, that is our Taylor series right here. The Maclaurin series, e to the x equals to the summation from n equals 0 to infinity of x to the power of n divided by n factorial. All right. Yeah, so let's write that down. So, well, it does have some ingredients in common with the Maclaurin series for the exponential function. So we'll write e to the x is equal to, and this one is the summation from up to infinity, n equals 0. And let's scroll back what it was again. This is x to the power of n divided by n factorial, and the radius of convergence is infinity. So we have x to the n over n factorial equals to, yeah, it's equal to 1. When you put a 0 there, then the next one's going to be x to the 1 over 1. And yeah, this could be still x plus x to the 2 over 2 factorial plus x to the 3 over 3 factorial plus dot dot dot. And then this is radius of convergence is infinity. And now we can make the series look more like our given series by replacing x by x plus 2, because well, we have it over here, the series here x plus 2, and then the other one's n plus 3. So we'll replace it, and then basically what we'll have is, let's just write that down. So instead of e to the x, we'll just go e to the x plus 2. So this is going to equal to, right here, let's put that neater. Okay, this is infinity, n equals to 0, x plus 2 to the power of n divided by n factorial. And then if you write this out, this will be, yeah, at n equals 0, that's still going to be just 1. X plus 2 to the power of 0 is still going to be 1. And divided by 0 factorial is 1. You should, yes, 0 factorial is defined as 1. The next one's going to be, well, when it's 1, x plus 2 to the power of 1. And yeah, so this is going to be power of 1 divided by 1 factorial is just 1. And then the next one's going to be plus x plus 2 over 2 factorial. And for completeness, let's write one more, plus x plus 2 to the power of 3 over 3 factorial plus dot dot dot. Yeah, but here, notice the issue here. So, but here the exponent in the numerator, this is the top part right here, the n, matches the number in the denominator whose factorial is taken. So you have n and n, and you have, yeah, you have 2 and 1, 2 and 2, 3 and 3, etc. To make that happen in the given series in the example, because notice this one right here, they don't match. Let's go back here. So n, this right here, yeah, so you have the power of n, but this is n plus 3, so they don't match over there. So separated by that 3 there. Yeah, so instead what we could do is, to make that happen in the given series in example, let's multiply and divide by x plus 2 to the power of 3, because remember they're separated by 3, and then what we'll do is do some manipulation, make it so that they match up. And let's go back here, and then we could just use our this part right here and plug it in. So what we have is our series in the example from n equals 0 to infinity of x plus 2 to the power of n over n plus 3. This is just factorial. So this equals 2, and I'm going to multiply the top and bottom by x plus 2 to the power of 3 divided by x plus 2 divided by 3. And notice the trick that we're going to do. And that is, well, it should be self-evident by now. But let's put this here. Summation from n equals 0 to infinity of x plus 2 to the power of n over n plus 3, and then this is factorial like that. So we want to make these the same. So this n needs to match up with this 3, this n plus 3 over there. This one here has n and n. So what we could do is, well, we can combine this. We already multiplied top and bottom, so we're not changing anything. And now this is just x plus 2. We could bring that in. There's no n value there. So we just bring that in directly into here, and then add up these powers. These are the same power right there. This x plus 2 to the power of 3, and this x plus 2 to the power of n. We could just use our power rules and combine the two. So this equals 2, 1 over x plus 2 to the power of 3 times it by, and let's just move this down a tiny notch, summation from n equals 0 to infinity of, this is going to be x plus 2 power of n plus 3. So we just combine those powers inside, and now this is going to be n plus 3 factorial. And this one is the exact same thing over here. Or actually, no, I mean over this one here. So this is just x plus 2 to the power of n, but this is past the first 3 terms. So this is at, you could just start it off at here. So if you put n equals 0 here, you basically start off right here, and you ignore all this setup right here because you start off at x plus 2 to the power of 3. It's because 0 plus 3 is 3, and then yeah, so then divided by 3 factorial. So you just start off from that. And we can expand this series, so write this as, and just make this more compact. So x plus 2 to the power of negative 3, it's the same thing as this, and then times it by, put a bracket. This is because, yeah, when you plug in n equals to 0, you're just going to get x plus 2 power of 3 divided by 3 factorial. Plus, the next one is going to be n is 1. You're going to get x plus 2 to the power of 4 divided by 4 factorial. And then plus dot dot dot. It keeps going on and on. Yeah, so thus we see that the series between brackets is just the series for x plus 2 with the first 3 terms missing. So this is just e to the x plus 2 and then subtracted by these 3 setups over there. So we just remove those first 3 terms because you see it's all gone. So we have the summation. Let's put our given series. Let's put this a bit neater. Alright, so I just paused the video and just added that. So summation from n equals 0 to infinity of x plus 2 to the power of n divided by n plus 3 factorial. This equals to, well, just our x plus 2 power of negative 3 like that. And then times it by e to the x plus 2 minus the first 3 terms. So we just put minus all these ones, so we'll just put a negative on all of them. So minus 1 minus x and minus x plus 2. And yeah, just put it like that. And yeah, that is what it is. Now we could just box this whole thing. Alright, yeah, so we just solved the example right there. So now let's take a look at our problem 1. So if f of x equals to sine x cubed, find f of 15th, 0, in other words, the 15th derivative of f at x equals 0. So yes, that's an epic question right there. Alright, so let's take a look at the solution. So it would be far too much work to compute 15 derivatives of f. So the key idea is to remember that the nth derivative at 0 occurs in the coefficient of x to the power of n in the Maclaurin series of f. So we start with the Maclaurin series for sine from the earlier table above. Going back here again, so notice that the nth derivative is inside that series. So if we go back to the Maclaurin series, because we're dealing with x equals 0, so there's a derivative right there, f of the nth derivative. So that was the first derivative, second derivative, etc. So if we could find the coefficient of the 15th one, we could just find a derivative at n equals to 15 of this Maclaurin series like that. So let's look at the sine one because we're dealing with sine. So sine is equal to this summation, but we'll just look at here. R is equal to infinity. You have x minus x cubed divided by 3 factorial plus x5. So it's always odd, and it's going from minus plus, and yeah, and they're just odd power and odd factorial. So let's write that down. So sine of x is equal to, it's going to be odd power, so power of 1. The next one's minus 3 factorial, plus x to the 5 factorial. And it keeps going on. It goes minus, plus, let's put it like that. Dot, 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 and then r is equal to infinity. So for all x, it converges. Alright, so now in our case, we're going to be plugging in x to the power of 3 because we have the sine x cubed there. So let's write that down in our Maclaurin series. So sine of x cubed, actually. So yes, sine of x cubed, put the bracket, x cubed. This equals to x to the 3 minus, well, x to the 9, 3 factorial. And the next one is going to be plus x to the 15, so 5 times 3, over 5 factorial minus plus dot, dot, dot. And then, again, this can be r is equal to infinity. Alright, yeah, so we have the series like that, but again, recall the definition of the Maclaurin series. We have summation from n equals 0 to infinity, and then you have the fn factorial of 0 times x power of n divided by n factorial. Notice that the n matches up with the power and the factorial. And so then that means, yeah, so when you keep going on here, this just over here just means you have a lot of cancellations. Either they're 0 or they subtract and they cancel. Or they combine 2, etc. That's why they're missing a whole bunch of x power 14, etc. So what that means is, well, this is x to the 15. That means that's the derivative is right over there. The 15th derivative is right beside it. So, and yeah, so that means that this part right here, but for n equals 15, let's put it actually like this, for n equals 15, matches with this 1 over 5 factorial. Thus, at the x to the power 15, we can determine the corresponding derivative. So, f of the 15th derivative at 0, divide this by 15 factorial, this equals to, times it by the x to the 15 now. This equals to 1 over 5. Yeah, this is going to be right here. So that's that section over there. Equals to 1 over 5 factorial times it by x to the power of 15, like that. Alright, so this means, well, we could just cancel this out, and then we can move this over to this other side. So what that means is the f of 15... the 15th derivative at x equals 0 is equal to 15 factorial over 5 factorial. And this just equals to, well, 15 times it by, let's write this all out, 15 times by 14 times by 13 times by 12 times by 11 times by 10 times by 9 times by 8 times by 7 times by 6, and then times by 5 all the way, but you're dividing by 5 times 4 times 3 times 2, etc. And then if you plug this into the calculator, what you're going to get is 10 billion 897 million and then 286,400, like that. And that is the 15th derivative at x equals 0. And now let's just do a calculation check on this. So my OneNote has a built-in calculator. Yeah, so you could just type it around here, 15 times 14, etc., all the way to the 6. And if you do this here, whoops, let's go back here, equals, yes, it just rounds up to 1 power of 1e times, 1e10. This just equals to 1 times 10 to the power of 10. And this is right here. So that just rounds it up to basically 10, 0, 0, 0, 0, 0, 0. So that's 9 plus 1. Yeah, so that just rounds it up there. So we're on the right track, but we need a better calculator because, it doesn't have, the calculator is not that good, just rounds it up. And you can also do this 15 factorial divided by 5 factorial to get the same thing. So since my OneNote calculator is not that precise, we could use the Google search alternative, presearch.com, which pays out in pre-cryptocurrency. So if you type it over here, presearch there, and has built-in calculator, 15 factorial divided by 5 factorial, you get this 10,897, 286, and then 400. Yeah, so that is correct. And yeah, before going further, just make a note, if you sign up for pre-search, just use my referral link right here, so I get a few pre. So just if you click here, just to show you what it looks like, it's pretty much like Google search, but you earn pre. So it's a cryptocurrency token. Here's the calculator. And so just type in, it automatically brings up the calculator and so on. So yes, if you sign up, use my referral code or link, and you can see the price here of pre goes up and down and so on. It's currently at 7.9 cents. So yes, very, very interesting. Anyways, let's jump back into this. So let's look at problem 2. And problem 2 states a function f is defined by f of x equals to the limit as n approaches infinity of x to the power of 2n minus 1, and then all divided by x to the power of 2n plus 1. And we're asked, where is f continuous? Alright, so let's take a look at the solution. So what we could do is use the problem-solving strategy of taking cases and basically look at key cases. And here, notice that there's a plus 1, minus 1. So let's just see what happens when x is, well, absolute value of x is less than 1. So this is case I right here. And make this space. Alright, so if we have the absolute value of x is less than 1. Let's put this better like that. Yeah, so if we have that, then what we're going to have is, well, the absolute value of x, x squared, because we're dealing with a squared right there. See how it looks like. So when you square this is going to be, well, less than 1. Yeah, because, for example, 0.9 times 0.9, that's going to be 0.81. So when you're multiplying it less than 1, you're always going to be less than 1. And it's going to be greater than or equal to 0. Because you're squaring it, it's always going to be positive. So that is where this is between. And then what we have here is when this is between, this is less than 1 here, and it's greater than or equal to 0. What we have is a limit as n. The n approaches infinity of x to the 2n square, 2n. Yeah, 2n, or more clear, just put it x squared power of n, and this equals to limit as n approaches infinity of x 2n. This equals to 0. This is from my earlier video, and I'll just put this in bracket, and we'll reference it soon. So this is from my earlier video, just added that there. So thus what we have is thus, let's put this better. Yeah, so thus if we put this all together, what we have is f of x. So if we go back to our f of x, this equals to here limit as n approaches infinity of this, and we could break that all down. So limit f x equals to the limit as n approaches infinity of x to the 2n minus 1 over x to the 2n plus 1. And this means, well, we're going to have a scenario such that this will be equal to, well, the top part's going to be 0 because we have it over here, 0 minus 1, and then bottom part 0 plus 1. So this equals to negative 1. So we have negative 1 there. That's the limit when x is, absolute value of x is less than 1 there. All right. Now before we get to the next case, just a recall from my earlier video. This is from over here, my earlier video over here. So remember, this is limit as n approaches infinity of x squared power of n, or just x to the 2n. So recall from this video, here's a link and screenshot just from my calculus book. So the sequence r power of n is convergent if r is less than or equal to 1 and greater than negative 1. Yeah, and it's divergent for all other values of r. So you have a limit as n approaches infinity of r to the power of n equals 0 if r is greater than if r is greater than negative 1 and less than 1, and it's equal to 1 if r equals to 1. So yeah, that's the scenario. And in our case here, this x to the n is less than 1, and it's also greater than or equal to negative 1. In this case, 0. So that's going to be 0. So this is our case. So this is our case right there, where r is x to the power of 2. Alright, so now let's take a look at the second case, so case II, or case 2. This is where absolute value of x is equal to 1. So let's write this down. If absolute value of x is equal to 1, so if it's equal to 1, then what we'll have is, well, this is just the same thing as writing x is equals to plus or minus 1. And the absolute value of that is just going to be the positive, like that. And what this means is, well, then the x squared is equal to plus or minus 1 squared, which equals to 1, like that. And if it's equal to 1, well, this obviously just means, well, this case right here, and that you could see that already, limit as n approaches infinity of x to the 2n, well, this just equals to limit as x approaches infinity of x to the 2n. So it's just going to be equal to limit as, that's just going to be 1 to the power of n. And so right here is going to be 1 to the n, 1 to infinity, that's still going to be 1. Or it's better yet, I'll write above here. So this equals to, 1 to the infinity, and that just approaches 1. So in other words, this equals to 1 as per this case right there. So that equals to 1. So thus what we have is, that's what we have is f of x is equal to the limit as n approaches infinity of x to the 2n minus 1 over x to the 2n plus 1. So this equals to 1 minus 1 over 1 plus 1. There's the x to the 2n is just equals to 1. So this equals to 0 over 1 equals to 0, like that. Alright, and now let's take a look at the next case, case 3. The last case is where absolute value of x is greater than 1. So if we have that, so let's write this down. So if the absolute value of x is greater than 1, like this. Yeah, so if it's that, then what this means is, well, when we square x squared, it's going to be greater than 1 times by greater than 1. This is going to be greater than 1 as well. Yeah, and if it's greater than 1, then what we'll have is limit as n approaches infinity of x squared power of n. Again, I just put that just for clarity, just to match up with our earlier video, x to the 2n. This goes to infinity, so it diverges. Yeah, so it's diverges over here. Divergent for all values of r there that's greater than. The absolute value is greater than 1. So in our case, r is x squared. That's going to be greater than 1, so it's going to diverge. And you can also see it. When you have a greater than 1 to the power of infinity, that just goes to infinity. So that's what we have. Thus, we could put this in our function. So thus, f of x equals to limit as n approaches infinity of x to the 2n minus 1 over x to the 2n plus 1, because now because here we're dealing with infinity over infinity, what we can do instead is multiply the top and bottom by x to the 2n, 1 over x to the 2n, so then we'll have a bunch of cancellations. So this equals to limit as n approaches infinity, and then this is going to cancel there. We're going to get a 1 minus 1 over x to the 2n divided by, and this is going to be 1 plus 1 over x to the 2n, like that. And in both of these scenarios right here, and the top one, we have a 1 over, well, infinity. This is going to be 1 over x to the 2n as approaches infinity. So we're going to have a 1 over infinity, which equals to, well, 0. So in other words, this whole thing equals to 1 minus 0 over 1 plus 0, which equals to 1. Alright, and now putting it all together, we have, let's just put this in a giant function, f of x is equal to, put it like that. Yeah, so it's equal to, so let's look at the scenario. So absolute value of x is greater than 1. In other words, and that equals to 1 here. So it equals to 1 if x is less than negative 1. And then it's also going to be, well, equals to 1 if x is greater than 1. So the absolute value is greater than 1. And yes, that's what we have there. And then let's go back above here. So when it equals to 1, when absolute value equals to 1, in other words, x equals plus or minus 1, we have this equals to 0. So it equals to 0 if x equals negative 1, and it equals to 0 if x equals to plus 1. Like that. I'll just put it 1. And then the next setup is, right, this neater 1. The next one is in between there. So when absolute value of x is less than 1, in other words, x is between negative 1 and 1, this equals to negative 1. So we have 1, 0, and then we have it at negative 1 if x is between 1 and greater than negative 1. And then if you were to graph this out, so let's graph this out like here. This equals to, this is the x, this is the y. So there is our key points is at 1. So at plus or minus 1, they're both at 0. So let's put a dot here. This is at 1. And then the other side is at negative 1. And in between, it's at negative 1 right here. Just put it like this. This is at negative 1, like this. And this is a open circle there. It's not filled in because it doesn't equal -1 over there. It equals a 1 over here. So it's an open interval. It's a closed interval right here, that spot. And then above it, so right 1 right here, is passed when absolute value of x is greater than 1. So put a circle and it keeps going. And put a circle and it keeps going. So that's how it looks like. Notice it. So it's basically continuous everywhere here and everywhere in between except and then everywhere past 1. So it's continuous everywhere except -1 and 1. Alright, here, so I just added it here. So the graph shows that f is continuous everywhere except at plus or minus 1, at x equals to plus or minus 1 right there. Alright, so now let's go to the next problem, and that's problem 3. This has 2 parts. This one states, show that tan of 1 divided by 2x, so 1/2 x, equals to cotangent, or cot 1 divided by 2x, minus 2 times cotangent of x. And then part B says, find the sum of the series, and series here, summation from n equals 1 to infinity, of 1 over 2 to the power of n, times tan of x divided by 2n. Alright, so now let's look at the solution to part A. So basically this trig identity we're going to try to prove. So first, recall the trigonometric identity from our earlier video, went over proof of this one. So we have this one, tan x plus y, and tan x minus y equals to, right over here, tan x plus tan y, minus, and then divided by 1 minus tan xy. The other one is going to be plus. You just switch the signs for this one. But in this case, what we're going to use is the plus, the plus version. So using x equals y equals theta in the tan x plus y identity, we get, and yeah, because you notice here's a tan 1/2 x, and what we're going to do is just write it down like this. You basically combine, we're going to combine the angles because here this just has an x, doesn't have a y. So it has both there, and we'll call it theta for now. Yeah, so thus tan of theta plus theta is equal to, and just combine that there, it's going to be tan theta plus tan theta, and then divided by 1 minus tan theta, times it by tan theta. Alright, so now what this equals to, let's just simplify this. This becomes, well, 2, just add the like terms, 2 tan theta, divided by 1 minus, now this is going to be just squared, tan squared theta. And put this down here. Now this tan theta plus theta, that's just equals to tan 2 theta. And also recall that this just equals to, well, 1 over cotangent of 2 theta. So yeah, just recall tan, yeah, cotangent is just the reciprocal of tan, which is just basically 1 over tan theta by definition. Yeah, so cotangent is just the 1 over tangent. So then this equals to right here, 2 tan theta, 1 minus tan squared theta. And then what we'll do is we're going to move this over to this side, and yeah, just move this over to this, and move this other one over to the other side. So just cross multiply across. And what we're going to get is a setup like this. Yeah, we'll get a setup of cotangent 2 theta, that's on the other side. And I'm also going to divide this out as well. So divide this out as well. So we're just going to be left with a 2 there. This equals 2, 1 minus tan squared theta. That's because this whole thing moved over to the other side. And then we're going to be dividing also by tan there. Just basically just flip it upside down, but keep the 2. But keep this 2 there. And then divide this by tan theta. So this equals 2, and you could also just simplify this. This equals to 1 over tan theta minus, and then tan squares cancel. Well, it just is going to be tan theta like that. Alright, so what this equals to now is, well, this just equals to, and this 1 over tan theta, that's just going to be equal to cotangent theta, then minus tan theta, like that, and this equals to 2 cotangent theta, 2 cotangent 2 theta, and notice that our identity is, we're looking for tan in the form of cotangent. So what we can do is just move this over to the other side. Move this over, and then move this back. So what we're going to get is tan theta And so tan theta equals 2 cotangent theta minus 2 cotangent theta. 2 cotangent 2 theta, like that. And now what we'll do is, well, we're just going to replace, replacing theta with 1/2 2x, we will get our identity. So we're going to get tan 1/2 x equals to cotangent 1/2 x minus 2 times cotangent, and there's a 2 1/2 x, that's just going to be x, like that. And this is our answer. We could just double check. So tan 1/2 x, and then cotangent 1/2 x, and then minus 2 cotangent x. So it doesn't have a 1/2 there, but it's a 2 there. And that's exactly what we have right here. So that's a check mark there. All right, now that we have part A, let's look at the solution to part B. So we need to find the sum of the following series. So this one right here, summation from n equals 1 to infinity of 1 over 2n x, and then tan of x over 2n. So let's just write that down for completeness. So n equals 1 of, this is going to be 1 over 2n of tan x over 2n. So notice this is x over 2n, but our identity is 1 over 2 to the power of x. So we want to write this identity such that we'll have a x over 2n. And we could do that by replacing x with this x over 2n minus 1. So using part A, but replacing x with x divided by 2 to the power of n minus 1, we have, and we could see that, let's just write this, tan, so instead of 1 over 2x, we'll have 1 over 2 times it by where x is right here, x over 2n minus 1. And remember, this is 1 over 2 is power of, it's the same thing as 1 over 2 to the power of 1 there, and this will cancel with this right here. I'll just erase that. So those cancel. So then this right here is equal to, well, 1 over, this just equals to x over 2n. Because you could just combine that power. So that's why we write x as, replace it with x over 2 to the power of n minus 1. So now this equals 2, and then cotangent, yeah, and this is going to be cotangent of the same thing, 1 over 2 times x over 2n minus 1, because you see the identity is the same thing. The next one, there's no 1 over 2. So, minus 2 cotangent of x over 2 to the n minus 1. And yeah, so this one right here, this just equals to x over 2n. Yeah, so let's just write that out. So what we have is right here, this is tan of x over 2n equals to cotangent of x over 2n minus 2 cotangent of x over 2n minus 1. Alright, so now that we have this, so now let's take a look at the nth partial sum of the series, and that is right over here. So let's look at the nth partial sum. So we just sum it up to n instead of up to infinity, and then later what we'll do is apply this identity to every single every single term. So let's just write this down. So the nth partial sum is going to be written as Sn, and we'll write this as summation, and we'll change a variable. So it's up to n instead of infinity, and instead of n, we'll start with I equals 1, like that. 1 over 2 to the power of I, and then we'll have tan x 2 to the I. Now this equals 2, this equals 2 tan, when you plug in I is 0, I is 1. We're just going to get x over 2 to the 1, so that's just over 2, and then I'll divide this all by 2. The next one's going to be tan of x squared over 2. Actually, not x squared, I mean x over 2 to the 4, or 2 to the power of 2. And then this is divided by, and this is 2 to the power of 2, that's going to be 4, like that. Yes, in other words, this is 2 to the power of 2. The next one's going to be plus tan, and then x over 8 to the power of 3, over, and then this can be 8. And this is again 2 to the 3. And here I quickly just moved it down over to here, and then just so we can get the next one, so we're going to go plus dot 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 plus tan of x over 2 to the n over, this is going to be n, like that. I mean 2 to the n, yeah, this is going to be 2 to the power of n, like that. So when I is equal to n all the way up to there. So that is our nth partial sum. Alright, and now what we could do is apply the identity to each of the tan functions over there. So for example, for this one right here, tan x over 2, we're going to replace that over with this. So tan x over 2, yeah, this is just same thing as x divided by 2 to the power of 1. So this equals to cotangent, it's going to be x over 2, then minus 2 cotangent of x, because you have x over 2, and then this is going to be times by, yeah, this is you don't have that 2 there, so 2 to the power of n minus 1 there. And this x, yeah, so this is the same thing as writing x over 2 to the power of 1 minus 1, so that n minus 1, or yeah, then that just goes to 0, equals x over 2 to the 0, which equals to x over 1, which equals x. So that is that part. The next one here, just to illustrate it before we put it all together, tan x over 4, this equals to cotangent of x over, x over 4 minus 2 cotangent x over 3. I mean x to the 2, not 3, x to the 2 power of 1 there. Because you subtract 1. This is 2 to the 2. 2 to the 2, this is 2 to the 1. So basically each time you have 1 less. It's 2 to the n is a 2 to the n minus 1 there. And then lastly, in this one here, just tan x to the 8, just so you understand the pattern. So tan x to the 8, this equals to cotangent x over 8. Again, this is 2 to the 3. Minus 2 cotangent x over 4. This is 2 to the 2. Like that. Alright, so now we have all that, and let's put it all together. Let's put a line here. Thus what we have is the partial sum Sn, the nth partial sum is equal to, and we're going to replace this tan x over 2 with this, but then we also divide by 2. So that means this will have it as, put a bracket like this, it's going to be equal to cotangent x over 2, that's this part, and then divide by 2, minus, this one, the 2's cancel. So this is going to be minus cotangent of x, like that. And then the next one is, we're going to add a plus. Yeah, and we're going to divide this out right here. So tan x over 4 divided by 4 now. So we're going to go over to this side and look at, and then we're going to add that here, but divided by 4. So this is going to equal to plus cotangent x over 4, divide this by 4. The next one's going to be, well, this 2 divided by 4 is going to be 1 over 2. And this is going to be cotangent x and then 1 less power, so x to the 2. X divided by 2, like that. And notice here, this cancels with this. Just notice that. And the next one here, because we're going to get a, what it's called, a telescoping sum. The next one is, we're going to replace this tan x over 8. So, and then divide by 2. We're going to replace it with this identity over here. And then, I mean, yeah, divided by 8, yeah. So we're going to divide all that by 8. So we're going to get a cotangent x over 8 divided by 8 minus, and there's always that extra 2 there. So minus 4, yeah, so divided by 4. Cotangent x over 4. So notice that these always match. This divided by 1 there matches the power. So you have this 4, 4, 2, 2, and there's 8, 8, 4, 4. They always match. And notice also this cancels with this, and this pattern keeps going on and on. The next one will have a cotangent x, a minus a cotangent x over 8 divided by 8, and those will cancel, and so on. Plus, and keeps going dot, 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 plus, and then all the way to the end. And you can see the pattern. The next one's going to be cotangent x over n, or actually a 2n. Divide this by 2 to the n, because this one's 2 to the 1, 2 to the 0. This is 2 to the 2, 2 to the 1. This is 2 to the 3, 2 to the 2. And then minus, and the powers are the same there, and then minus cotangent of x over 2n minus 1 over 2 to the n minus 1. And then this would cancel out. So notice how always the right side cancels out. All you're left with then is this and this. And I'll cancel this out too. So this equals to negative cotangent of x plus cotangent of x over 2n over 2 to the n. And I'll just put an arrow, put this Sn, and I'll just box this out for now. So that is our nth partial sum. And yeah, recall now that the above cancellations, this is known as the telescoping sum, and I've gone over that in several videos before. So let's go further. Now we have to take the limit of the partial sum to infinity to get the exact sum. Yeah, the exact sum of the series. So yeah, again, it's taking the limit to infinity. So that S is the sum equals to limit as n approaches infinity of Sn. And now this equals to, well, this cotangent of x, there's no n there, so we just take it out of the limit, the cotangent of x plus limit as n approaches infinity of cotangent x over 2n over 2 to the n. Alright, so now that we have this right here, and now just recall the trig identity, or just the definition of cotangent. So recall that cotangent theta is equal to 1 over tan theta by definition, and then the tan theta is equal it's also equal to pretty much by definition sine over cosine theta. It's actually not definition, but it's pretty close to the definition. Just an identity there, sine over cosine theta. So that's what tan, but then it's upside down. So sine over cosine, but then you're going to flip it over. So cosine theta over sine theta equals to cotangent, like that. So we're going to throw that inside that limit. So let's just take a look at that limit separately. Thus, limit as, so let's write this right here, limit as n approaches infinity of cotangent x over 2n becomes like this. I'll write this as this is a giant fraction, so there's a 2n there, and then the cotangent becomes cosine of x over 2n divided by sine of x over 2n, like that. And note that x over 2n, this approaches, well, you have x over 2 to the infinity approaches x over infinity approaches 0. So both sides we have a 0, but then what we get is a cosine 0 over, this is going to be, well, 2 to the n is infinity, times it by sine of 0, like that. And if you recall, cosine 0 is 1, and this is, so it's approaching infinity, and then sine of 0, sine of 0 is 0 times 0. So this is indeterminate, and I'll illustrate that in a bit. And I'll just write this down, indeterminate, because you have an infinity, times it by is 0, so you're not sure if it cancels or diverges. Indeterminate. And here, just recall the trig functions of cosine and sine. So recall. So if we have it like this, if this is our let's put theta. So recall that the sine looks like this, etc. So that is sine. Yeah, let's put this. This is at 1, and it's at 0, like that. This is our sine. So it's a 0 is over there. It's just sine theta. And then the cosine is just the opposite of that. So it's going to start at 1, goes to 0 there, goes to the peak here, goes to 0, etc., goes to the peak there. I'm just going to draw this side only. And we might as well keep going. So if this is at the peak, it's over at the 0, and so on, goes over here. This is the cosine, like that. And this is our cosine theta. Notice how it's at 1 here. So at 0, it's at 1, and so on. Alright, so let's continue further. So let's try to solve that. Yeah, we'll try to solve this here by trying. I'm going to multiply, the solutions manual did this, multiply the top and bottom by x. So try, let's go over here. So let's write that limit. limit as n approaches infinity of cosine x over 2n, over 2 to the power of n. This is times by sine x over 2n. So multiply top and bottom by x. And then I'm going to separate these two just to get the infinity one by itself, or separate with these 0 there. So notice as infinity, if we get it on top, so it'll be a 0 and then divided by 0. Or infinity over infinity. Just to do that, so then we could apply L'Hopital's rule. So this right here, combine these together, this just equals to limit as n approaches infinity. I'm going to write this x with this cosine. Cosine x over 2n over x, times it by, and this x here, I'm going to combine it with this x over n, 2n. So the same thing as writing x over 2n like that, over sine x over 2n, like this. Like that. Because this is x divided by 2n, same thing as writing divided by 2n over here. So we just write it like this. And now this one here, this x, we could just take it out of there. And also we know that this limit right here goes to 1. This part here, because we have this goes to 0. Cosine 0 is just approaching 1. So that means we could just take that out. So this equals 2, just using our limit rules. This equals 2, so it equals to 1. And then this x, we could just take it out anyways because it doesn't, because it doesn't have the n value variable there. So it's not part of the limit. So this just equals to 1 over x times by limit. So the only one that matters is over here. X over 2n over sine of x over 2n, like that. And now what we'll have is, remember this is infinity there, so 1 over infinity is approaching 0. And this one here is just approaching 0. So it's approaching 0 like this. This is number sine 0. It's approaching 0 there, or just equals 0. So what we have that is a 0 over 0, and this is also indeterminate, but we could write this in L'Hopital. We can solve this using L'Hopital's rule. Indeterminate again. So whenever we have indeterminate such as this infinity times 0, we want to make it such that it's 0 over 0 or infinity, and then we could use L'Hopital's rule, and I'm going to denote that by putting h on top of this equal sign. So that means we're taking the derivative of the top and bottom. So limit, and then take the derivative of this, and just for completeness for this time, but later I'm just going to do it automatically, d over dx, x over 2n. And then, just divide this all out by sine x over 2n, like that. I mean, d over dx of this. D over dx of this. Just move that over, put a bracket, etc. And this equals to 1 over x times by limit as the derivative of x over 2n. 2n just a constant, so just put a 1. So 1 over 2 to the n. And then the bottom part right here, I'll just move this limit higher up. And recall the derivative of sine is just going to be cosine. So this is equal to cosine of x over 2n. And then using chain rule, we have to multiply by the derivative of the inside. That's just going to be 1 over 2 to the n. In other words, this cancels. This whole thing cancels with the top. This cancels. This cancels. So what we're left with is, well, this cosine 0 is approaching 1. So that whole thing, the derivative is just going to be this whole limit as n approaches infinity. Let's put the limit again. I think I missed every single one. Whoops, n, not pi. Looks like a pi. Like that. And so just do that. Then this equals to, well, 1 over x times by 1 over 1 equals 1 over x. And note that this is for, well, when we have the scenario where x is not equal to 0. Otherwise, you're going to have 1 divided by 0 goes to infinity. So so you can't divide by 0 there. So note that I used the L'Hopital's rule in the above limit here. Take the derivative. And here's a reference from my earlier video. I'll just, bold this. So L'Hopital's rule, suppose f and g are differentiable and g prime of x is not equal to 0 on an open interval I that contains a except possibly at a. Suppose that you have limit as x approaches a of f of x equals to 0, and for g of x goes to 0, or you have one going to plus or minus infinity, other one's going to plus or minus infinity. In other words, we have indeterminate form of 0 over 0 or infinity over infinity. Then the limit is equal to the limit of the derivatives of f prime of x divided by g prime of x. So this one, limit as x approaches a of f of x divided by g of x is equal to the same but with the derivatives. And yeah, it's equal to it if the limit on the right side exists or is infinity or negative infinity and so on. Yeah, so thus putting this all together, we have for x is not equal to 0 or x is not equal to k times pi, and I'll get to that in a bit, where k is any integer, and then combine this together. So our s here is equal to limit as n approaches infinity of Sn. And before we even get to that, yeah, this equals to this, negative cotangent x plus, and then this whole thing becomes 1 over x. But also let's write the limit initially. So let's write the series right here. So sum of the series, summation from n equals 1 to infinity of 1 over 2n times tan x over 2n. So let's write this all out. So that's what we have is our sum is equal to, or our s is equal to the sum, is equal to summation up to infinity of n equals 1, and then 1 over 2 to the power of n times tan x over 2 to the n. And this equals 2, or actually we don't need to write s there, just write, this is, the summation is, or s, equals to the limit as the partial sum, as n goes to infinity of the partial sum, like this, Sn, and this equals 2, just put it all for completeness, just a solution manual just puts it all together. Limit as n approaches infinity of negative cotangent of x plus our 1 over 2n cotangent of x over 2n. Yeah, if you scroll up, that's just this part right here. Yeah, so limit as n approaches infinity of Sn. So we have this, negative cotangent of x, plus this right there, and this all equals to, all equals to, just move it over to this side, equals to negative cotangent of x plus 1 over x, like that. And I'll just box this in. So that is our limit, or that's our sum of the series. Alright, so that's what we have there. And also, the reason we have this x not equal to k pi, so first we all know this one, x is not equal to 0, because if you plug in 1 divided by 0 there, it goes to infinity. But if you have this, x is not equal to k pi, if x equals to k times pi, where k is any integer, recall, let's put, here, recall that, well, cotangent of x, so notice that there's a cotangent there, cotangent of x is equal to 1 over tan of x. And if you graph out the tan of x, it looks like this. This is our x, this is our tan of x, and recall what the graph looks like from my earlier videos, went over it. This is at pi over 2. This goes to pi over, negative pi over 2. So this one here, 1 over, whenever it's 0, here's at 0. Then the next one is, it's going to look something like this. And it's going to keep going. And this is, again, at 0. And this distance right here, this is pi over 2. This is going to be pi. And it keeps going on, and so on. So then this distance is going to be our pi. Yeah, so at pi or at 2 pi, etc., 3 pi, and so on. So thus, this equals to 1 over 0 is goes to infinity at, or here, just move it over here. So this, make room for it over here. So cotangent of x equals 1 over tan of x. This equals to a 1 over 0, which goes to infinity for x is equal to k, any integer times pi. So any integer times pi is always going to go to 0. That's 1 over 0. So we can't have that. Also note, for x equals 0, so instead of having to write it over here, if x equals to 0, so right here, if x equals to 0, we don't even need to do the limits or anything. We could go straight to, so if x equals 0, then summation, we could just solve the sum right away. N approach infinity, or I mean n equals to 1. Yeah, so n equals to 1 right here. Yeah, so n equals to 1. And let's just write our summation, 1 over 2n. Yeah, 1 over 2n times tan of x over 2n. This just equals to, well, tan of 0 is just 0. And then this one, whatever these are, it doesn't really matter. Yeah, because every single term is going to be 0. So you're going to have a 0 plus a 0 plus a 0, etc. And yeah, so then plus dot dot dot. And any finite n value, it's always going to be, well, 0. Yeah, divided by, even if it's a super large number, you're still multiplying by 0. And this equals to 0. So it's not, because the thing is, the difference is it's not a limit that this is going to 0. This equals to 0. So this whole thing equals to 0 when x equals 0. So we don't need to even do this equation, because we can't do it for for x equals 0 there. So yes, that is for that question. Alright, so now let's finally move on to the next problem, and that's problem 4. And here we're asked, let this sequence right here, Pn, P sub n, be a sequence of points determined as in the figure over here. Thus, the absolute value of, this is a distance, just meaning distance. So, thus, distance A, P1 is equal to 1. So you have right here, A, P1 is equal to 1. This distance is equal to 1. A, P1. This is typically how you write distances. And then then the distance Pn plus 1 equals to 2. 2 to the power of n minus 1. That is from here to here is equal to that. Yeah, that's the figure we're given here. So it goes 1, 2, and then, so this is 2 to the 1. This is equals 2 to the 0. This equals 2 to the 2. So each time it's getting bigger, 2 to the 3. So 2 to the n minus 1. So at n equals 1, it's 0. At n equals 2, it's 1, and so on. And then the angle A, P, so we have this angle right here, A, Pn, and Pn plus 1. So Pn plus 1 is a right angle, so 90 degrees there. So we're always given it's 90 degrees across there. And we're asked, find the limit as n approaches infinity of Pn plus 1. In other words, we want this angle, Pn plus 1. So this is the angle that we are asked to solve. Alright, so now let's take a look at the solutions. So here I copied and pasted it over here, just to show you that how the triangles go up to n. So we'll go to the nth triangle. So we have this right angle triangle, gets bigger and bigger and bigger, and then we have eventually dot dot dot, eventually to the nth one. I'll draw a line like this, gets super big, and so on. And this it'd be a right angle. This is A. Yeah, so I'll move it away from this A right here. So from there, so there's the point A. This point is gonna be, notice how each one here, so yeah, each time it extends from P2 to P3 there. So this is gonna be our Pn point, and then this is gonna be our Pn plus 1. And then we're going to draw a line all the way across here. And we are asked to solve the angle. Theta is here. Is PNA, Pn plus 1. So that angle, PNA, Pn plus 1. And we know that this distance right here, each of these triangles distance is getting bigger and bigger to the point of 2 to the n1. And this distance from here to here, that is our APN, like that. And just note, we can calculate this right here using Pythagoras theorem. This distance is equal to, put an arrow like this. This is our AP2, like this. This equals 2, and then just recall the triangle, the Pythagorean theorem. If you have right angle, this is A, this is B, this is C, and you'll have c squared equals to a squared plus b squared. So in this case, what we have is this distance is equal to the square root, that's the hypotenuse, of 1 squared plus 1 squared. That just equals to, well, square root of 2. Well, technically plus or minus, but we always look at the plus. I always write plus minus just because it has some good questions that arise up when you always have this minus sign to deal with. Alright, then continuing further, just note that the hypotenuse of the previous triangle becomes the base of the next one. So here's the hypotenuse over here of this first triangle. That becomes the base. So notice how it becomes the base of this next one. And then the hypotenuse of this triangle becomes the base for this one. Hypotenuse becomes the base for this one, and so on, like that. And using the Pythagorean theorem, we could write a formula for the square of the length APN. In other words, started from over here. So this AP2, let's write this like this. AP2. Yeah, notice here, so the previous hypotenuse becomes the base of this next nth triangle there. So AP2 squared, let's keep it squared so we don't need to deal with square roots every time. So if you square that, that just equals to a squared plus, 1 squared plus 2 squared, 1 squared plus 1 squared for this first one, or a squared plus b squared. So this equals to 1 squared plus 1 squared equals to 1 plus 1 equals to 2. So that's the first one. And then the next triangle, remember, that becomes the base. And then, so then AP3 becomes, well, we know this side is 2. And the next side is just AP2, like that. And then square that. So what we're going to get is a AP3 squared is equal to AP2 squared becomes, yeah, so the hypotenuse becomes the base. And then plus our other side, which increases to the 2 to the n minus 1. And this is going to be 2. Then this is going to equal to, well, we know this is 2 plus 2. And this is a square. So 2 plus 2, or 2 plus 4. And I'm not going to solve it. I'll just leave it as that. This becomes 2 plus 2 squared. Just keep it like that. Alright, and then the next one is AP4 squared. This equals to, well, AP3 squared plus, and then the next one is, well, 4. Yeah, so 2 to the 2. I mean, I know that was already 4. It's going to be 2 to the 8. So P4. Yeah, this is going to be right here. Actually, no, that is correct. This one is 4. That's 2 to the, that's 2, I mean, that was this one here, 2 squared, like that. And then this one's going to be 2 to the 2, and then we're going to square that. Yeah, because that was a distance, so the next distance is going to be 4 squared. Oh yeah, I'll do that here. So the 2 squared, 4 squared, and this is the same thing as writing, well, plug this inside. 2 plus 2 squared is our AP3 squared, plus this is the same thing as writing 2 to the 2 to the 4, or better yet, 2 to the 2 squared. Just keep it like that until we can see the pattern. Let's go to the next one. Let's see if we can grasp the next one. AP5 squared is equal to AP4 squared plus, well, it's going to be 8 squared, because we have that right here, 8 squared. So we have AP5 equals to AP4. So AP4 plus this, and we're doing the squares because we're doing Pythagorean theorem. So this equals 2, and we know this throws it over there, this throws it in there, this throws it in there, and so on. And this becomes 2 plus 2 squared plus, this next one is, yeah, let's write it again, 2 to the 2 to the 2 plus, this is 2 to the 3. 2 to the 3. And then this is squared. And then what I'll do is dot, 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 all the way to the nth one. So APN squared. And that's over here, APN squared at distance. This equals, all right. And yeah, so this one's going to equal 2 APN minus 1 squared. And then plus, and then this one becomes, notice how this setup is. Yeah, each one, so 2 to the 3. And then squared, that's we're going to have to subtract by 2. So this is 5, 3, this is 4, 2, and so on. This becomes, this is 2 to the n minus 2 squared. And if we write this part all out, this first part is going to be, well, 2 plus 2 to the squared plus 2 to the 2 squared plus 2 to the 3 squared plus all the way up to plus, yeah, plus, well, this actually just lines up, actually. Look at this one here. So this is 2 to the 1 and then 2 plus 2 to the 2. I mean, yeah, you could consider it as this is just 2 to the 1. Then it goes 2 to the 2, 2 to the 2 squared, 2 to the 3 squared, and it's all perfectly in line. So in other words, we could just add this last part to it. 2 to the n minus 2 squared. And now notice what we have here. Instead of dealing with 2's, you could write it as 4. So we could write this as 2 in the first one. And the next one, 2 to the squared, is going to be just 4. And then this next one's going to be, well, 2 squared is 4, but then you have a squared. And now for over here, we could just switch up this 3 with this 2. So we'll have 2 to the 2 to the power of 3. And that just becomes 4 to the 3. And you could see this because, well, 2 to the 3 power of 2, this just equals to, well, just using the power rules, this equals to 2 to the 6. Yeah, it's equal to 2 to the 6, and the same thing as writing, well, 2 to the 2 times 3. Or you could write it as 2 to the 3 times 2, and yeah, you could just take the 2 squared. 2 squared, 3. And this equals to 4, 3. And anyways, just a bunch of power rules there. Alright, so anyway, so we get that, and this goes continually on, plus, 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 all the way here, and then you could, again, replace these two. Replace them or switch them over, so you'll have 4 to the n minus 2. Alright, here I just moved it over there, and now this whole thing, right, what we have here is a geometric series, or I mean geometric sum, not a series, geometric, because it doesn't go to infinity. Geometric sum, or a finite geometric sum. Alright, let's continue further, so we'll go over this. So for n is greater than or equal to 3, a, p, n, the distance, and then squared, forms a geometric sum. So for this part right here, 2 plus, there's a 2 squared, that's 4. So that's our first part there. So for n is greater than or equal to 3. And then recall from my earlier video on the geometric series and sum. So the geometric series is like this. So summation from n equals 1 to infinity of a to the r a times r to the power of n minus 1, and this equals to a plus ar squared, etc. plus plus. And it's convergent if absolute value of r is less than 1, and its sum is right here, a divided by 1 minus r if r absolute value of r is less than 1. But if absolute value of r is greater than 1, the geometric series is divergent. Note that the above formula is for an infinite geometric series, or just geometric series. That's just the sum going to infinity. But for a finite sum, recall that the formula, or not that, recall the formula below from also that same video. So Sn, the nth partial sum, is equal to a plus ar squared all the way to ar n minus 1. And then partial sum is equal to a times 1 minus r power of n divided by 1 minus r. And when this goes to infinity, if you have a convergent series, this goes to 0. And hence you have this a divided by 1 minus r. If that's, and that's where the r is less than 1. Absolute value of r is less than 1. But just for general, so for the general finite sum is write it like this. Since we are not yet finding the limit to infinity, let's apply the finite geometric sum, not infinite series. So we have this, and in our case, what we have is a is r. I mean, a is 4, and then it goes from, then it goes, r is 4. So r squared, r cubed, etc. So same thing here, a plus ar squared, and it keeps going on and on. So let's write this out. So a p n squared is equal to 2 plus our 4 plus our, and here I'm going to break this apart here. So 4 squared, I'm going to write this as 4 times 4, 1. Then the next one is, the next one's cubed, so I'm going to write 4 times 4 squared. Yeah, so we'll just write this out, 4 times 4 squared, and it keeps going on and on, plus, and the last one is over here, 4n minus 2. Yeah, so we'll take that out, and then it'll be 4n minus 3, so we just subtract 1 there. So 4 times 4n minus 3, like that. So in our case, what we have is to make it like this geometric sum right here. So this is our going to be our a equals to 4. Our r is there, r equals to 4, and a equals to 4, r equals to 4, and now this part right here, our n minus 1, is our n minus 3. So I'll just write this as triple equal sign just to say that it's replacing our n minus 1. N minus 1 is our n minus 3 there. Alright, so now put this all together. This equals to 2 plus, and then we'll write our formula a 1 minus r n minus n minus 2. And because notice here, this one is Sn goes all the way to n minus 1, but the sum has it up to n. So the formula just has it n. So we so we add 1. So this is n minus 1 plus 1 equals to n. So we have to add 1 to it. So in other words, if this is our n minus 3, that's similar to n minus 1. This has to be our n minus 2 there. And I'll put this in a line right here. This is our equivalent to our r to the n. That's this is equivalent to the n minus 1 there. So, or this part right here, r to the n. And then divide this by 1 minus r. All right, so now we can input our parameter. So 2, and then our a is 4. Then 1 minus 4 and minus 2. All over 1 minus 4. And let's simplify this further. I'm going to multiply top and bottom by minus 1, just so we have the bigger numbers positive and the 1 is negative. Alright, so this equals 2, and yeah, and this is going to equal to plus 4 times it by 4 and minus 2 minus 1. So we're switching over the negative signs. And now this is a 1 minus 4. That's just a 4 minus 1. Let's put this 4 minus 1 just for completeness. And that becomes a 3. So this equals to 2. Yeah, 2 right there. I'm going to times it by top and bottom 3 over 3. And then plus 4. And let's just keep writing this further. We're actually multiply this inside. This is 4 to the 1, so we're going to add it over to here. So this is going to be 4. And then this is going to be n minus 1. And then minus 4. Then divided by 3. So we have the same common denominator. This equals to 2 times 3 is 6. So what we have is a 6 over 3. Yeah, and solutions manual doesn't actually combine them all together, just puts it as 6 over 3 like that. And then separates this one here. I'll just separate those. This becomes, and I'll move this in front. So plus, or I'll actually do that after. 4 and minus 1 over 3 minus 4 over 3. So this equals 2. 6 minus 4 is 2. So 2 over 3 minus 4 to the n minus 1 over 3. Like that. And actually I made a mistake. It's not minus, it's a plus. And this equals to our, I'll put this over here. Equals to our absolute value, or not absolute, this is just the distance. So the absolute value of the distance, APN squared. Like that. So that is what this equals to. Alright, so now that we have this, so now that we have the now that we have the lengths of two sides of a right angle triangle, we can calculate the corresponding angle at A. So let's put a bold here. Yeah, so if you go back up here, so now we know the length right here. We know this, we can solve this just using our tangent. And yeah, I should have stated that earlier, but it's pretty obvious if you think about it. So there is our right angle triangle like this. So we have this length, this is PN. So there's our point A, there's our angle, there's our PN plus 1, there's our right angle PN. We know this side is 2 to the n minus 1. It's going back above, 2 to the n minus 1, as well as in the question PN plus 1. And then this is APN, we know that now. And this is our APN distance. Alright, so now we know the tangents. Recall tan theta is equal to opposite. Yeah, so opposite over hypotenuse, adjacent. And then the adjacent is the close side, opposite is the opposite side. Equals to, and then this is our, I'll just put this all together. So this theta is equal to tan, like this, tan of the angle. You can also write it as PN plus 1. So that just means from PN A to PN plus 1. So that's the angle. And now put this all together. This equals 2. Yeah, just for even more completeness, this part right here, this equals that 2n, yeah, so that 2n minus 1, this just equals 2. Again, you can write it as pn, put the absolute value out of the way, pn plus 1, like that. Yeah, so just for completeness, so opposite is equal to the side pn plus 1 over, I'll just fix that up, and then yeah, write it as here a pn distance. So that's the opposite, and there's the adjacent, and this equals 2. We know this is 2n minus 1. This is what we're given, and here is our giant formula. Now we're squaring it. Yeah, I mean we're square rooting it. This is apn squared. So you take the square root plus or minus, but we're obviously going to take the plus. So it's going to be plus, and then 4n minus 1 over 3. Like that. So we have that over here. Yeah, so all that together inside. And now we're going to take a limit and so on. But before we even do that, let's just do this first. Yeah, I'm going to write this in the form of this 4n minus 1. So note right here that, yeah, 2n minus 1. So this part right here. Simple, just rewrite it out. This equals 2. It's the same thing as writing 2 to the n minus 1 squared and then square root. So we're not changing anything. Just gonna get it back and forth. And then what we'll write is equals 2. Yeah, equals 2. And we'll bring this 2 down. So this equals to square root of 2 to the 2n minus 2. Or actually, better yet, do that same thing as before. We'll just take this power and flip it with this one. This equals to 2 to the 2 times by n minus 1. And this equals 2, or I'll just keep it over here actually, square root 4n minus 1, like that. Because we have this, and then all square root there. So, and then we're going to replace that over to that one there. So, what we'll have is thus, put it like this, thus, and scroll up. Yeah, so thus tan theta is equal to, and we'll write this, replace that with 4, and 4 to the power of n minus 1, all square root, and then divide this all by square root 2 over 3 plus 4n minus 1 over 3. And since we're going to take a limit soon, let's multiply top and bottom by this so we can do some cancellations. So 1 times it by 1 divided by 4 to the n minus 1 divided by 1 divided by 4n minus 1. So we're not changing anything again. Let's multiply top and bottom. Alright, so then the top parts cancel. We just have a 1. And then the bottom part, the square root, we can just put that inside. So it's all a giant square root. And let's do this. This is going to be, so when you take the square root, yeah, you just take that out of there. So 2 over 3 times it by, or else put the 2 under, or 2 on top, 3 times 4n minus 1. And then when you bring that inside, this cancels, so we're just going to be left with plus 1 over 3. Alright, so that's what we have there. So thus, limit as n approaches infinity of tan theta equals to limit as n approaches infinity of 1 over square root 2 over 3 times 4n minus 1 plus 1 over 3. And notice this part right here, as it goes to infinity, this is 2 over 3 times it by 1 over 4 to the infinity. So in other words, we're going to have a 1 over infinity, 4 infinity go to infinity, this goes to 0. So this equals to 1 over square root 0 plus 1 over 3. 0 plus 1 over 3. And this equals, alright, and this equals to 1 over, well, we can move the 0, and square root of 1 is just 1, so this can be 1 over square root 3. So 1 divided by square root 3, that's just equals to, bring the 3 on top, square root 3. And now if we just recall our exact trigonometric ratios, and in particular if we look at an equilateral triangle, so instead of just recalling from my earlier video, I'll just derive it now. Yeah, it's pretty much from my earlier video, just it's easy to memorize. All right, so let's draw this equilateral triangle, and let's say the length is 2. This length is 2, and then put this all the way, cut it down in the middle. This is, this whole length is, also 2, but I'm just going to put one here, so it's split in half. And remember, a triangle has a 180 degrees or pi total angles. So I'm going to divide this pi over 3. So each one's pi over 3, but then we're cutting this in half. This is going to be our pi over 6, like that. And then this height right here is our square root 3. Now that's from Pythagoras. And again, recall that's just going to be, this is going to be square root. This is going to be equal to, square root, the hypotenuse squared minus the base right here, this squared. So this equals to square root 4 minus 1 equals to square root 3, like that. So that's square root 3, and notice what we have here. So we have our tan theta limit as n approaches infinity equals square root 3. So in our case, well, we have this right here. So the exact trig ratio, tan pi over 3 is equal to, well, opposite over adjacent equals to square root 3 over 1, which is just square root 3. So in other words, our angle, so I'll just put this all together, and put it all together. So thus, the limit as n approaches infinity of the angle PNA to PN plus 1 is equal to pi over 3, or in other words, 60 degrees. This is 60 degrees in degrees, or in pi over 3 radians. And we can just box this whole thing like this, and we'll just write this as 60 degrees, like that. Remember this exact trig ratio, 60, 60, and then we'll have another 60, and that will be 180 degrees total. So there's 60 degrees, and that is that angle right here. PN plus 1. That's what we were asked. That's the angle. Anyways, let's continue further. All right, so now let's take a look at problem 5. So to construct the snowflake curve, start with an equilateral triangle, so all the sides are the same, with sides of length 1. And then step 1 in the construction is to divide each side into 3 equal parts, and then basically construct an equilateral triangle on the middle part, then delete the middle part as in this figure. So step 1 is to divide each side into 3 parts, and then construct an another equilateral triangle in the middle part, and delete it. So in other words, so we separate this into 3 parts, draw a triangle, and then delete this part, and we're gonna be left with this, and do that for all 3. 1, 2, 3. So there's 3 there. So we divide those all in the middle. And step 2 is to repeat step 1 for each side of the resulting polygon. This process is repeated at each succeeding step. So initially we had 1 triangle, then we had to make 3 more on it. So 1, 2, 3. And now each one of these, we're going to make 1, 2. Then make 1, 2, and then add another one here and here, here, and so on. So let's take a look at how this one is. So remember, this was that earlier triangle. This is the earlier triangle, but now we added 2 onto it, onto each one of these segments here. But then now with this one, because you have another one here, here, so you're adding 2 on every single one there. It's just fascinating stuff. So it looks like that, and then you keep doing that again onto this, onto this, onto this, and then you become this. So yes, you can see how it looks like a snowflake now. So the snowflake curve, is the curve that results from repeating this process indefinitely. So you keep going on and on like a giant fractal. So now we're asked for question A. Let Sn, Ln, and Pn represent the number of sides, the length of the side, and the total length of the nth approximating curve, the curve obtained after n steps of the construction, respectively. And then it says, find formulas for Sn, the number of sides, Ln, the length of a side, and Pn, which is the total length of that curve. And notice here, every single one of these is exact same lengths. So we have exact same lengths on everywhere, even these all become exact same. This exact same. This is dividing it in thirds there, and that is these are all the same sides. So it's always equilateral triangles everywhere. So, and then part B says, show that Pn approaches infinity. So the total length Pn approaches infinity as n approaches infinity. And then C, sum an infinite series to find the area enclosed by the snowflake curve. And then it says, note parts B and C show that the snowflake curve is infinitely long, but encloses a finite area. Fascinating stuff. Alright, so now let's take a look at the solution. So solution to part A. At each stage, each side is replaced by 4 shorter sides, each of length 1/3 of the side length of the preceding stage. And we can see this, but let's just draw our triangle like this, our equilateral triangle. I'm going to write it like this. And then the first one here, I'm going to cut this up like this. We'll do this actually twice here. So I'm going to cut this up right there. So initially we had side length L, and then we have divided it into 3. So this can be L/3. This is going to be L/3 like that. And then we're going to have a triangle like this. And these are all exact same length. So instead of having one giant length one, we're going to have 1, 2, 3, 4. So this one is 1 and is replaced by 4 shorter sides. And these are all equilaterals. This is going to be side L/3. And this is going to be L/3. And this is going to be L/3. And we're... Yeah, so this side is, it goes from one side to 4. And each one of them is a third shorter. So now, and you'll see this pattern keeps going on even if we do another one. So let's do another one right here. So if we have right here, and then split this in half. So this is L/3, these are equilateral, and then you're dividing this by 3. So then this is going to be L/9. And they're all equilateral, so this is also L/9. And yeah, so it goes from one side here, one small side, it goes to 1, 2, 3, 4. And then again, there's another L/9. Because they're all equilateral triangles. Like that. Alright, so now writing S0 and L0 for the number of sides and length of the side of the initial triangle, we can generate the table below. And also just note, on solution A, we're just asked to find the formulas for the number of sides, the length, and the total length of the curve. So what we'll do is start S0 and L0 for the number of sides at the beginning. So let's write this down. So the first one, we have just a regular triangle, just one triangle, equilateral triangle. We have 1, 2, 3 sides. So our S0 is equal to 3 sides, and our length L0 is equal to 1. So they're all length of 1. So that's what we start off with right here, all length of 1. So that was the 0th one, and now the step 1. Yeah, so we'll put a 0. This is the 0th, so we'll start off at 0. Now we go to the step 1, and we go from right here. So we split this up like this, and then this goes like that, and like this. So each one of them is split. And it goes like that. Actually, no, it keeps going, actually. Yeah, actually, it's like this. And that is our 12-sided triangle. The 6-pointed triangle. The 6-pointed star, actually. Yeah, so 1, 2, 3, and then 3 at the bottom. So let's count the number of sides. We have 1, 2, 3, 4. So those one side becomes 4, and each one of these does that as well. So we just multiply by 4. So S1 equals to 3 times it by 4. So we multiply that 4 3 times, and the length is going to be half. So a third. Each one of them is a third. So L1 equals to 1/3. And then step 2, we do the same thing, and what we'll get is, well, each one of these sides becomes 4. So this one here, I'm going to write this like this. So this one right here, write it over here. So it's going to go like this, and it becomes a triangle. It becomes 4 sides. Like this, and then this other one becomes 4, then this other one becomes 4. Oops, let's do this again. This becomes, and then this goes like that, and this one here goes to 4 like that. Now let's erase this arrow. So notice here, this becomes 4. This becomes right here is a 4. Each time there's a point, there's 4 sides. And there's another 4 right here. So there's four of those. And I'm not gonna, yeah, then you just multiply it by 3 on each side. Yeah, so this one, then you can do that same thing on here and here. So this multiplied by 3. So in other words, we're gonna get S2 is equal to 3, and this is 4 times 4. So it's 4 times 4, that's just 4 squared. And then L1 is equal to 1 over 9, or 1 over 3 squared. So each time it's half of the previous one. So 1 over L squared, and it keeps going on and on. And then just put dot, 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 and then this, yeah, this keeps going on, dot, dot, dot. So the nth construction, we get Sn is equal to 3 times 4 to the n, then Ln is equal to 1 over 3 to the n, like that. Yeah, so in other words, we got the number of sides and the length, and then we could just find the total side length, the total perimeter around it. Yeah, so multiplying the side length with the number of sides, we get the total length of the perimeter at the nth stage of construction. Or yes, we get that is, I'll remove this is, but just get the nth stage. So Pn is equal to the total number of sides times the length of each side, which equals to, this is going to be 3 times 4n times it by 1 over 3n. And combine those powers there. So this is 3 times 4 over 3 power of n, like that. So that is our total length. So we have answered question A. And let's look at question B now. So that's question A. And now question B, yeah, so that's question A, find formulas for them, so we found them all. And question B says, show that P sub n goes to infinity as n goes to infinity. Alright, so let's look at solution to B. So taking the limit of the perimeter length we get, and let's write this limit as n approaches infinity of Pn, this equals to limit as n approaches infinity of 3 times 4 over 3n. So in other words, this just goes to, well, infinity, because what we get is a 3 times 4 over 3 infinity. This is going to 3 times infinity, it's just infinity. There it goes to infinity. So it's equals to infinity, and this is since 4 over 3 is greater than 1. And yeah, that's also similar to that earlier limit we went over. So because it's greater than greater than 1, it goes to infinity as you take it to the power of infinity. So yeah, so that's what we have. Alright, so that's infinity, and now let's take a look at solution to C. So part C, let's just see what it was. So see, sum an infinite series to find the area enclosed by the snowflake curve. So find the actual area there. So let's take a look here. So solution to C, the area of each of the small triangles added at a given stage is 1/9. So that's a key one. I'm just going to bold up. Of the area of the triangle added at the preceding stage. And just to illustrate this, so let's say we have, an equilateral triangle like this, and length is, and it's all, so the base is B, like that, and then the height here, I'll just back and back. Yeah, let's write this better here. So let's say the height is, here is a right angle, and this is all lengths B, and then the height is H, and let's say you had an angle here is theta, like that. So the area, recall the area of a triangle is just base times height divided by 2. And now what are right here, we could write the sine, we could write the h right here. So we want to solve for h. So we could write, recall sine is equal to opposite over hypotenuse. That just equals to h over b. H over b, so move it around. So h is equal to sine, just move this over to that side, sine theta times h. Sine theta times b. I'll put this here. b times sine theta. So throw that inside, and we're going to get a b times b sine theta, like that, all divided by 2. And then just square that. This equals to b squared 2 times by sine theta. So that is what the area is for this triangle. I'm just going to bold this. So that's for any given triangle like that. But in fact, we're not just dealing with just any triangle. This is an equilateral triangle, so this is going to be pi over 3, actually. So remember, that's just pi over 3. I'll just put this like this instead of actually solving it. Pi over 3. So all of these are pi over 3. And they're all equilateral triangles. Alright, so we have that. So for so now for the next triangle after that, thus for length of or better yet, just write for side length, and then let's say we have a third of that. So for side length b over 3, then the area is equal to, well, we already know that because they're all equilateral triangles. So this is going to be this area, but then we'll replace b with b over 3. So b over 3 squared over 2. And then times it by sine, times it by sine pi over 3. Like that. So this just equals 2, well, equals to, this is 3 over there. I'm just going to square that. So this is going to be equals to 1 over 3 squared times it by b squared over 2 sine pi over 3. And so this is the previous one. Oh, this whole thing is a previous length. Yeah, so I'll just write this as A1, and let's call this A2. This is A1 then. So the previous one. So A2 is equal to 1 over 9 times it by A1. So it's 1/9 of the previous one. And we can bold that here, or just circle it. So there it is. At any given stage, it is 1/9 of the area of the triangle added the previous preceding stage. Alright, so let A be the area of the original triangle. Yeah, so then the area AN of each of the small triangles added at stage N is, and let's just write it down. So let's say the 0th one, we have A is the area. Then the A1 is equal to A times it by 1 over 9. And then A2 is equal to A 1 over 9 times it by 1 over 9. Or spread this as A1 times 1 over 9, which is equals to A9 squared. And then dot dot dot, just for completeness, it goes AN equals to A divided by 9 to the power of N. So notice when A2 is just A divided by 9 power 2, A1 is A times 1 divided by 9 to the power of 1. Times it by 1 divided by 9 to the power of 1. So that is what our AN is. Alright, so now since a small triangle is added to each side at every stage, it follows that the total area AN added to the figure at the nth stage is, so this is the extra area. So we start off from the beginning. So let's say we start off here, and then we're going to add an extra, so this is A, we're going to add an extra A over 9, an extra A over 9, an extra A over 9 at each side. So initially there's 3, now we're adding 3 at each side, so 1 at each side, A over 9. So we're adding all these extras. So we could write this as, so at the nth stage, so what we'll do is, AN is equal to SN minus 1. This is the previous stage, or previous sides. Number of previous sides. And then times it by AN, new area added. This is the new area added. Yeah, so initially for the first construction, we're adding 3 triangles to the 3 number of sides of the original triangle, and then this is going to equal to, well, we know the number of sides right here. This equals to 3 times 4 n minus 1, and that is just from the above. Remember our formulas. So we had set up for part A. So Sn equals to R times 4 to the power of n. But we're looking at the previous one, so n minus 1. And then so then we'll put a Sn minus 1 is equal to 3 times 4 times 10 times n to the power of n minus 1. And the next one is an. That's just over here. That is a over 9n. And note here we can combine this 9n and this 3 because they both have the same factor, which is 3. So note right here. Yeah, note 3 over 9, and this equals to, well, 3 over 3 squared. 3 squared to the power of n. That's just the same thing as writing 3 over 3. Yeah, 3 over 3 2n. Again, it's all just power rules. And then now we get to subtract this over. So we can write this as 3 to the power of 1, move that downward, so it's equals to 1 and 3 to n minus 1. All right, so we have this, and then we could throw that inside. So this equals 2, and put the a in front, times 4n minus 1 over 3 2n minus 1. And so that is the area added at each subsequent construction. So each time you do the new snowflake construction, you're adding area of this, which is a of the original, times it by 4 to the power of n minus 1 divided by 3 times 3 to the power of n minus 1. Alright, so moving forward, so then the total area enclosed by the snowflake curve is, total area, we'll just write that as a. This equals to lowercase a is the original, so original triangle. So original triangle, and then plus a1, that is step 1. Step 1 triangles were added, then we're a2, and that is step 2, plus a3, plus dot dot dot, and again this is just dot dot dot. So we're good. That's to be step 3, and so on. And each step is this an that we're adding there, and I'll just write that here all the way plus an, so the nth step there. Well, actually, we're not going to n, we're going to infinity. So it just keeps going on. I'll remove that an. So that's just over to an, or you could just write an and then plus dot dot dot, etc. All right. So what this will equal to is equals to a is equal to lowercase a plus, and now a1. So that's n equals 1. We could put that in here. So when you have 4 to the n, to the a, or to the 1 minus 1, that's 4 to the 0, that's equals to 1. And then here, if you put a n equals 1 here, you'll have 2 minus 1. That's just 1. So that equals to a times it by 1 over 3, and then I'll just put a bracket here. This part is just the 4, 1 minus 1, over 3, 2 times 1 minus 1, which equals to 4 to the 0, over 3 to the 2 minus 1 is 1. It is 1 over 3. So that's just 1 over 3, like that. All right. And then the next setup is plus, and then when we have n is 2, this will be 4 to the power of 1. This will be 3 to the power of, this is 4 minus 1, that'd be 3. So this will be, again, another a times by 4 power of 1, 3 to the power of 3. And the next one's going to be a 4, and it's going to be 2, because when you put a 3 in, 3 minus 1 is 2. And this one, 3 times 2 is 6, minus 1 is 5. So notice the pattern now. 3 to the 5, like that. And then the next one is just going to be a 4, 3, 3, 7. So it goes every odd. This one is every single one, plus dot, dot, dot. And put this in a bracket like that. And notice what we have here again. This is another geometric series. And I'll show you that. So this is a geometric series. Whenever you have something increasing like this, where there's power 1, 2, 3, and then even this one is odd, but they're all in the same number. So it's 3, it's just separated by 2. So 3, 5, 7, etc. This is a geometric series. Geometric series. And what we could do is, well, let's just determine the terms. So this is, recall a geometric series. We have a plus AR plus AR squared plus etc. dot 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 all the way until forever. Yeah, so in our case, what we have is we have A and then this is 1 minus 1 over 3. So we have a over 3. This could be our equivalent of our a, like this. So this could be our a. So that's this part right here. And then what we have is plus, and then, yeah, so that's our a. So hey, a is multiplied everywhere. So notice how it's multiplied everywhere there, 1 over 3. So we'll put this a over 3 right here. And then the next term is going to be r. And this is going to be, well, 4 over 3 squared. So 4 to the 1 over 3 squared. And notice here, so 3 squared, this is a 1, so these combine, so you'll have 3 to the 3, so that's just this one right here. And then the next one here, you can start seeing the pattern. A over 3 again, that's our a. And then this will be a 4 there. So then this would be a 4 over 3 squared again, but then squared there, so that the bottom is a 4. Is a 4 like that. So basically, we could just put this in a bracket, and you're seeing that this is actually the r value. And put it like that. Yeah, just fix that up and fix this up to 3 squared. Yeah, so notice here. So when you square this, you get a 4 squared. And this will be 3 to 3 squared. Squared will be 3 to the 4. But then you already took this out. Add those up, that'll be 3 to the 5. So in other words, r is equal to 4 over 3 squared. And let's just do one more here. A to the 3 times it by 4 over 3 squared to the power of 3. So then this would be 4 to the 3, and then 3 squared cubed, that'll be 3 to the 6 plus 1, 3 to the 7. So 3 to the 7, and there's 4 cubed there. Plus dot dot dot. Let's put a closed bracket like this. Because we already have the regular brackets there. So now this one here, 4 over 3 squared is equal to 4 over 9, and this is less than 1. And remember our geometric series, if the absolute value of r is less than 1, it's convergent, like that. Alright, yeah, so this is a convergent geometric series, so now we can apply the formula for it. So using the formula for the sum of a convergent geometric series we get, and we already gone over it several times in this video, that's going to be a divided by 1 minus r. So we get is the area, or the total area is going to equal to the original a plus, and then this is going to be our a minus 1 over r. So in our case, our a is our a over 3 divided by 1 minus our r, and our r is going to be our 4 over 9. So remember, this is our equals to our a in our formula, and this is our r in our formula. And I put this 3 lines for equals to say that this corresponds to it. It doesn't actually equal to a because we have an a here. Just to show that we're not talking about this a. We're talking about this one here. So it just corresponds to. So what we'll do here is, multiply the top and bottom by 9. And here just made that a bit more clear. And also, times by 9 on top and bottom, so we can do some cancellations. This will cancel, will just equal to a 3. This will just cancel, because 9 is just 3 times 3. And what we get is, and this is going to equal to, this will equal to a, and we're only doing it on this fractions, plus, then we'll have an a on top, and then this 1 minus 4 over 9, well, that's going to be 9, we're going to multiply it inside, minus 4. So that's just a 9 minus 4 there. Yeah, fix that up. So this would be 9 minus, minus 4, just like that. So then this equals to a plus a over 5. And forgot the 3 here. So we forgot this 3. So this is going to be 3a, and there's going to be a 3a over 5, like that. So times this one here, times it by 5 over 5. What we get is, so this whole thing equals to 5a plus 3a, so we have the same common denominator of 5, equals to 8 over 5a. So that is our answer. Or put that together, 8a over 5. So that is our total area of the triangle, of the snowflake. And now we just need to solve for the area of the original triangle, and we could use a sine function, or we'll just do the we'll just use Pythagoras right here. So remember, these are equilateral triangle. Just do this for completeness. Draw this. Remember, in the sides were 1, 1, and then we have a 1 right here, and also the h right here. This is, let's go 1/2, 1/2, and we already solved h earlier, but we'll just do that again. Yeah, so h is equal to, well, let's just go over here. So the hypotenuse squared, 1 squared, equals to h squared plus 1/2, and then all squared, like that. And that just equals 2. And then we'll just solve it. H squared is equal to 1 minus 1 over 2 squared is 4. And square, yeah, then basically square both sides. So h is equal to plus or minus. This is 4 times 4. Plus or minus, this is square root 3 over 4, like that. And here's move that over. So this equals 3 over 4, square root both sides. And take the positive always. So it's going to be square root 3 over 2, because 4 square root 4 is just 2. And yeah, just for completeness, this one, I always do this 4 over 4, same common denominator, and that becomes that. So that is our h. So that's our h. And now we put that in our area formula. So a, or I'll put lowercase a because we're dealing with a equals to base times height divided by 2, which equals to base is 1. Yeah, base is 1. This is 1/2, and that was just for this Pythagoras. But base is b, like that. And move this away. And then base, then height is going to be, and this is divided by 2, square root 3 over 2. Yeah, that's our h. So then this becomes, yeah, and yeah, just throw that in there. This becomes square root 3 over 4 is equals to a, like that. So that is the original area. Yeah, so the area enclosed by the snowflake curve is, and then this is 8a5. So total area is equal to 8a over 5, which equals to 8 over 5 times by square root 3 over 4. Like that. This cancels, be a 2, this cancels, and we're left with equals to 2 square root 3 over 5. Absolutely amazing. So we were able to solve the area of an infinitely long snowflake curve. All right. Yeah, so the solution manual just stops here, but let's go a bit further. So for further context, let's calculate the original versus snowflake areas. So the original a, lowercase a, is equal to square root 3 over 4, so that's over here. That area is equal to 0.433012, etc. Keeps going on and on. And this is just with my built-in calculator on OneNote, so equals the space like that. And then you could also do it over here. And then compared with the large area, or the total snowflake area squared 3 times 2 over 5, that equals to 0.69. And here's 0.69. And then the percent increase, so if you subtract the total area minus the original area, and then divided by the original, so we get a ratio, times by 100, you get 60% point. Yeah, so it's a rounding error here, but it should be exactly 60. So yeah. Calculator gives this one 60%, 0.000 all the way to 112. And the percent increase, yeah, if I use the equations as opposed to the results of it, so there's less storing. And then if I do just go square root 3 times 2 over 5 minus square root 3 over 4. This is a, that's capital A, divided by the original a, and times by 100 equals to 60. Yeah, so there it is. It just if you right away press space, it automatically calculates. And this one all the way to 0.1 there, so it's slightly more accurate. But MES note, likely a calculation rounding error, since the exact answer is 60%. And there's a link to Wolfram Alpha. And yeah, so Wolfram Alpha calculator has it exactly that. And yeah, here, if I just go to Wolfram Alpha, so there's a link, click it, it goes to here, and you get this square root 3 set up here, times 2 over 5 minus square root 3 over 4. Then divided by square root 3 over 4, and then times 100, exact result is exactly 60. So yes, fascinating stuff here. All right, so now let's go further and look at question 6. Or actually not question 6, problem 6. All right. Alright, so problem 6. So this one states find the sum of the series 1, and then you have 1 plus 1/2 plus 1/3 plus 1/4 plus 1 over 6 plus 1 over 8 plus 1 over 9 plus 1 over 12 plus etc. dot dot dot, where the terms are the reciprocals or 1 over of the positive integers whose only prime factors are 2's and 3's. Alright, so now let's take a look at the solution. So this looks like a pretty complicated question, but again, just a lot of terminology. So reciprocals and prime factors, etc. So a solution, first note that prime factors are prime numbers that can divide into a number cleanly. And a prime number is a number that only has 2 factors, itself and 1. So for example, this example is 1092. So yeah, 1092. If you divide this by 2, you get 546. And divide that by 2, you get 273. Divide that by 3, this equals 291. And then divide that by 7, you get 13. And yeah, these are all prime numbers here. So you can't divide 13 cleanly by any way except 1 and 13. Same with 3, same with 2, same with 7, etc. So prime factors of 1092 are 2, 2, 3, 7, 13. And you could even try that here. 2 times 2 times 3 times 7 times 13 equals 1092. So you could keep dividing those out and so on. And the reciprocal of a number is of the form 1 divided by x. For example, 1092, the reciprocal of 1092 is 1 divided by 0, or 1092. So just flip it over. So let's call the series, this one here, S. Then every term in S is of the form, and it's because, note here, its reciprocals are the positive integers whose only prime factors are 2's and 3's. So it can only be divided by those prime factors. It can't be divided by 7, for example, 13, and so on. Yeah, so what this means is then every term in S is of the form 1 over 2 to the power of m times by 3 to the power of n. Like this, where n and m are integers. Yeah, are integers greater than or equal to 0 and integers. Yeah, so they're integers greater than or equal to 0. And for example, so if we write our S series, so let's say our S, let's put an arrow here. S is equal to, so we have our 1 plus 1/2, just write it all out and compare the difference. So 1/2, 1, 3, 4, there's no 5 there. 6, 8, 9, there's no 7 because you can't divide by that. 7 is a prime factor. 5 is as well. It's a prime number. 5 and 7 are prime numbers. You can't have those, and you keep going. You can't have 10 because 10 divides into 5 and 2. You can't have 11 because 11 is a prime number. So this will become 1 over 3, 1 over 4, skip the 5, 1 over 6, plus 1 over 8, skip the 7, 1 over 9, plus 1 over 12. Like that, just dot, dot, dot. And, well, actually, yeah, we don't need to go that far, but anyways. So this equals to 1 plus, so write this in this form. So 1 over 2 is equal to 2 to the 1 and times by 3 to the 0. This 1 over 3 is equal to 1 over 2 to the 0 times 3 to the 1. And this 1 over 4 is equal to 1 over 2 to the 2. So that's a double factor of 2. And 3 is 0. This next one is 1 over 6 is 2 to the 1 times by 3 to the 1. So 2 times 3. Plus the next one, etc. You see the picture. Let's do one more. 1 over 8 is 2 to the 3. And then 3 to the 0. Honestly, let's keep going. It's pretty fun. And then the next one is 2 to the 0 times 3 to the squared. The next one is 1 over 2 to the 2. So that's 4 times 3 to the 1. 4 times 3. And so on. Plus dot, dot, dot. Yeah, so that's what we have. And furthermore, each term occurs only once. So there's no repetition here. There's no 1 over 9 plus 1 over 9, etc. So it just keeps going as one of each time. And so now we can apply a double summation because we don't need to worry about it doubling up like that. I mean, so we don't have it the same term. So we just do a double summation and noticing that we obtain 2 convergent geometric series. So that's actually pretty amazing here. So the total sum S, or total series S, the summation is equal to summation from M equals to 0. And then so we have a double one because we can sum up all the way M to infinity and also N to infinity, and they all alternate. So we have 1 0 0 1 2 0 1 1 3 0. Then we also have 0 2 2 1 and so on. So we'll have every single term there, and then N equals to 0 here up to infinity. And yeah, here we're summing up two things, and that's going to be this 2 over M, to the power of M, and 3 to the power of N. So it's going to equal to 2 to the M times it by 1 over 3 to the N, like that. And what we could do here is we could separate these into two summations instead of a double one, two like this, and multiply by each other. So this is M equals 0, separate as 1 over 2M, times it by, like this, infinity, N equals to 0, and then it's 1 over 3N. And the reason we could do this is, these are just summation rules, but also you could see over here. But first I'm going to remove this 1. I'm going to write this as 1 over, just to be complete, 2 to the 0 times 3 to the 0, which is equals to 1. So notice here what we do. So this basically means we could factor out every single one of these terms out. So I'm going to look at the 2 to the 0. I'm going to look at that 2 to the 0 there. There's another 2 to the 0. And notice what we have. I'll also erase this. Yeah, put this back. Yeah, so what we have is, notice here, so we could factor out this 1 over 2 to the 0. And then we're going to be left with this 1 over 3 to the 0, plus 1 over 3 to the 1, plus 1 over 3 to the 2. And the next one's going to be 3 to the 3. The next 2 to the 0. We'll have a 3 to the 3, which is 3 times 3 times 3 is just 27. So in other words, we could do this keep going on to infinity. And then we could do the same for this one. Then we could do the same for this 2 to the 1, this 2 to the 1. And keeps going on and on. So in other words, we could factor out all of the 3 to the n terms, and then we'll have an entire series all with just 2 to the m terms. So in other words, we could just sum it up like this. So yes, we could factor out and it will look exactly like this. So yes, we could do that. I'm going to leave these circles and lines like that just to illustrate how we could factor it out. Yeah, so that's what we have. And now this equals 2. And well, this right here, we have over here is just two geometric series, and in fact they are both convergent, and we'll see that here. So this part is A is equal to 1 over 2 to the 0. This equals to 1. And then the R is equal to, well, just 1 over 2. And notice this is less than 1, so in other words, it's a convergent series. So whenever you have this M or N, and then it goes in increments 1, 2, 3, 4, 4, etc., or even or any sequential one, not multiplying. So this is separated by 1. So 1, 2, 3, 4, etc. Or it could be 2, 4, 6, 8. It will still be a geometric sum because then the R will just be different. So what we have is that. Then what we have here is A is equal to 1 over 3 to the 0, which equals again 1. And R in this case is equal to 1 over 3, which is also less than 1. So in other words, these are both convergent series. So right here, both convergent geometric series. Let's put GS. Yeah, so what this means then is, well, our S is equal to, we just now do the formula for both. A is 1 for both, then 1 minus 1/2 for the first one. And then times it by 1 over 1 minus 1/3. That's the R of this one. So that's R of the first, is R of the second, and so on. Now we'll just do some simplification. To multiply 3 over 3 on this side, 2 over 2 on this side, so we could sum these up. So this equals 2. 1 over 2 minus 1 is just 1/2. And combine those, same denominator. Times it by 3 minus 1 is 2. So 2/3 like that. And what we have is, well, 1/2, and there's a 2 on top. This cancels. And this is, we're just going to be left with 1 over 1/3. So in other words, this equals to 1 over 1/3. Let's put this a bit bigger. 1 over 1/3, so the 3 just goes on top. This equals to 3. So the sum is equal to 3. So all that, and just to show you, the sum is equals to 3, which is quite amazing actually, because so this entire setup here, where you're dividing by the prime factors that are of 2s and 3s, and you sum all that up, you just equals to 3. You go to infinity, and it approaches 3, which is absolutely fascinating. All right, now let's continue further, and now let's look at problem 7. And so it has, let's see, how many parts is it? 6 parts. So it's part A says, show that for x times y is not equal to 1, that arctan of x minus arctan of y is equal to x minus y divided by 1 plus xy. If the left side lies between negative pi over 2 and pi over 2, and positive pi over 2. And then part B says, show that arctan 120 divided by 119 minus arctan 1 divided by 239 is equal to pi over 4. And then part C says, deduce the following formula of John Machen. He was born 1680, died 1751. Of 4 times arctan 1 over 5 minus arctan 1 divided by 239 and equals to pi over 4. So deduce from that. And then part D says, use the Maclaurin series for arctan to show that arctan 1 over 5 is between this right here, 0.197395557, and over here, 0.19739555616. Then part E says, show that arctan of 1 divided by 239 is between this number, so 0.0041840075 and 0.0041840077. And then lastly, part F, deduce that, correct to 7 decimal places, pi equals to 3.1415927, and Machen used this method in 1706 to find pi, correct to 100 decimal places. Fascinating. So recently, with the aid of computers, the value of pi has been computed to increasingly greater accuracy. In 2009, T. Daesuk and his team computed the value of pi to more than 2 trillion decimal places. Fascinating. Alright, so now let's take a look at the solution to part A. So part A says, show that for xy is not equal to 1, and you have arctan x minus arctan y equals x minus y divided by 1 plus xy. If the left side is between negative pi over 2 and pi over 2. So let's just write this out. Arctan x minus arctan y equals to arctan x minus y over 1 plus xy. Yeah, just scroll up here. So arctan x minus arctan y equals x minus y divided by 1 plus xy. And just recall the definition of arctangent, or just whenever you're dealing with this arc or this inverse tangent or inverse trigonometry. So if you have something like this, a triangle, here's the theta. So that's theta. If you have opposite right here, opposite, and then you have adjacent, and we're dealing with tangent, so tan theta is equal to opposite over adjacent, just a general definition. This means that, well, the arctan of the ratio opposite over adjacent is equal to theta. So basically, you're looking at the inverse of it, so you're solving for the theta. So when you have theta, that's the arctangent there. Alright, so now let's start off with this. Now that we have that, so let A equals to arctan of x and B equals arctan of y. So then this formula that we're trying to show, basically show that A minus B is equal to arctan of x minus y. X minus y over 1 plus xy. So that it is what we want to show. So show... show this one, or just move it over and write show that A minus B of equals to arctan x minus y divided by 1 plus xy. And now if we compare this that we're asked to show with this right here, well, we could see that arctan, this is the opposite of our adjacent, and this is the theta, is right over here. So this is equal to our theta. I'll just put a theta right there. And similarly, you could write this this trig identity right here as tan of a minus b equals to x minus y, 1 plus xy, where this is, yeah, that is theta. Yeah, so basically this is exactly what we need to prove. So basically we can now use the trig identity for tan a minus b and then try to prove that it's this. And then hence we've proven our identity that we're asked to prove. Alright, so now continuing further, so recall the earlier formula I referenced above in the, I think the other question. And now take a look right here. Yeah, so we had tan x plus y is equal to this, and this is tan x minus y equals to this tan x minus y, and then divided by 1 plus tan x tan y. And we're going to use this identity, throw that inside, and basically try to prove that it's equal to x minus y, 1 plus xy. So let's jump right ahead and do that. So using the second formula we have tan of a minus b is equal to tan a. So instead of x we use a, instead of b we use y. Tan a minus tan b over 1 plus tan a tan b. And now we could plug in our a and our b's. Number a is equal to arctan x, and b we let it equal to arctan y. So that means this equals to tan of arctan x minus tan of arctan of y. I'll divide this by 1 plus tan arctan x times it by tan arctan of y. And yeah, now that we have this, note that when we do a tan of an arctan of x, this actually cancels out equals to x. This whole thing becomes x. This is just x. And this right here is going to become y, and we'll go over that in a bit. This becomes x. This is y, and I'll just do a brief breakdown. So recall. Yeah, so recall again. It's when you look at the inverse trig definitions, with the regular definitions of trig, they all just match up. All right. So here, if you just draw a triangle, so let's say you had opposite at x, and then adjacent is 1, and you had an angle theta like this. So we have tan theta is equal to OP, opposite over adjacent, equals to x over 1 equals to x, right here. So it's equal to x. And we know that, well, when you take the inverse, theta is equal to arctan of x. So the arctan of the opposite over there, yeah, equals to, yeah, so this is arctan of x. Yeah, so then what that means is, well, we could just plug in this theta inside. And again, this is by definition, this is the opposite of this one, so it's the arctan of the opposite over adjacent. So then what it becomes is tan of arctan of x. So plug that theta inside, this equals to x, that's just over here. So in other words, tan of the arctan becomes whatever is inside there. So we could just replace that over here with y, this one with x, this with y, etc. So, yeah, so what we have is, well, let's just throw this over here and write thus. And if you've listened to my earlier videos in this video, you'll see my favorite word is thus. So thus, we'll have here tan. Yeah, so thus tan of, I'll put this, yeah, better. Tan of a minus b equals 2, and we have x minus y, 1 plus xy. X minus y, 1 divided by 1 plus xy. And now when we take the arctan of this, take the inverse, So then this means a minus b is equal to arctan of x minus y divided by 1 plus x y. And we know that a and b, well, a is equal to, just put it all together, arctan of x, that's a, and then minus arctan of y, that's b. This equals to arctan of x minus y over 1 plus x y. And just bold this out or circle it, and that is our identity. And yeah, so look at this one. If you scroll back up to the question, and we'll see that, yeah, that's exactly it. So arctan x minus arctan y is equal to x minus y divided by 1 plus xy. And note that this identity is for xy is not equal to 1, and also the left side lies between negative pi over 2 and pi over 2. And we can show that. We'll go over here further. That's because, again, we're dealing with this tan a minus b. And I'm just going to put this for xy is not equal to 1. Yes, and continue further. So note that the left side is between negative pi over 2 and pi over 2, again, because we're dealing with this tan a minus b. So if we have, let's say, I'll just say recall. Well, first we have tan of, I'll just do theta. Like this, I'll just draw it like this, actually. So let's say we have our angle, theta, where theta is equal to a minus b. Because remember, yeah, a minus b is just a tan. It could be viewed as the angle inside this tan. And remember that this goes up like this. This is the asymptote line here, and this is our tan theta. Tan theta. And then going this way, this goes back downwards like that. And this is our asymptote line. This is at pi over 2. This is at negative pi over 2. So that's where the tan function is applicable for here, negative pi over 2. And here I just moved it over to this side. So that's this asymptote line at negative pi over 2. And then this is a periodic, so it keeps repeating. But since we're doing the inverse or the arctan, I'm going to get a drawing right here. And it's drawn in red. So let's draw in red. So recall that the inverse of this would be, well, we just switch everywhere. So instead of this going to infinity at pi over 2, you instead are going to pi over 2 at infinity. So this goes here. And then so we just inverse everything. Draw it like this. This asymptote line now is pi over 2 for the inverse. This is arctan theta. And then similarly, this goes like this. Oops, it's actually under. And it keeps going on and on all the way until infinity there. Let's try this a bit better. Okay, so it goes like that, and then there's asymptote line, never reaches it, just keeps going and on and on and on. This is going to be our, I'll just keep going, this is our negative pi over 2. Yeah, so what we have is arctan theta never reaches beyond pi over 2 and negative pi over 2, and that's by taking the inverse of just the first periodic cycle of this tan theta. And you can't keep going more, otherwise you're going to have a non-one-to-one function. Basically, you'll have this stacked up on top vertically, then for every theta, you'll have multiple arctan, or every arctan theta value here, because then you'll have, when you're inversing, this will be the opposite over adjacent, etc. This will be the theta sign. But anyways, so this is, for the arctan. We just do the first cycle, and we have one function like that. Yeah, so thus, what we have is theta is less than pi over 2, and, so theta is between negative pi over 2 and pi over 2, like that. Where theta is just our, so let's go pi over 2, a minus b. So the left side is going to be between pi over 2 and pi over 2, like that. And that is the, quote, left side. Let's put quotations like that. That's just left side right here. Alright, and now the last thing to check is just that, note that if xy is equal to 1, so here we have it not equal to 1, because if it is equal to 1, then what we'll have is, well, rearrange it, y equals to 1 over x. And then what we have is our a minus b is equal to arc arctan of x minus arctan of 1 over x, like that. And we could even plug in the full formula, but it doesn't matter there. It's going to be the same thing. So the issue with here is at x equals to 0, we're going to have a arctan of 0 minus an arctan of 1 over 0, which is going to infinity. 1 over 0. In other words, we're having an arc. It's approaching arctan of 0. And also, arctan of 0, that is just, arctan of 0 is just 0. That's just 0 there. So it's approaching, well, 0 minus arctan of 1 over, that's going to infinity. Let's go arctan infinity. And this is approaching 0, we'll just remove the 0, minus, and then when you go to infinity here, you're going towards pi over 2. I'll just go negative pi over 2. Like that. Yeah, so you're going negative pi over 2, but this is, so it's approaching that. But the thing is, or it equals to that when you go into infinity, but we can't equal to this, so it's between that. Yeah, and it's also infinite, that you can't have an infinite there, so we're not actually there. And I'll just say, but you never actually reach it, and then you'll just say negative pi over 2 is greater than a minus b. So you can't have it equal to that. You're going to have an infinity, and you're also approaching this pi over 2, which you can't actually, which the left side is never actually going to ever reach. So anyways, so we can't have undefined stuff in the equation there. So we can't have this undefined even if you solve this, and this will also be the same thing. So anyway, so it's not equal to 1 there. And I'll just write this for completeness. This is undefined. The solutions manual just assumed all this. They didn't even talk about this equals to 1 there, or not. What happens when it's equal to 1. Alright, so now let's jump right ahead to solution to the question B. So let's recall question B, or part B right here. Says, show that arctan 120 divided by 119 or 119 minus arctan 1 divided by 239 is equal to pi over 4. So let's just throw in those numbers there. So we have, from A we have arctan, so our formula we proved, arctan of x minus arctan of y is equal to arctan of x minus y over, or else remove the bracket, x minus y over 1 plus x y. And now we're going to replace x with, let's see, arctan of, and scroll back quickly again, it's going to be 120 over 119, 120 over 119, and then 1 over 239 equals pi over 4. So let's go back here, 120 over 119 minus arctan of 1 over 239. This equals 2, so we have that. Now we can just add those terms. So arctan of 120, this is 120 over 119 minus 1 over 239, and then divided by 1 plus 120, 119 times it by 1 over 239. Alright. Alright, so now we're just going to do a bunch of algebra and solve this. We need to show that this is equal to pi over 4. And what I'll do is throw this inside. And let's do this. So 120 over 119 minus 1 over 239. Like that. Divide this by 1 plus 120 over 119 times by 1 over 239. And multiply this by the common denominator that we want is 119 over there, and we're going to divide by that as well. So and that's at the bottom, so we'll just multiply it and get it all canceled out. So 119 times it by 239, divide this by 119 times 239. And now we're going to get a bunch of cancellations. And this is going to be, well, when you multiply this inside to this left side here, the 119 cancels. So we're going to get a 120 times it by 239. And this one, the 239 cancels, and then we're left with this 119 minus 119. Then the bottom, this whole thing at the bottom cancels, so we're left with a 119 multiplied by the 1 here times 239, and then plus just a 120. And now instead of just putting this in a calculator, let's just do some algebra. So this equals 2, and I'm going to factor out this 120 into a 119 plus 1 times by 239 minus 119 all over 119 times 239 plus 120. Just so we have the same common denominator, multiply this inside. This equals to 119 multiplied by 239, and then plus this extra right there, 1 times 239, so 239 minus 119, like that. And this is a 119 times 239. Notice they match up, plus a 120. And now if we subtract these, this is 239. Alright, yeah, so just subtract the 239, just do long subtraction, 119. So subtract that, this cancels, we get a 0. So it goes a 0, and then actually I just remove those lines, you don't need to cancel, just put a 0 there. 3 minus 1 is 2, then 2 minus 1 is 120. So remember that equals to 120. Yeah, so put this all together, we got a 119 times 239, and then plus 120 over 119 times 239, and then this is plus 120. So they all just cancel, and we're left with equals to 1, which is quite fascinating. And now here's do a quick calculation check. So MES calculation check of 120 times 239 minus 119. This equals 2, and then built in OneNote, just press space, auto calculates, and so on. Same with this. This will get a 28,561, then 28,561 over there. And that is just this part right here. And then this part is the bottom one. And then you'll see it's the exact same thing. So those obviously cancel. And you could also just do it from the very start without actually any of these manipulations. So 120 divided by 119 minus 1 divided by 239. And then divide that all out by 1 plus 120 times 119 times by 1 divided by 239, which is this. And you could see, there's press space, it equals to 1, which is quite fascinating. So now that we have this equals to 1, and we could throw that inside there. And when we throw that in there, so this whole thing becomes 1, and then we can recall our exact trig ratios. And so first, let's write thus. Thus arc tan of 120 over 119, that's our x, minus arc tan over 1 over 239. This equals to arc tan of 1. And remember what this means. When you have arc tan, you're dealing with the angle. Whereas this inside number, that's the ratio opposite over adjacent. So if we draw a triangle, this is going to be, so a triangle with, like this, if it has opposite 1 and adjacent 1, that means this is just a square. So that's just a square with opposite 1. Yeah, so this is just a square, so that means this is divide this by 2. So the full angle is pi over 2. So this is pi over 4. So in other words, 45 degrees angle there. And likewise, this is pi over 4. So this is right angle, like that, pi over 4. And that means, yeah, that's pi over 4, so that's the angle. So that means tan of pi over 4 is equal to 1 over 1 equals to 1. So again, opposite or adjacent. And this means now we take the inverse. So arc tan of 1 is equal to pi over 4. So we just solved it. Like that. So this whole thing is equal to pi over 4. Like that. So yes, quite fascinating. And now let's move on to question C. So scroll up there. So question C says, deduce the following formula of John Machen, 1680 to 1751. And this is 4 arctan 1 over 5 minus arctan 1 divided by 239 equals pi over 4. So essentially, basically, we're going to try to switch this up with this, because everything else is the exact same. This is 1 over 239. This is 1 over 239. This is 120 over 119. So we got to write that as 4 arctan 1 over 5 if we can. And they do this just so that there's only 1 on the top. And this is 239. There's nothing on top, just 1. This one's a 120. It looks a bit off. So this is simplified. So let's continue further. So we are asked to show, that 4 arctan 1 over 5, write this better, 1 over 5 minus arctan 1 over 239 is equal to pi over 4. Alright, so now to try to demonstrate this, first notice that this has a 4 there, so that means we're adding up arctan setups. So what we'll do is so the solution manual does this, so it replaces y by negative y in the formula of part A. And recall the formula of part A, that is just this part right here. Arctan of x minus arctan of y equals to arctan x minus y, and then divided by 1 plus xy. So it replaces that so that we'll have an addition here. So the idea is to have an addition, so we'll have a 2 arctan, etc., plus this, and so on. So let's continue on, and we'll start to make sense. So arctan of x is equal, or minus, arctan of negative y, and this equals to arctan of, and then this is from the formula of x minus negative y, like that, and then divided by 1 plus x times y, but it's negative y now, like that. All right, so we have this. Now this setup right here, this is equal to, this part right here is equal to a negative, this is equal to negative arctan of y, and we'll show that. And we'll show that, and the reason, so then we're going to have an addition there. So we're going to show that because, well, recall that if we have a triangle like this, let's say we have a triangle, again, a right angle triangle, and when we're dealing with tan, we're doing opposite over adjacent. Let's say we have y here, and let's say this side length is 1. So this is the angle theta. So tan of theta equals opposite over adjacent, so y over 1, like that. So thus the arc length is going to be, or theta is going to equal to arctan of y. But now if we have the negative y, that means the opposite side is going to be negative, so like this. So this would be all the way down. So if this is still positive, you have a negative y like that. And this is going to be negative theta. So that's angles theta. This is going to be negative theta if that's the starting point over there. So that's what we have there. So that means tan of negative theta. So negative theta is equal to negative y over 1. So this means that, so we're going to get a negative theta is equal to arctan of negative y. So that's equals to this, and where this theta is just this, so we could plug that in. So then basically what we'll have is arctan of negative theta is equal to negative arctan theta. So negative theta, which is just equal to a negative arctan y there. So negative arctan y. So throw that whole thing in there. So we can box this out. So basically, this whole thing is arctan of negative y is equal to negative arctan y. So put that inside, throw this in, thus, all right, so thus we have is arctan of x. So I'll write this out, thus arctan of x plus arctan of y, of negative y, I mean, yeah, not negative y. Negative y becomes this whole negative arctan y. So arctan y, and then equals 2, and then do some simplification. This negative times negative becomes positive, so we'll have a x plus y over 1 minus xy. So we basically switch the signs there. So this is a plus x times negative y, so it's minus, and this one's negative times negative, it's plus. So that is what we have there, which is quite fascinating. Alright, so now, yeah, we have this, and again, we did this so that we can, and yeah, also, yeah, I forgot to put the arctan of x here. So yes, lots of writing. Arctan of that, so arctan, then over there. So yes, so we did this so that we can use addition in the formula we are asked to show, and let's go over that again. Yes, so we are asked to show right here. So 4 arctan 1 over 5 minus r over here, but we're only worried about this one. So we could use that addition identity, separate this up, and the goal is to make it match up with this arctan 120 over 119. Yes, so let's just write that out. So again, where's this? 4 arctan 5, 1 over 5. All right, so let's write that down. So we could, so again, we did this so that we can use addition in the formula we are asked to show. So let's do the first part. 4 arctan 1 over 5 is equal to 2 arctan. So again, we've removed one of, yeah, so we simplify this 4 to a 2. So though eventually we're going to do this again, so it's a 1. 1 over 5 plus 2 arctan 1 over 5. Now this equals to, right over here, arctan, but this is going to be a 2 there, so 2 times arctan of x plus y is, again, y and x are the same, 1 plus 5, plus, well, yeah, then plus 1 plus 5 like that. Divided by 1 minus 1 over 5 times by 1 over 5. And what we'll do now is, well, inside this arctan, I'm going to multiply the top and bottom by 5 over 5 squared over 5 squared, like that. So we get rid of all these 5 squared. So mainly this one, get rid of that. So this equals to 2 times arctan, like this. And then 1 over 5 times 5 squared, that just gets 5 plus 5, like this. And then the bottom becomes, well, this is 25, like that. So 25 is just 5 squared, 5 times 5. And then minus, this all just cancels, becomes a minus 1. So then this equals to 2 arctan of 10 over 25 minus 1 is 24, like that. And let's simplify this further. We could cancel this as it becomes divided by 2 is 5, divided by 2 is 12. So in other words, yeah, this equals 2 arctan 5 over 12. And let's box this, and then we're going to do the repeat again. So repeat, like this. I'm going to put this like this. Repeat, the same setup, using the same identity, so we can use the same addition one. And we're going to get a 2 arctan of 5 over 12 is equal to arctan of 5 over 12 plus arctan of 5 over 12 equals to arctan, and then we had x plus y, then divided by 1 minus x y. So we'll have a 5 over 12, or actually here I just moved it over to this bottom right here, so this becomes, so let's make this a bit bigger. So 5 over 112 plus 5 over 112 divided by 1 minus 5 over 12 times 5 over 12. Alright, so now multiply top and bottom again by this exact same setup as we did earlier, 5 over 12, and then we're going to square this. And this is 5 over 12 squared. And we'll do some cancellation. And yeah, actually I made a mistake here. Yeah, so notice this one here we multiplied by the above it. So this is 1 over 5 multiplied by 5 there. So here we got to multiply, flip these upside down. 12 over 5 and 12 over 5. So then we'll have cancellations. This equals to arctan tan of, and then this will cancel one time, and then we'll just be left with a 5 over 12, and then plus, I mean not a 5 over 12, well, because we're doing this, will cancel out, we're just left with this by itself, so 12 over 5, it's the exact same setup as before, 12 over 5, and then this is going to be subtracted by, this whole thing cancels, well, this whole thing, and this one is just a 1, so 12 squared over 5 squared minus, and now this all cancels, minus 1. And now we'll do this again. Now we have a 5 at the bottom, and there's a 5 squared there. Multiply the top and bottom by 5 squared over 5 squared. Alright, now we'll do some more cancellations, and this equals 2. Well, 12, the 5 cancels, we're left with 1 5 there. So arctan of 12 times 5 plus 12 times 5, like that, and then this, then divide this out, this becomes 12 squared, and then this, this 5 cancels, 5 squared cancels, and this minus 5 squared. And now simplify this one further, so this 12, this 12 times 5, you could factor out the 12s, so then this is, let's put this like this, 12 over 5 plus 5 equals 1210. Yeah, so we'll just write this complete down, so 12 times 10 over this one here, 12 squared is 144, so recall that, and then minus 5 squared is 25. So the only thing we need to do is, well, right here, this is 144, and this part here is 120 there. 144 minus 25. Yeah, so, alright, so like that. And then minus this would be a 14. Minus this is a 9, and then this cancels, be 3, because we had carry that, we added a 10, so we have to subtract 1, so this can be a 1, and then right here 1 minus 0 is just 1, and right here is going to be equal to, well, actually before that, again, we forgot to put the arctan there, so move this to this side, and this is arc 10. It's kind of like when you're doing limits, you also need to put the limit sign at all times. Alright, so we have that. This top part is just 120. Like that, or yeah, so that's just 120. So now what we're going to get is equal to arc 10 of 120 over 119. And yeah, this is quite amazing, do all that. Alright, so thus, from part B, we have, so put this all together, 4 arctan 1 over 5 minus arctan 1 over 239. This equals to, well, this part is just this. So this equals to arctan 120 over 119. Again, that's just from part B. 119 minus arctan of 1 over 239, and from part B this just equals to pi over 4, like that. So yes, fascinating. Alright, yeah, so that is part C. So now let's look at the solution to question D. So let's just scroll up to question D, and let's go back up here. And again, note here, so this is for question C, 4 arctan 1 over 5. We show that it equals to this, and then we already showed that this equals to pi over 4. So combine that all together. So now part D says, use the Maclaurin series for arctan to show that arctan 1 over 5 is between this setup. And let's just go over to the table and recall the arctan. See how far we have to go to get the table. Alright, here, so we teleported across here, and here's that Maclaurin series. This is arctan. It's the same thing as writing tan, inverse tan, or tan negative 1x. The same thing as writing arctan. So that is that. And this is the series. The Maclaurin series go to x minus x cubed over 3 plus x5 over 5. So it's odd powers and odd factor. I mean, there's no factorials. Odd powers and odd divisors or denominators. And they match, and there starts from x to the 1, and it goes from minus plus, and its r is equals to 1, the radius of convergence. Alright, let's go back all the way down. Alright, and now we're asked to show that it's in between these two range. So we're going to have to sum up that series. And this is arctan 1 over 5. Alright, so let's go over there. And we're going to be using part C, which had a 4 arctan 1 over 5 there. So that's at 1 over 5, and so on. And eventually use it to estimate pi. Alright, so recall from the earlier table above, or here, solution to D. So we are asked to use the Maclaurin series for arctan to show that arctan 1 over 5 is between this number 0.19739, etc. all the way, and then it's less than, it shows greater than this, but it's less than 0.1973955,616. This one has a 55597. So very, very accurate. We need to get it to. So recall from the earlier table above, inverse tan of x, or tan negative 1 of x, it's the same thing as arctan. It's just different ways of writing the exact same setup. Arctan of x equals to an arc. I think it's arc. They say this because it's like the arc of the angle. So it's the angle or the arc there. So arctan of x, this equals to number odd. Power starts from x to the 1 minus x3 over 5 plus, over 3. So they match up, plus x5 over 5 minus x7 over 7. And then it goes from plus minus dot dot dot. And r, radius of convergence, is equal to 1. Alright, so now let's plug in our 1 over 5. So we're asked to go 1 over 5 there. So x is 1 over 5. So thus, we'll have in our case arc tan of 1 over 5 is equal to 1 over 5. So 1 over 5 minus, and then there's the x's there. This becomes 1 over 5 cubed. Or before we get to that, I'm just going to write 1 over 3 times it by 5 cubed. And then plus 1 over 5 times 5 to the power 5. Because this is 1 over 5 to the power 5. The next one is going to be 1 over to the 7. So let's put a 7 there times it by 5 to the 7. And then it keeps going on and on. Plus, minus, dot, dot, dot. Alright, so now that we have this set up here, note that this is just an alternating series, so it's switching from minus, plus, and the size of the terms decreases to 0, so notice how it's getting bigger and bigger at the bottom. Eventually you're going to go 5 to the infinity at the bottom, and so you're dividing it, it's going to approach 0. So we can apply the alternating series estimation theorem as recap from my earlier video below, as well as on alternating series test and so on. So note, if the alternating series is for the alternating series test, summation from n equals 1 to infinity of negative 1 to the power of n minus 1 bn equals to b1 minus b2 plus b3, where bn is greater than 0, similar to ours. So this, or bn is greater than 0, and it's alternating, the terms are alternating from positive, negative, etc. Positive, negative, and satisfies that bn plus 1 is less than or equal to bn. So notice that each of the bn's are getting smaller and smaller. So this is going to be, you're dividing by a bigger and bigger number. So I is true for all n, and the limit as n approaches infinity of bn is approaching 0. So this is approaching 0 there. Then the series is convergent. So this is a convergent series. And then, before giving the proof and so on, yeah, I'm just not going to go over that paragraph, but basically, if we recall this line graph, and yeah, here I just removed that initial paragraph just so it gets in the way. So I'm just going to look at this graph right here to show you how it converges, just to illustrate this. So, for example, at 0 right here, let's say the S1 here is going to be just the B1. And then you're going to subtract that by B1, which is getting smaller, by B2. So this is B1. And then you're going to subtract it by B2, which is getting smaller. So it's going to get somewhere at S2 here. Then you're going to add by B3, which is smaller than B2. So it's going to go somewhere across here, so S3. Then you're going to subtract again by B4, and that's smaller. And then again, it keeps getting smaller and smaller. Eventually, you're going to get to converge to a point here. So let's illustrate the alternating series and how it's convergent for when B is getting smaller and smaller and it's going to 0. And then alternating series estimation theorem, if S is equal to, so negative 1 power of n minus 1 bn, so this is just showing that it's alternating, is the sum of an alternating series, then that satisfies bn plus 1 is less than bn greater than 0, so each one's getting smaller and smaller. And limit as goes to as n approaches infinity of bn is equal to 0. Then the remainder, r sub n is equal to s minus sn, so the actual sum minus the nth partial sum is going to be less than or equal to the next term bn plus 1. Yeah, so in other words, if we look at, let's say we had s5 there, and then we had the actual sum is here. This means that this is the remainder r5, and it's going to be less than, yeah, this one here, r5 is less than, well, the next one. The next one is this b6 there, less than b6, or the absolute value, or just, this is positive. Yeah, so it's less than that because notice how this one is much bigger than that, because this one goes all the way across this negative, this s1 there. And this happens each time. So even for s3, the difference right here, r from to s3, is less than this b4, which crosses that s. So yes, fascinating stuff. And that is what this note says. You can see this geometrically why the alternating series theorem is true by looking at the figure, this one right here. Notice that s minus s4 is less than b5, and the absolute value of s minus s5 is less than b6, right there. And they use absolute value because in this case s is less than s5, and then, but if you have it on the even side, s is greater than s4, s6, etc. So those will be positive. On the right side will be negative. So anyways, alright, so that was a recap on alternating series, the series test, and so on, and the estimation theorem. So the remainder is less than that. But also you could see that each s, so the s is always between, for example, s5, s6, it's always between s4, s3, and so on. And we just got to show that it's between this setup right here. And so what we could do is, so thus by the alternating series estimation theorem, the sum will be between each successive partial sum, and the error is the absolute value of the next term. So we're asked to show that arctan is between this. So first, if we put s1, this just equals to 1 over 5. So that's the first one. So it's s1 is 1 over 5. The next one's going to be 1 over, so the next s2 is going to be 1 over 5 minus 1 over 3 divided by 5 cubed. So that's this one. If you just put in the calculator, my OneNote calculator equals that. And then this one, 1 over 5 minus 1 over 3 times 5 cubed. This equals to this. Now s3 becomes this. But then, and this just, it's all rounded up. If you go s4, so 1 over 5 minus, so this is s3, and then minus 1 over 7 times 5 to the power of 7, etc. So we need to use a more powerful calculator. So here's going all the way here to using s5. S5 using Wolfram Alpha. Yeah, so Wolfram Alpha, very powerful calculator website. So here, put that inside here, and we'll get this giant setup here. So 1 over 5, this is s5. So this is 1 over 5 minus 1 over 3 times 5 cubed, and so on all the way. This one is to the 9th one, or to the plus 1 over 9 times 5 ninths, and then it goes all the way here, and it even shows you the period where it repeats. So it starts repeating at the 6-5. So notice the 6-5 there, 6-5, and then each time it's 6-5, it repeats with 6 numbers, 6, 5, 0, 7, 9, 3. So that's very, very fascinating. So that is that, S5. And also note that the S5 says 1, 2, 3, 4, 5. This is a plus. So then the S6 will be less than, because we're going to subtract by it. So we're going to have the S6 is less than the sum, and S5 is greater than the sum. So anyways, keep going on. So then S6 using Wolfram Alpha, we get this. This is 19739555616. And this is 1973955, etc. 197. This is, so minus 1 over 11 times 5 to the power of 11. And we get all the way up to here. And so thus the sum lies between S5 and S6. So S6 is less than, because you have the subtraction term. So we have S6 is less than arctan 1 over 5, less than S5. So that means, that means arctan is less, arctan 1 over 5 is less than, is greater than, all the way here, 197395597, and it's, it's greater than, and it's less than this, and then here I have a dot, 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 just to stop just to match up with the question we were asked, and this is the, up to here, Just before that 8. So you have this exact, there's 5 3 5s. And the other one up top here is 5 5 6 1 6. So here 5 5 6 1, etc. And this is the same as that we were asked to show. And yeah, actually going back up here, this was 5 9 7. This one is also a 6 there. Just put a 6 there. We could see that right over here, 6 1 6, and so on. So this is the same as that we were asked to show. So we were asked to show this. I just copied and pasted it. I'm not going to go and check again. But yeah, so this is it. And it's the exact same. So note that the solution manual rounds up to, over here, they just round up 6 0. So 5 9 7. This becomes 6 0 right here. And it also rounds up 6 1 6, rounds it up to 6 2. So anyway, so that is what we've shown, just using that Wolfram Alpha. So now let's take a look at solution to part E and scroll up to part E and see what it's asking us. So part E says, show that, and then basically same thing as this top one. Instead of arctan 1 over 5, we use arctan 1 over 2 to the, arctan 1 divided by 239, or 239, and show it's between these two setups. So let's go look at part E. All right, part E is right here. All right, so now solution to part E. So we are now asked to show that arctan 1 over 239 is between 0.00418, etc. And then it's less than 0.00418, etc. The only difference is 4075. This is 4077. So basically 75 and 7 7. We got to show it's in between. So using the series in part D, we get, let's just write it out for completeness sake, and then we'll start using Wolfram Alpha again. Arctan 1 over 239 is equal to 1 over 239 instead of 1 over 5. Then minus, this is going to be 1 over 3. Let's go 1 over 3 times 239 cubed plus 1 over 5 times 239 to the 5 minus 1 over, well, yeah, it keeps going on and on, etc. So minus plus, so that is a 1 minus, and then this is minus plus dot dot dot. All right, so now that we have this, and now since we are asked to determine the sum to 9 decimal places, so those right over here, so this is 4, and that's 5, and then that's 9 decimal places. This is 9. That's 5 plus 4 is 9. We can calculate the corresponding remainder. So let's look at R2. So if we have R2 equals to S minus S2, so that's just right here. This is S2. So the actual sum minus S2 is equal to, and actually instead of regular brackets, this is absolute value, because it could be negative. Yeah, so absolute value, and remove this. Yeah, so absolute value of S minus S2 is equal to B3, so the next term afterwards. So yeah, B3, so S minus S2 is less than or equal to Bn plus 1. That's the remainder. And again, this is this is less than or equal to sign, not, so add the symbol less than or equal to. So less than or equal to B3, which equals to 1 divided by, this would be the B3, 1 divided by 5 times 239 power 5. And then if you use my OneNote calculator, it's too small, so it just goes 0. So need to use a more powerful calculator. If you use Wolfram Alpha, and it gets to a 10 to the 13, negative 13. So that means this S2 is accurate to within 10 to the negative 13. So in other words, 13 decimal places, as opposed to what here we're just asked for 9. So that's going to be, so we could just use S2 as the number. Yeah, so the third term is less than 2.6. And here's rounded up 5, rounded up to 2.6, 2.56, round up to 2.6, times 10 to the negative 13. Thus, by the alternating series estimation theorem, we can just use S2. So if you use S2, that's just 1 over 239 minus 1 divided by 3 times 239 to the power of 3, and it equals this, again, using Wolfram Alpha, and you get this 0.004184076, like there. So thus, S2 corresponds to the inequality we are asked to show. So S equals arctan 1 over 239 is approximately equal to S2, which equals to this up to this 7, 6. So 9 decimal places. This one, notice there's a 5 there we're asked to show, and 7. And this one is a 6. So it's in between these two. So arctan is in between these over here, because remember, the remainders is very, very small. It's 13 decimal places as opposed to 9 right here. All right, so that is, yeah, so note we couldn't just use the inequality S minus, S between S1 and S2, because S1 is too large for the inequality we were asked to show. See if I could put this, that equals, yeah, this rounds it up. But if you use Wolfram alpha, it will show that it's equals to this. So yeah, S1 is 1 divided by 239. Put that in Wolfram alpha, you get this over here, 0.004184104. But then this is greater than the one we're asked to show. It's which is over here, 0.004184077. Yeah, because notice the 1 here. So that's this one right here, 4007. This is 41. So this is greater than that. And actually, here, because it's S2 is smaller than S1, this is, we'll have a reverse side. Let's go this right here. 2, 1, and then this one, 1. Whoops. 1, 2. Yeah, so we can't just use S is less than S1, and yeah, we can't use it less than S1 greater than S2. Yeah, because again, this S1 is too large for this one here. We're asked to show this. So we could just use the S2 then. All right, so now let's take a look at question F and scroll all the way back up. So yeah, this is a pretty tedious question, or tedious overall problem. So deduce that, correct to 7 decimal places, pi is equal to 3.1415927. And then here's some historical notes. Machin used this method in 1706 to find pi correct to 100 decimal places. And recently, with the aid of computers, the value of pi has been computed to increasingly greater accuracy. In 2009, T. Daisuk and his team computed the value of pi to more than 2 trillion decimal places. So here we're going to show it correct 7 decimal places over here, 3.145927. So let's go over to here. And again, we could just use that the formula we derived. So we're asked to show that. So then pi is we're asked to show that pi is is approximately equal to 3.1415927, or basically accurate to 7 decimal places there. So from part C, we can deduce that, and we remember this one here. This is 4 arc tan 1 over 5 minus arc tan 1 over 239 is equal to pi over 4. So we had solved this earlier. Let's just go back up to show that. Just so we, just to show, because I was just using by memory. So we have over here 4 arc tan 1 over 5 minus arc tan 1 over 239 is equal to pi over 4. All right, so we have that, and we already calculated those. We already estimated those to very accurate figures. And yeah, going back here, so and since we're asked to solve for pi, we can just multiply everything by 4. So what we'll do is we'll multiply by 4, and we're going to get a pi is equal to 16. Yes, so 16, scroll up, equals to 16 times, 16 times arc tan 1 over 5 minus arc, minus 4 times 4 arc tan 1 over 239. Alright, here I just boxed this in, and now recall from part D, or parts D and E, the estimations we did. So arc tan 1 over 5 is between this right here and this. And arc tan 1 over 239 from part E is between this and this right here. Thus, we can apply each inequality into our formula for pi. So we want, so basically, we'll take the pi as between, we'll take all the smaller number, or the numbers that give the smaller amount. So 16 times, we take the smaller one of arc tan 1 over 5. That is this right here. So there's, notice the 97 there. Then minus 4, now we need to pick the bigger number because we're subtracting, so we put this one in. So this and this. This one goes into here, this one goes into here. So minus 4 times that, so it matches up with this arctan 1 over 239. And then is less than pi and less than 16 times, now we get all the bigger numbers. So this is the bigger one here, 616. No, 616 at the end. And then minus 4 times a smaller number, which is this one here, because we have a negative, so 7575. So we do that, and what we get is, while calculating this out, we get, let's do the left side, 16 times this, minus 4, and then you could just use my OneNote calculator, has it built in per space, it goes to here. And likewise for the right side, per space equals to this, 3.14, and this is 7.2, this is 5.6. So in other words, pi is between this, right here, and this is, the decimal places here is, this is 4, 5, this is 10 decimal places. We only are rounding it to 7 decimal places, so we go 1, 2, 3, 4, 5, 6, 7. We get over here. Yeah, so we get over to the 647, and then here's 3.14 all the way to, let's see, 4, 1, 2, 3, 6, 8 right there, and then it's rounding up. We get a 6, and then this becomes a 7. So rounding to 7 decimal places, we get 3.14526 pi equals to over here. Yeah, so we get pi is between this right here, 3.1415926, less than pi, it's greater than this, and it's less than 3.145927. And then the solutions bound, use the upper bound. So using upper bound, we get the estimation pi is approximately equal to 3.141597. And just another note here, calculation check. So let's go put it here. MES calculation check. Calculation check. So my OneNote has a built-in calculator. I could just type pi equals to, and it gets over it here. So that's an exact one. So 3.1459265. So there is the rounded part up. So those are the rounded up. So exactly this. 27. Yeah, so here we have 5927. This is 59265. So rounded up to 7. So that is correct. All right, so now let's go over problem 8. And this one states, well, part A. Prove a formula similar to the one in problem 7a, but involving arc cotangent instead of arctan, or arctangent. And then part B says find the sum of the series, summation from n equals 0 to infinity, of arc cotangent of n squared plus n plus 1. Alright, so let's take a look at question A and look at the solution to it. So solution to A, first recall from problem 7a that we started off with the tan x minus y trigonometric identity. So again, we're going to look at problem 7a, but switch it up to using arc cotangent instead of arctan. So if we scroll all the way up to our 7a, so in 7a, how far did we go? Yeah, it keeps going. So we were asked to show this arctan x minus arctan y equals to x minus y divided by 1 plus xy. So we want a similar formula, but instead of arctan, we use arc cotangent. And if you look at the solution, remember when we used this identity, so first we wrote this as a minus b as theta, and then we used the identity right here, tan x minus y. So we'll start from this, and we're going to switch it up to cotangent, and then from there get arc cotangent, similar to the solution to A. Alright, so teleporting over to here, so solution to A. So recall from problem 7a that we started off with the tan x minus y trigonometric identity. So again, this one right here. And let's use the same identity, but convert it to the form with arc cotangent. So first off, let A equals to arc cotangent of x, and we'll let B equals to arc cotangent of y, like that. And this is for let's say it's defined for 0 is less than a minus b less than pi. And notice here, this one is, this domain is from 0 to pi, as opposed to the earlier one for tan was a negative pi to pi. So if I scroll all the way back up to our graph here, so we had it from negative pi to pi. And this is arctangent. And just a note here, and I'm just going to draw this in red. Notice here, so when we do the inverse, we're basically switching x and y. So then this is theta there. This becomes theta on the arctan setup over there. Or I just put that there just so that to show that this switches over to this side here, and so on. And then you're going to be defining theta according to that setup there. So anyways, I'm just going to erase that. All right. So then remember, this one is between negative pi over 2 to pi over 2. That's because of the tan was set up over like this. The arctan is so tangent is defined from here, but it's periodic, and then this arctangent will just go from negative pi over 2 to pi over 2, and it only just once, so you'll have it as a one-to-one function. So that instead of doing this multiple times like that, you're gonna have you'll have a theta, and then you'll have a y1, y2, etc. So we can't do that, so we need to make it all one-to-one. And so we'll just pick that just this domain becomes the range right there. Alright, so going over here, now in our case, we're going to be dealing with cotangent instead of tangent, and then we'll show the corresponding domain of that. So, alright, so now we're just going to do a refresher on inverse functions. It pretty much becomes that. So recall, first of all, that cotangent theta is equal to 1 divided by tan theta. So that means then first we gotta show the graph for tan theta, then cotan theta, then we'll look at arc cotangent. So if we have a theta like that, and this right here goes up, so this is, well, first this goes up like this. Just you can have this ingrained into my brain, the curve for the tan. This is at pi over 2, and this is at negative pi over 2, and this right here is our tan theta, like that. And then the next setup is at pi, and so you have this pi over 2, add another pi over 2, and that becomes, add another pi over 2 becomes over here. Let's put a pi. This is at a 0, and actually no, I got that mixed up. So add another pi over 2 becomes over here. Let's just do one more time here, and then add another one. It becomes 3 pi over 2 right here, and 3 pi over 2. And notice it's going to basically reflect again. It's basically it's periodic, so it repeats again and goes like that, and so on. And then if we go one more here, this is at negative pi over 2, like that. Actually, no, we already have negative pi over 2. We don't need to keep going further. Yeah, that's just right here. So now, if I draw in red, let's go here in red. Okay, so I'm going to draw in red now for cotangents. Remember, cotangent is 1 divided by tan. So then over here, as it goes to infinity, we are going to, basically as it goes to infinity, it's actually going to 0. And as it goes to 0, you'll have 1 divided by infinity, so that goes over like that. And likewise, over here at this pi, I'm going to draw this down here. And then this is going to go downwards like that. And likewise, over at this point right here, at this point, it's going to be on the positive. This is on the negative side, it's on the positive over like this. And this goes to the 0 there. Yeah, and that goes 0 as tan goes to infinity. And again, I'll just put this as, this is at cotangent theta. And then the next setup is over here 0, but it's at the negative, so that means it's going downwards. And then this is at infinity goes to, well, 1 over infinity goes to 0. Like that. Let's make this a bit better. And like this. Alright, so that is where it is. And then to get a one-to-one function of the arc, or the inverse cotangent, we're going to have to look at, well, typically what's picked is this section right here from 0 to pi. It's from 0 theta less than pi, and we're going to take this section and then do the inverse of it. So put it down here. We're going to get a function that looks like this. So let's just write this out here. This is our theta, and now we're going to draw that same curve. So this is at 0, and this is at pi. I'll say pi is here, and then dot dot dot, and it goes like this. This is at pi over 2, and it goes to infinity, and it goes down. And this right here is our cotangent theta, like that. And now we're going to draw the arc cotangent. So basically we switch everything. We switch this. If this is theta, the new theta will go over there, and so on. And I'm just going to erase that just because you switch them, but then you redefine the variables. All right, so let's just extend this further, and this is at our pi. So we go from the asymptote as the vertical becomes horizontal when you take an inverse, and then this pi over 2 becomes over here is the 0. This becomes pi over 2, and yeah, this is our pi over 2. And notice what happens here. We just switch the x and y's. So at theta is approaching pi, cotangent goes to infinity. That means the reverse would be as arc cotangent, or the inverse cotangent, goes to infinity. I mean, as the theta, the x coordinate goes to infinity, or the theta coordinate, then it approaches pi. And it's not just infinity; it's negative infinity. So you have a negative infinity there. So you go to negative infinity, so if we basically rewrite this again. So if we're approaching pi, we go to negative infinity. So then we'll have to go the reverse. We have to approach negative infinity, approaches pi. So that means we go negative infinity, approaches pi right here. So that's this part right here. So that, and then it goes over to here. So that means it's going to go like this to negative infinity. And then likewise over on this side, we're approaching 0. So as x goes to theta goes to 0, we're approaching positive infinity. And then the other way around is x goes to infinity, or a horizontal coordinate goes to infinity, then this approaches 0. So then this goes like this. Yeah, so this approaches this setup there, like that. Alright, yeah, just move things around, and now this one is the inverse or arc cotangent theta. And notice how the domain of the cotangent is from 0 to pi, or that's the range we're looking at. Because notice it keeps repeating, we're only looking at this one. So then that means this vertical range is going to be from 0 to, this is theta, is pi. So that is what it's defined for, so that it's a one-to-one function. So for each theta, you only have one arc cotangent theta here, and not multiple ones on the top or the bottom, etc. Otherwise, you'll have a non-one-to-one function. Anyways, let's remove all that. And all right, now that we have that, basically recap on inverse functions and where the range / domain is. So we have this set up here. So that's where it's defined for, where the a minus b is like that. And that's because we're going to be taking the arc tangent of it soon. And also, so let's take a look right here. So tan x minus y, we're going to use that identity. Yes, tan x minus y is equal to tan x minus tan y plus, and then divided by 1 plus tan x times tan y. But instead, we're going to look at the cotangent version. So I'm going to write thus. Thus, what we'll have is cotangent a minus b is equal to, by definition, 1 over tan a minus b. And this equals to, basically, we'll take that tan a minus tan b. So this one, but then we'll flip it upside down. So we'll just go over it because we're doing the reciprocal of that. So this equals to 1 plus tan a times tan b. This was originally the bottom. Tan b divided by tan tan B minus tan A. Actually, no, we got that mixed up. It's tan A minus tan B. So you can see that here, tan X minus tan B, and so on. All right, yeah, so let's continue further. So we have this setup right here. And now what I'll do is, well, rewrite this all also in cotangent version. So so this equals to 1 plus 1 over cotangent A. So cot A times by 1 over cotangent B. I'll divide this by tan A becomes 1 over cotangent A minus 1 over cotangent B, like that. And now what I'll do is multiply the top and bottom by cotangent A. Yeah, cotangent A times cotangent B, just so we can have this denominator the same and then do a whole bunch of cancellations. Cotangent, and divide it also by cotangent A times cotangent B. So we're not changing anything because this is just multiplied by 1. So now what we'll do is do a bunch of cancellations. So this equals to cotangent A times cotangent B. So that's a 1 over here. And this part cancels out. We're going to be left with 1. And then divide this by, right here, 1 over cotangent A cancels. So we're going to be left with 1 over, not 1 over, just we're going to be left with cotangent B. And then minus cotangent A, like that. And now what we'll do is I'm going to move the 1 in front, equals 1, plus, and then we're going to place our A and B. Remember, our A is equal to arc cotangent X, and our B is equal to arc cotangent Y. So what we get is 1 plus cotangent arc cot X times by by cotangent of arc cot, this is going to be Y. I'll divide this by arc cot of, it's cotangent of arc. Cotangent arc cot of X minus cotangent, oops, I'll remove this one, cot arc cotangent Y. This one's Y. This one's Y. This one's X, because that's B, and that other one is A. And now, recall what we did with the tangents, the same thing for cotangent or any other trigonometric and inverse trigonometric function. So this becomes right here, this whole thing is just X. This whole thing is just Y. And cotangent of this, again, is just Y. This is just X. Yeah, so what we get is thus, and I'll just put this, this is a cotangent A minus B equals to, so cot A minus B is equal to 1 plus xy over y minus x, like that. And yeah, that is pretty amazing. So that is that. And now we're going to take the arc cotangent. So since we defined it as theta is between a minus b, or thetas are a minus b, is between 0 and pi, then we could take the arc cotangent of both sides. So since it's that, we have arc, so just take the arc cotangent of both sides, or obviously just switch this over. This equals to the arc cotangent of this. But just for completeness, and also do this another way. So arc, and notice that arc, the word arc derives from just the arc. So that's the arc, or theta, so that, hence the arc cotangent. And usually, and that's why it's called arc, as you're going to be equaling to this theta, which is this a minus b inside this cotangent. So arc cotangent of cotangent a minus b, like that. So we're going to arc cotangent of both sides. You can also do it that way. Arc cotangent of 1 plus xy, and then y minus x, like that. And now this, again, this just equals to a minus b, like that. And same thing if you have a coat or arc coat, and it's the same thing. So this cotangent of this or arc cotangent of a coat, mix those around, it'd be the same thing. You look at the inside angle there. And now this means is A minus B is equal to arc, or actually let's put the whole thing. So A is arc cotangent of X minus arc cotangent of Y, and then this equals to arc cotangent of 1 plus xy over 1 plus xy over y minus x, like that. And let's box this whole thing. So there is our similar formula to the tangent one or the arctangent, but now we're dealing with we're dealing with arc cotangent. All right, and now that we have that, now let's continue further and look at the solution to question B. So let's look at question B right here. So question B says find the sum of this series, summation from n equals 0 to infinity of arc cotangent of n squared plus n plus 1, like this. And what we could do is notice this polynomial inside n squared plus n plus 1. That a bit better. N squared. Oh, let's try it one more time. N squared. All right. So we have that. And what we could do is let's look at the solution to part B. So we can reformulate the polynomial inside arc cotangent to match our identity from part A. So we could look at that and match it with this right here. And we could see that by, well, if we do some algebraic manipulation. So n squared, let's go n squared plus n plus 1 is equal to, let's factor out the n from these two terms. So this equals to n times by n plus 1. So n, just take that out. N times n plus 1 plus 1. So notice that this looks like this one, 1 plus xy. And I'm going to write this as, put the 1 in front, 1 plus n times n plus 1. Divide this by, now we need a y minus x. And notice again, if this is our x, if this is our y, then what we'll have is n plus 1 minus n, which is now, and these just cancel out. This is just, fix that up. This is just equals to, well, n cancels with this one right here. So n minus n plus 1 equals to 1. So we're not changing anything. So this is the same thing. Oh, this is just having n. I mean, this is just 1 and then plus n minus n. So then, those just cancel out. And then what we have here is y, and here is x. Like that. So in other words, this is equivalent to our 1 plus xy over y minus x, like that. So that's equivalent to that. So thus, we can just plug that inside. Yeah, so I'll put thus, and then write this as the arc cotangent of this. So we'll just write this out. So now we've made it pretty much match our identity. So thus arc cotangent of 1 plus, or actually put the whole thing in, of n squared plus n plus 1 is the same thing as writing arc cotangent of 1 plus n times n plus 1 over, and put this in a bracket like that, like this, and now this is going to equal to n plus 1 minus n. In other words, now we could apply our identity that we have from part A. So this is arc cotangent x minus arc cotangent y. And in this case, x is n, and y is n plus 1. So this equals to arc cotangent of n minus arc cotangent of n plus 1. And I'm just going to box this out. This is an important formula for this solution. All right, now notice what we have. This is, again, looks like our telescoping sum setup. Whenever you have a subtraction where you're subtracting the next term, that's usually means we're going to be canceling out Yeah, so continuing further, so this setup is the familiar case which gives us a telescoping series with nth partial sum being, well, let's just write it out. So Sn, because we're going to be summing this up to infinity, so that is the function arc cotangent of n squared plus n plus 1. Again, we're asked to find the series, this right here, so summation there. So let's take a look at the nth partial sum. So Sn is equal to, well, arc cotangent of, arc cotangent, let's put a 0 in here. So arc cotangent 0 minus arc n plus 1. So when n is 0, n plus 1 is 1. Arc cotangent of 1. And then the next term is going to be 1 plus arc cotangent of 1, like that, minus arc cotangent of this is going to be 2. And notice here, this cancels with this. So this cancels with this, and we can keep going on and on. Plus, let's do one more here. Arc cotangent of 2 minus n plus 1, or 2 plus 1. Arc cotangent of 3, and remember this cancels with this, and so on, plus dot dot dot. We keep going all the way until arc cotangent of n minus arc cotangent of n plus 1, like that. And put this in a bracket, a closed bracket, like that. And then everything cancels out. This will eventually cancel out. This arc n also cancels out. And all that we are going to be left with is this and this. In other words, let's put an arrow, So this equals to, everything cancels, arc cotangent of 0 minus arc cotangent of n plus 1, like that. Alright, so thus, let's put it all together, and we'll just box this out as well. So that's our Sn. Alright, let's do a better boxing. Alright, so that's our Sn. So now, thus, put it all together, the summation as n approaches infinity, as from n is 0 as it approaches infinity, of arc cotangent of n squared plus n plus 1 is equal to, well, the limit as n approaches infinity of our Sn, which is this setup right here, arc cotangent 0 minus arc, let's see, right here, so I'm going to write this a bit neater, arc cotangent 0 minus arc cotangent n plus 1, and then all bracket like that. And now that we have this, well, we know the limits here. We'll look at these limits actually here. So this part right here is approaching, this is approaching arc cotangent of infinity, like that. And if we see our earlier graph, this is approaching 0, because we can see, if you see our earlier graph above here, so right here, as it's approaching infinity, as theta is approaching infinity, this is approaching 0 right here, like that. So this is approaching infinity, and so we have that. I'm just gonna draw that out. So that's approaching infinity, and then when it's at 0, this is at pi over 2. So this is at, I'm going to draw this in red. Let's get this red here. This is pi over 2. So this is at the x1, at the horizontal becomes the vertical. So that's at pi over 2. And just get the black, and let's keep going. And I'll draw it over it again. So this approaches 0, and this approaches, well, this is equal to pi over 2. So in other words, this equals 2, well, pi over 2 minus 0, and equals to pi over 2. So fascinating stuff there. And let's just recall for completeness. Recall here the angle. This is theta, and this is right here. Remember, this is pi, This is 0, and then it goes like this, where this is pi over 2. So at 0 is pi over 2, and it goes to infinity. Let's try this a bit better. And then it goes like that, but it doesn't curve up, it just keeps going down like that. Alright, so something like that, and this is at pi over 2. Yeah, so that's pi over 2. This is our arc cotangent theta, and as it goes to infinity, it goes to 0 right there. This is going to infinity, and it's approaching 0. And here I just fixed up the graph, but yeah, so yeah, as it approaches infinity there, it goes to 0, and then at pi over 2, I mean at cotangent or theta 0, we have arc cotangent of 0 is equal to pi over 2. So yeah, that is equal to pi over 2. So yes, fascinating stuff. So now let's continue further. Let's look at problem 9. And this one states, find the interval of convergence of the following series and find its sum. So we have the summation from n equals 1 to infinity of n cubed times x to the power of n. Alright, so let's take a look at the solution. And so solution, well, we can start with the following geometric series and differentiate. Basically, look at this geometric series here, x to the power of n. So if we do that, what we end up having is, we can do term by term differentiation, and again, that's using this summation of it. So let's just write this better. So if the summation from n equals 1 of x to the n, this is a geometric series, we're at n equals 1, we'll just have x to the power of 1. Well, actually, but let's start off with n to the 0, like this. So at n equals 0, we get x to the power of 0, that's just 1, plus x, then the next one, n is 1, x to the 1, plus x squared, plus x cubed, plus dot, 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 and let's say we have absolute value, and then, yeah, for this case, we have absolute value of x is less than 1. Yeah, this is where it converges, remember, for a geometric series. So absolute value of x is less than 1. That is the R. So let's say we have, this is our A, and then this part here is our R equals to x. So that means this whole sum is equal to A over 1 minus R. So it's a convergent geometric series for the absolute sum. Absolute value of x is less than 1, where it converges like that. Like this, a equals 1 over r, and in this case equals to 1 over 1 minus x, like this. Alright, so that is what that geometric series is, but now we'll differentiate this whole series. So d over dx of the summation from n equals 0 to infinity of x to the n, this is equal to, well, we'll just take a derivative of the sum there. The sum is right there, equals to that. And this is of 1 over 1 minus x. This equals to, well, same thing as writing d over dx, just to make it easier to differentiate. 1 minus x to the power of negative 1. Alright, so we have this, and now if we solve this, we get, and we could also, this is the same thing as doing term by term differentiation, or doing the derivative of this inside a function there, as per my earlier video on this. So it's the same thing as writing a summation from, write a better summation, infinity n equals 0 of dx to the n over dx. So that's just going to be, well, take the n down, x, n minus 1, subtract the power. And now derivative of this one, do the same thing, bring the negative 1 down, bring the negative 1 down, and then we'll have 1 minus x, and then subtract a power, so minus 2, and then this, and then using chain rule, multiply by negative 1, like that. And then the negatives cancel, so we're left with a 1 over, and bring it down, 1 over x squared, like that. Alright, so we have this, and what we're going to do is, well, solution manual does, it wants to get rid of this n minus 1, just make it to the n, so by adding another x power, so what we could do is multiply it by x, so we could write x to the power, x times, and then this is, let's put it x like that, x, actually like this, x times summation. Yeah, the summation as a whole is the hardest to draw. Infinity, n equals to 0. I'll put this better. N equals to 0. N, x to the n minus 1. This is 1. So then those just add up, and we're just going to be left with infinity, n equals 0, and then n, x, add up the powers times by n. Like that. And now this equals 2 and multiplied by x on top. So x over 1 minus x squared. Alright, so this is what we have now. Notice the difference. When we did that differentiation of that geometric series, we started off from this xn. And notice when you take the derivative, you bring that down. Then notice there's this is n cubed, and now we're going to have an n there, and we're going to do this again. And notice for differentiation, the power, the interval of, or the radius of convergence doesn't change. Again, this is 4. Absolute value of x is less than 1. So it's the same thing there. And we can go over this later in this question. Alright, and now before differentiating, notice that we had this derivative d over dx. And notice this right here. This 1 goes to 0. So then we're going to be left with... we're going to be left with a term that's gone. So we don't start at n equals 0 anymore. We start at n equals to 1 now. Because, we're not going to have a negative 1 there. So at n equals 1, we'll have x to the 0. As opposed to, if you put a 0, we'll have a 0 minus 1. That's a 1. That doesn't make sense. So this is a 1. Starts at 1. Like that. Yeah, so each time when you're canceling, you're going to have to add it up. So the next time we'll do it, because this derivative becomes 1, take derivative, then we'll start off at 2. And start off with 2, again, depends on other changes we do. So anyways, going here, so differentiating again, this time using the quotient rule we have. So we're going to differentiate this again, and then, but this has a x over 1 minus x squared. So it's easier to use the quotient rule. So recall from my earlier video. Yeah, so from my earlier video, the quotient rule, so if f and g are differentiable, that means you could take the derivative, then d over dx of fx divided by gx is equal to gx times d over x f of x minus fx times d over dx of g of x. And then this and then divided by gx squared. In other words, we'll go with g times by f prime minus f times by g prime all over g squared. So so we alternate the derivatives on the top, and then we square the denominator. Alright, so that's what we have. So let's start solving this. Alright, so let's go over here. So thus, let's put it thus just so it's away from that. So thus we have d over dx of summation from n equals to 0. Let's write this a bit better. Summation, just fix that up. So summation up to infinity from n equals 1 of n times x to the n, like that, equals to d over dx of this whole thing right there, x over 1 minus x squared, like this. And now we're using quotient rule, so this setup is equal to, and I'll just put let's put it equal like this, equals to summation. This becomes n, so x, bring it down, n squared times by x to the n minus 1, and we'll keep it like this. N equals 1 up to infinity. And we'll just keep that n equals 1 because there's no negative there. And this equals 2 d over dx right here. And remember how this looks like. So x is f, so we'll take the derivative of that. And so we'll put 1 minus x squared is g, times by derivative of x is 1, minus f, which is x, times by derivative of g of x, which is going to be a 2, bring it down, 1 minus x, and then 2 to the power of 2 minus 1. Yeah, the power of 2 minus 1 is just 1. And then, I'll just put a 1 like that. And then divided by 1 minus x squared becomes 1 minus x to the power 4. And then notice what we have here. We can do some cancellations. This can cancel with this. Yeah, so when we divide into it, that cancels. And then this, or actually instead of dividing it separately, we'll just cancel one of these. So we'll cancel this, becomes a 1. This becomes a 3, and then this whole thing cancels because it's 1 minus x, like that. So this equals 2. Well, multiply that inside, just 1, just it doesn't change anything, 1 minus x, minus 2 x, and also we forgot to do the, over here, the chain rule, negative x, so times it by -1 there. So that becomes a positive 2x, like that. Positive 2x, and this just changes the sign, like that, over 1 minus x cubed. And now we could just subtract this, so negative x plus 2x, that just becomes, well, x, and move that in front, so x plus 1 over 1 minus x cubed, and then similarly, we'll take this multiplied by x, so that we'll get rid of this -1 there. And notice that we have an n squared there now. Then we're going to have to differentiate again. So this is going to be x times it by, like this, summation from n equals 1 of n squared times by x. N minus 1 is equal to, and then this goes summation from n equals 1. This goes n squared. This is going to be x to the power of 1. And that cancels out. So xn. This equals 2. And this equals 2, yeah, so just multiply by x. And then we'll do that on this summation as well. So x squared, or the actual sum there, x squared plus x, 1 minus x cubed. Like that. And then we're going to differentiate again using the quotient rule. Alright, and then notice there's the n squared there. Alright, so continuing further, so differentiating one last time to get an n cubed. So when you take the derivative, the n goes down, and so on. So what we'll get is, let's go write this down. So d over dx of the summation up to infinity from n equals 0. N equals 1, not n equals 0. N equals 1. N squared x to the n is equal to d over dx, and then take the derivative of this one, x squared, plus x over 1 minus x cubed, all bracket like that. And then again using quotient rule again, and again first let's take derivative of the inside. This is equal to, I'll just put an arrow or just put an equal sign here, equals summation, let's put a better summation, let's make it a bit more, one more try. Alright, that's decent. N equals 1, and this is going to be n, yeah, so that is, this x, and bring that down. So first we have n there, n to n squared, but then bring the n down, so that'll be n cubed, and then times by x, and then subtract the power xn minus 1. Now this equals 2, and again using the quotient rule. So what we'll do is, again, quotient rule, g of x times d over dx of fx, and then minus fx times g prime over there. So what we'll do is write g of x, 1 minus x cubed, times it by the derivative of fx, which is 2x plus 1. So bring the 2 down, subtract the power. Same thing for here. So we get that. And then minus f, like this, x squared plus x, this fx, times by g prime. So derivative of g, again, always remember the chain rule. So this is going to be, bring the 3 down. It's going to be times by 3. I'll just put this in, remove this dot. Let's put a 3 like this. Times by 1 minus x to the squared, and then times it by minus 1. It's for the chain rule. Then there's a negative x there, so multiply by, so the derivative of negative x is what, -1, so that's a chain rule. And then this is all divided by 1 minus x cubed squared, which is x to the 6. Alright, so let's do some cancellations. Notice there's the like terms 1 minus x, and then there's a cube. This is 1 minus x squared. So we can cancel this entire thing out, including the square. Whoops, let's do this a bit better, like that, and cancel this, and just leave the 1 there. And then this cancels, becomes a 4. So we cancel 1 minus x. So in other words, 1 minus x squared, we cancel it all out. And then what we're left with is, is this. I'm just gonna, I'm going to just multiply this out inside. So this 1 multiplies by here, and then this one, and etc. So keep doing that out. So just expand it out. Also, undo. Okay. So now we have all that. Now this is going to be, so 1 times 2x, that's just going to be 2x. Then 1 times 1 is just 1, plus 1. And then we're going to have a negative x times 2x. That's going to be negative 2x squared. Negative x times 1, that's going to be negative x, like that. And then minus, well, there's a minus and there's a plus. There's a minus and minus, so it becomes plus, and then this 3 just goes in there. So 3x squared plus 3x. And then again, this is all divided by 1 minus x 4. So what this means is, well, let's just simplify this out. Let's look at the highest power, x squared. So we'll have 3x squared minus 2x. So we'll have this and this. That just becomes x squared. And now we'll look at the next one is x. So we'll have a 3x plus 2x is 4x. And then minus x is, the 3x plus 2 is 5, and then minus 1, that's 4. So this is plus 4x. And lastly, we're just left with this plus 1. Plus 1 there. And this is just going to be 1 minus x to the 4. And then likewise, we're going to multiply by x on both sides, get rid of this negative 1 there. So what we get is, so then put this all together, we get x times the summation up to infinity of, starting from n equals 1, of n cubed times by x, times by x to the n minus 1. So again, power 1, there's a power of n minus 1, add those up. This equals 2, and then just do that. And this becomes our formula. Or this becomes the sum that we wanted to find. So n equals to 1 of n cubed x to the n, like that. This equals 2, and then just put an x over there. So this becomes x cubed plus 4x squared plus x, all divided by 1 minus x to the 4. And bold all this, and that's what we get. And again, this is for the radius of convergence. Absolute value of x is less than 1, like that. Alright, so now continuing further. So the radius of convergence is 1 because that is the radius of convergence for the geometric series we started with. And the geometric series is also a form of a power series, and the radius of convergence remains the same after differentiation or integration, as per my earlier video. So if the power series, the summation is Cn times x minus a power of n. So in this case, a is 0 for the geometric series, or our geometric series. And then those are just coefficients, and it has radius of convergence r is greater than 0. Then the function defined by right here, fx equals to this summation is differentiable and therefore continuous on the interval a minus r and a plus r, and the derivative is equal to this, and you bring that down so you can take derivative inside as we did, and you can also take integral as well, and so on. This is just a note that they just rearranged this so that this part here looks like this, as opposed to here. So there's a c0 here. If you take the integral, it's going to be c0 times x, and so on, but they just write it like this. So you have this c there, coefficient. But anyway, so that's for the integral. And going further, let's put that for reference. And so basically this just means that the d over dx, the derivative of this power series, is the same thing as having d over dx of the inside, and so on. In other words, term by term, and so on. So that's what we have. And notice here, the radius of convergence of the power series in equations 1 and 2, the derivative or the integral, are both r. So that is the key. And again, from my earlier video. So since the radius of convergence doesn't deal with the endpoints, because remember, we're asked to find the interval of convergence. So find the interval of convergence of the following series and find its sum. So radius convergence is not the full interval. And so it's not necessarily the full interval, and again, so we have to do the endpoints separately. So since the radius of convergence doesn't deal with the endpoints, we have to determine convergence separately at the endpoints. So if x is equal to plus or minus 1, the series diverges by the test for divergence. And recall this for divergence from earlier video is just here. If limit as n approaches infinity of an does not exist, or if the limit as n approaches infinity of an is not equal to 0, then the series summation from n equals 1 to infinity of an is divergent. So if it's not exists or it's not equal to 0. Yeah, so in our case here, at x is equal to plus or minus 1, then our summation, let's put this a bit better. So at this, at plus or minus 1, we have the summation. Write this nicer. Okay, one more time. Yeah, here just pause and added it there. So summation from n equals 1 to infinity of n cubed of xn. This equals to, plug it in. So if we plug in our infinity, yeah, like that. So summation from n equals 1 to infinity of n cubed of plus or minus 1 to power of n. Then this right here, well, this is this is 1 is always going to be 1 or plus or minus 1, and this infinity as n goes to infinity, well, this becomes a infinity cubed times it by plus or minus 1 to infinity. In other words, we're just going to be either having plus or minus infinity, and this is not equal to 1, so it does not exist, and it's not equal to 0. And yeah, it just doesn't exist either. So we could just do that. So it equals plus or minus infinity, like that. And I'll just move that over here. So this is equal to plus or minus infinity, and again, this is same thing as approaching infinity cubed times it by plus or minus 1 to the infinity, and it's going plus or minus infinity depending on. Yeah, it's going to be alternating actually. Yeah, plus or minus infinity because of the 1 there, and for odd power or even power, it's going to be plus. It's going to be minus for odd, and then even for even power. I mean, it's going to be positive for even and negative for odd. All right, yeah, so since it goes to infinity, so it does not converge there, so thus the interval of convergence is open bracket, -1 and 1. So just so not at the endpoints. All right, very interesting. So now let's continue to problem 10. So if a0 plus a sub 1 plus a sub 2, etc. plus ... plus an is equal to 0, and we are asked to show that the limit as n approaches infinity of a0 times square root n plus a1 times square root n plus 1 plus a2 times square root n plus 2 plus ... plus ak times a times square root plus square root times n plus k is equal to 0. Yeah, so show that this whole limit is approaches 0, so equals 0. If you don't see how to prove this, try the problem-solving strategy of using analogy, and basically try the special cases k equals 1 and k equals 2 first. If you see how to prove the assertion for these cases, then you will probably see how to prove it in general. Alright, so now let's take a look at the solution. Basically, we're given this, and then we have to show this. And we're given a hint to use analogy. So my calculus book describes the problem-solving technique of using analogy as follows. So use analogy. Try to think of an analogous problem, that is a similar problem, a related problem, but one that is easier than the original problem. If you can solve the simpler problem, then it might give you the clues you need to solve the original, more difficult problem. For instance, if a problem involves very large numbers, you could first try a similar problem with smaller numbers. Or if the problem involves three-dimensional geometry, you could look for a similar problem in two-dimensional geometry. Or if the problem you start with is a general one, you could first try a special case. Alright, so we are hinted at trying a specific case. Basically, use analogy to just break it down and or try something simpler as opposed to trying to solve the full problem right away. So let's try the special case of k equals 1 and k equals 2 first. So let's first try the case k equals 1. So for k equals to 1, we have a0. So this goes all the way to k is 1. So we have a0, a1. So a0 plus a1 equals to 0. So a0 plus a1 is equal to 0. And then we got to show this setup here. And if we could resolve this, so then a1, move this over to the other side. So that means a1 is equal to is equal to negative a0, like that. So we could throw this inside. And now we're going to take the limit. So limit as n approaches infinity of a0 times square root n plus a1, let's put it here, plus a1 times square root n plus 1. And let's go back above here. So that is what we're asked. And so then you have a0, square root n, a1, and then n plus 1. In our case, when you have n is 0, actually we haven't got to that, but yeah, it's just square root n and then square root n plus 1. So yeah, that's what we have there. And we know, and we just end up at ak is 1. So we don't, and this is n plus k, yeah. So we go all the way until k is 1. Yeah, so that's k, yeah, so we go to k is 1, so we just stop there. And then again, we have to take the limit as it goes to infinity. So it's a bit more work here. So let's go, so now we have this. And now we're going to take our a1 and throw that inside here. And then, yeah, what we end up having is this equals to limit as n approaches infinity of now it's going to be a0 square root n minus a0 square root n plus 1. All right, so now that we have that, and we're going to now factor out the a0. So this equals to a0 times by, times by limit. So limit as n approaches infinity of square root n, let's write this a bit neater, square root n minus square root n plus 1, like that setup. And this is all bracket times it by, yeah, so we just have this. And now the trick is, Calculus Book does it, is, well, we'll multiply this by, instead of minus, same thing but plus, we'll have a bunch of cancellations. So we're going to multiply this by square root n plus 1, and divided by square root n plus square root n plus 1, like that. And then, and notice a bunch of cancellations. Notice that we're going to multiply this inside top, and then over here, this goes here, etc. And then this multiplies this and that, etc. So I'm just going to erase that. So this equals to, so it's equals to a0 times by limit as n approaches infinity. And now we have n times square root n times square root n is equal to, let's put a giant line like this. This just equals to n. And then we have square root n times square root n plus 1. And that is just going to be, I'm just going to keep that out of there. So plus, this is, yeah, again, square root n times square root n plus 1. Square root n times square root n plus 1. Like that. And just because it's not the same base inside there. It's not the same thing that you're square rooting. And then the next one is negative square root n plus 1 times over here. So we're going to subtract it as square root n times it by square root n plus 1. So we're going to cancel these two out. Those cancel. And then the last one, negative square root n plus 1 times this one here. That just becomes, well, the square roots cancel. And we're going to become n plus 1. And yeah, I forgot a minus sign here. So there's a minus here because we have this minus there. And we're multiplying here. So this one, this by this, and this by that. So we'll have a minus over here. And then divide this all out by, well, this part here, square root n plus square root n plus 1. So what this equals to, yeah, what this equals to is, well, this becomes a0 times it by limit as n approaches infinity. So everything cancels, even this one cancels with this. All we're left with is a negative 1 there. So negative plus 1, so it's going to be negative 1. negative 1 over square root n plus square root n plus 1. And now we could take the limit, because we couldn't do it before because you have a bunch of infinities and etc. You'll have infinity minus infinity and so on. So now we have over here, this becomes, well, at the bottom, yeah, or actually here, just this whole thing. I'll just do this whole thing. This approaches, well, negative 1 over infinity plus infinity. So as n goes to infinity, if square root infinity, it's still going to be infinity. So square infinity or infinity is both approaching negative 1 over infinity. In other words, it's approaching 0. So this equals to 0. So we've proved it for case I. So this limit approaches 0 there. Alright, so now let's try the general case. We can actually see that how we can solve this. Although the hint gave us, will ask us to try special cases k equals 1 and k equals 2 first. The solution manual doesn't do k equals 2, and I'm not going to either, so I'll just jump straight ahead to the general case. So let's try the general case. So we're given that a0 plus a1, so plus a1 plus a2 plus plus ak is equal to 0. So that is what we're given. Remember, for k equals 1, we just go a equals 0, no, a0 plus a1, etc. But now we have a all the way to ak. So this means, and we're going to do the same thing. So if we had a1 is equal to minus a0, so then k equals n would just be minus everything else. So we have this, and now we're going to move all this over to the other side. So that means ak is equal to negative a0 plus, or negative a0, negative a1, negative a2, minus all the way until negative a, or put the negative sign, negative a k minus 1. So this whole thing equals to this. I'm going to box this out because this is important. I'll box the whole thing out because we're going to be throwing this into the entire limit. Alright, so thus we have limit as n approaches infinity of a0 square root n plus then it's going to be a1 square root n plus 1. And yeah, let's just go back to the limit, how it looks like. So yeah, n plus 1, it keeps going on and on. So square root n plus 1, square root n plus 2, all the way to n plus k. And we get, yeah, plus a2 square root n plus 2 plus plus ak, so ak like this, square root n plus k. Alright, so we have all that. So what it means is, well, we know ak is equal to this. So what we'll do is write this as, well, this equals to, we'll have two parts. So this equals to limit as n approaches infinity of, and then the first part is on the top. I'll just do this bracket like this. a0 square root n plus a1 square root n plus 1 plus a 2 square root n plus 2 plus Instead of going all the way to ak, we'll go to ak minus 1 and then square root n plus k minus 1. Like that. So we're going to go the second last term, and then we're going to replace ak with this equation. So we're going to have now plus, and I'll put this all over here, plus plus negative, I'll put this all in a giant bracket, negative a0, negative a1, negative a2, negative all the way to ak minus 1. This is k minus 1, and then we'll have square root n plus k, like this. And this is all closed bracket. And again, this right here, this whole thing is equal to our ak, like that. And now what we'll do is a pretty cool magic trick. So I'm going to take this this right here. I'm going to factor out the a0 from this and multiply this inside to the each one. So we're going to do that to each one. So this equals 2, and then take out the a0. So a0 times by limit as n approaches infinity of each of these separate stuff. So we're going to take out this a0. This is going to be now square root n, and then minus square root n plus k, like that. And then we're going to do the same thing for this one and multiply this inside this right here and factor that out. So this equals to a1 times the limit as n approaches infinity of, this is going to be n plus 1, and then n plus k. So n plus 1 minus square root n plus k, and then dot dot dot, keeps going on and on. So plus dot 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 plus the last one is, well, this multiplied by this inside here, and we're going to go and factor this out. So this is going to equal to now a k1 or k minus 1 times it by the limit as n approaches infinity of square root n plus k minus 1 minus square root n plus k. And now this is the exact same thing as this setup here, square root n minus square root n plus 1. But instead we're going to be dealing with n plus k minus 1 and then n plus k. And then we're going to multiply the top and bottom by the same thing, by n plus k minus 1 and then times plus n plus k, and then divide it by that. And then we're going to do a bunch of cancellation. We're going to have a similar, or pretty much, very similar setup. And it's going to be 1 over infinity approaches 0. So every single one of these is going to go to 0. So we could just put this whole thing equals 0, but Calculus book just has some more writing just to clarify. So each of these limits is 0 by the same type of simplification as in the case k equals 1. So we have put it all together, a limit as n approaches infinity of a0 times square root n plus a1 square root n plus 1 plus a2 square root n plus 2 plus dot dot dot, just for completeness sake, square root n plus k. This all equals 2, and then this equals to, all this is equal to 0, so then this equals to a0 times 0 plus a1 times 0 plus a2 times 0 plus dot 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 a k minus 1 times 0. So this whole thing is equal to, you guessed it, 0. And we've proven our setup. So there it is. We've proven the question that we're asked to prove. So it says use this to prove that this whole limit equals 0. And we just did. Alright, so now let's continue further and look at problem 11, and this one states find the sum of the series, so the summation from n equals 2 to infinity of ln of 1 minus 1 over n squared. Alright, so now let's go over the solution. So let's try to simplify this series. And what we can do is, well, let's just simplify this. So we get ln, I'm going to take the inside terms. So ln of 1 minus 1 over n squared, and multiply top and bottom by n squared, so that we get a ln of n squared. So n squared minus 1 over n squared. And now we could apply the log rule. Remember this one, when you have a division, this is the same as a subtraction. So this is ln n squared minus 1 minus ln n squared. And this is a, this is a log rule right here. So log rule, put a better logarithmic rule or ln rule, in this case natural log. Same thing, so log rule. Alright, so now that we have this, and then what we could do here, we could do this another log rule, and that is by, well, looking at this setup here, and then writing this out here. I'll just say, yeah, let's put it here. So note that because it's n squared minus 1, so it has some cancellations. In other words, if you had an n plus 1, we'll put it here. N plus 1 times it by n minus 1 when you expand this out. So n times n times negative 1, and then the same thing on the bottom. So what you're going to get is a n squared plus, n times negative 1 is minus n, and then here 1 times n. So here 1 times n is going to be plus n, and then 1 times negative 1 is minus 1. So these cancel. This equals to negative n squared minus 1. So whenever you have a squares like that, so n squared and 1 is the same thing as 1 times 1 is squared. It is just 1 squared. So when we have that, these cancel out, so we could write it as that, as this setup. So this means that we have, so this equals to ln of, instead of n squared minus 1, we get n plus 1 times it by n minus 1. And this is a ln of all that. So ln, just put a giant bracket. And then minus ln, and then also another log rule, the 2 goes down. So 2 go ln n, like that. And this is another log rule. And then this becomes right here, this whole setup equals to ln of, so when you have a multiplication, it becomes a addition. So that's a useful thing about logarithmics. So ln n minus 1, and also another log rule all the way across here. So then, yeah, so this log rule, this breaks it down into this right here. So that's another log rule. Let's put another arrow. So these are all just log rules. And then minus 2 ln n, like that. And another trick is, again, the solutions manual has a pretty next level trick. So this negative 2 ln n, just break that down into negative ln n minus ln n. So just separate that out. And now we're going to combine this to use ln rules. So I'm going to take this, yeah, I'm going to have this for each one of these. And notice there's an n plus 1, there's an n minus 1. Alright, so what we'll do here now, again, this is why it's problems plus, because this is very hard to grasp unless you're an absolute expert. So let's say we have ln n minus ln of n minus 1, and then subtract by ln n. We'll group that together, and we'll group this and this together, and yeah, so this and this one and this one. All right, so what we'll have is this equals to ln of n minus 1 minus ln n. I'm going to put this close brackets, meaning separate from the others. So that's this one right here. And now the other one is going to be, I'm going to subtract so that we have, yeah, so we have it similar so that the higher number, n plus 1, is at the bottom. Notice here's n minus 1 is first. N is 1 smaller, is 1 bigger. So that's at the bottom. That's on the right side. And then we're going to be dividing it using log rules. And then this is n plus 1. This is n. And we're going to have this first, this one second, because that's bigger. So this is going to be subtracted out, so we can factor out the negative. So this becomes first, ln n minus ln n plus 1. And the reason is, again, if you've seen this as you go through this video, telescoping sum is one of the most useful stuff ever. So this equals to, yeah, so then put it all together. Let's put this here. So thus, ln of 1 minus 1 over n squared is equal to, and again, using log rules, bring it down, this becomes ln of division. So when a subtraction becomes a division, n minus 1 over n, like that. And then minus this part right here, ln of n over n plus 1. Bold this. And put an arrow here. This one goes on this side here. Put that there. Alright, yeah, so basically this, of course, looks like we have another telescoping sum, and we could see that as we continue on this. So if this is the series, let's go to the partial sum, and since we already have n, a whole bunch of n's there, well, in this particular one, they just let the sk's partial sum equals to the summation up to k starting from n equals 2. And again, it just shows you different ways of solving it. You could either put I equals 2 up to n, etc. So we'll just do it this way. So ln, just because this solution manual did it this way. So 1 over n squared. Yeah, so this is this whole thing right there, starting from n equals 2. This equals 2, and in our case, we'll use k. So now we're going to throw that inside. So up to k, starting from n equals to 2 of ln, and ln, put a bracket, n minus 1 over n minus ln n over n plus 1. And again, you could see that this is telescoping sum because notice here is n minus 1 over n, and then there's a minus sign, so you always need the minus sign to cancel things out. And now each one of these terms, n minus 1 plus 1 is n, and then this n plus 1 is n plus 1. So these are one larger than this. So obviously we're going to have a telescoping sum here. And this, of course, is for k is greater than, let's put it here, this is for k is greater than or equal to 2. All right, so that's what we have, because it's, n is 2 is the starting point. Let's put this a bit neater. For, or not handwriting, for k is greater than or equal to 2. All right, so now what we have is sk is equal to, so that's the sk there. Yeah, and let's just expand this all out. So this sk is equal to ln 2. So ln 2 minus 1 is equal to 1 over 2. So when n equals to 2, yeah, so ln sk is the first term is when n equals to 2. So 2 minus 1 is 1, and then 2 there. Subtracted by ln of 2, and then n plus 1 is, 2 plus 1, so 3. And put this bracket, and then the next term is the n equals to 3. So ln, put a bracket first, ln, and then 3 minus 1 is 2, over n is 3, like that. Subtracted by, and then the next one is ln 3 over n plus 1, or 3 plus 1 is 4. And again, there's a cancellation right here, cancellation here. And then we keep doing this on and on. Let's do the next one here. Yeah, and just the next one is for n equals to 4, so plus, not equal, plus, put it here, plus ln of 4, so 4 minus 1 is 3, over 4, n is 4, minus ln 4 over n plus 1 is, 4 plus 1 is 5. And then this cancels with this. And then plus, plus, then we have all the way until ln of n minus 1 over n plus, minus. This is going to be minus, actually this is up to the k. Up to k, all the way to k, and then k minus 1 minus ln, where n is k over k plus 1, like that. And then this one eventually will cancel, and this ln 4 will cancel. All we're left with is this and this. So this all equals to ln of 1/2, ln 1 over 2 minus ln k over k plus 1. All right, so put the arrow here. So sk is equal to this, and box this out. All right, so thus, put this all together, we have the summation up to infinity from n equals to 2 of ln 1 plus 1 over n squared. Actually it's minus. It's going back here, it's a minus, not a plus. It's a minus, is equal to the limit as the kth partial sum goes to infinity. K's partial, k goes to infinity of sk. This equals to the limit as k approaches infinity of we have here ln 1/2. Yeah, ln 1/2, and then minus ln, and then where just put k like this, k over k plus 1. And now we're going to do here, and yeah, just put a stop like that. And what I'm going to do actually, again, just to get rid of this k stuff, and because we're going to take a limit, I'm going to multiply this by 1 over k on both sides, or just on top and bottom, I mean, of this ln right here, 1 over k over 1 over k, like that. And just put this bracket here, just to save some time. So now this all equals 2, move the ln 1/2 out of there. So equals ln 1/2 minus limit as k approaches infinity. K approaches infinity of, this is going to be ln, divide this out there. So it's going to be a 1. So 1, like k divided by k is 1. And then we'll have this k divided by k is 1, and then plus 1 over k. And this becomes 1 over 1 plus 1 over k. Like that. Yeah, so that's what we have there. And then this part right here, this approaches, well, 1 over infinity, approaches 0. So in other words, yeah, this whole thing equals to ln 1/2, or actually you could use a log rule. We'll put it over here then. So then this part right here equals to using log rule. Well, again, we already knew this log rule. So 1 over 2. 1 divided by 2 equals the same thing as subtraction. So ln 1 minus ln 2, and then this one over here becomes, limit is going to be just 1 over, or I forget the ln. Yeah, so just move that over there, put a ln there. So this becomes ln of 1 over 1 minus, 1 plus, 1 divided by 1 plus 0. So that's just ln 1. So that's just equals to ln 1. This cancels with this. And then this whole thing is equal to, well, equals to negative ln 2. And there's our sum. So that is absolutely fascinating. Yeah, so we're asked to solve for the sum of this one. And we get this negative ln 2, which is quite fascinating. Anyways, let's continue further. Now we'll look at problem 12. And again, we have 26 problems plus that example, so that's 27 total. So we are well on our way, almost halfway of the video, or of the questions. So yes, we have problem 12. So suppose you have a large supply of books, all the same size, and you stack them at the edge of a table, with each book extending farther beyond the edge of the table than the one beneath it. Show that it is possible to do this so that the top book extends entirely beyond the table. In fact, show that the top book can extend any distance at all beyond the edge of the table if the stack is high enough. And then it says use this following method of stacking. So the top book extends half its length beyond the second book. The second book extends a quarter of its length beyond the third. And the third extends 1/6 of its length beyond the fourth, and so on. And it says try it yourself with a deck of cards and consider centers of mass. So we have here is our setup right here. So here's a top book right here. It's half distance. The next one, it's a quarter from the second one's a quarter from the next one. And the third is 1/6, and so on. Then it goes to 1/8. And in this case, there's 5 books, and it stops over at the edge here. So it's quite fascinating. So this entire thing is over the edge there, and it's still balancing. So theoretically, this can extend forever, or it would be a bit higher though, like a log curve. So extend forever. And yeah, we're asked to show that the top book can extend any distance at all. But first show that it's possible to do this so that top book extends entirely beyond the table. And then, yeah, to basically show it for any distance at all, which is quite fascinating, beyond the table. All right, so solution first, let's note the pattern of distances in our construction method. So we have this 1/2 there, and this distance right here, this book is just given length 1. And there is 5 books, 1, 2, 3, 4, 5. So there's 5, and now what we could note this pattern. So this 1/2, you could write this as 1 over 2 times 5 minus 4. So that this just equals to 2 times 1. This equals 1 over 2. Now this next one right here, this equals to, well, 1 over 2 times it by 5 minus 3. Yeah, so 5 minus 3 like that. this equals 1 over 2 times 2, which equals 1 over 4. This next one, similarly, you can see the pattern, 1 over 2 times 5 minus 2. So notice this, it goes from 4, 3, 2, and so on. This equals to 1 over 2 times 3 equals to 1 over 6. The next one here, yeah, so these are getting bigger and bigger. So this, you're multiplying by a bigger number. And yeah, these are all just, yeah, it goes 2 times 1. This is 2 times 2, 2 times 3, 2 times 4, and so on. This next one is going to be 2 times 5 minus 1 equals to 1 over 2 times 4, which equals to 1 over 8. So you can see that pattern, and then there's flush with the book. Right there is the next one. Alright, so now that we have that pattern of this distances, so now let's place the y-axis and x-axis as shown below and let the length of each book be L. So as opposed to this example, which is just 1. So the center of mass, called COM, just for short, is represented with a dot, and N is the total number of books. So what we'll have is, so let's draw our table. So here's our table, like this. And let's say that's the table. And there's the legs right here. I'll just put a leg like that. So that's the leg. And now what we have is, let's say we have our book flush with over here, right at the edge there. And this is going to be our dot center of mass there. And now what I'm going to do is draw the y-axis. So the y-axis is right flush with this right there, y. And the x-axis is right at the center, right there. So that's the x-axis. Alright, here, just fix it up, made this more flush, and just remove that so it can extend indefinitely. Anyways, so now this length up to the center of mass is L over 2. Because the center of mass is important to see if it's going to be tipping over or not. We have to make sure the entire center of mass is less than, less than or equal to the edge there. Or basically less than the edge. So we have this center masses all the way up to here. And now that's the first book. And now the second book's going to extend like this. All right. And this distance right here. So this distance right here. And again, I'm going to make this in the center better. There's the center. And now this is going to be shifted over like that. And this distance, make this a bit more in the center. Alright, so that's in the center. Now this distance is the same as from here to here. It's the same thing. We're shifting exactly the same. Alright, just delete this. Alright, so that distance is the same, and this is equal to, as before, this is L over 2, then total number of books minus 1. Remember, that's the bottom one here. So total number of books in this case is 5, so minus 1. Whatever the number of books is. So that's the pattern. And now the next setup is we add another and extend this one accordingly. Now this distance is going to be like this. Make this black like that. This one is L over 2n minus 2. So yeah, you can see the next one right here. So this first one is going to be 1 over n minus 1. The second one is 1 over 2 times n minus 2. So the first one is 1 over 2 times n minus 1, n minus 2 over there. So that's fascinating stuff. Alright, so continuing further, so we want to show that the center of mass of the system of n books lies above the table. That is, the average or the mean distance center of mass is of the whole system is going to be less than L. So in other words, it's less than the full length all the way across this L here. So that's L, so it's less than this entire thing. So the average, so the full mass has to be less than this setup here, has to be not beyond the edge. All right. So note that X with this bar on top is called X bar and represents the weighted average center of mass of the system. And the X represents it's in the X coordinate we're looking at. So the X coordinates of the centers of mass of the books are, so let's write of each one. So we have this one here is shifted. Notice how it's all shifted here by this distance. So for X1, the first book on the table is equal to is L over 2. X1 is L over 2. So L over 2 like that. And then, that's x1 is L over 2. x2 is equal to, well, L over 2 plus right here, which is L divided by, L divided by 2 times, and then divided by n minus 1. So L over 2n minus 1. So that is x2. And then x3 is equal to, x3 is equal to, well, we start off from here, and then we just add this extra distance. So we're just adding this extra bit. So it basically equals all that. So it equals L over 2 plus L over 2n minus 1. And then add the next distance plus L over 2n minus 2. And so on, and this keeps going on and on. Then what we get is xn is equal to the nth book is gonna be L over 2. L over 2 plus L over 2n minus 1 plus dot 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 all the way. It keeps going all the way to the very end, and that end is going to be L over 2n minus, and notice how it's minus n there, it's one less than it. So it's going to be minus n minus 1, like that. Let's put a bracket, n like this. And this equals to, well, this just equals to n minus n, it cancels. And there's a negative 1 times a negative is be plus 1. So, so this equals to L over 2 plus L over 2n minus 1 plus dot 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 all the way until L over 2. So that's the final distance is going to be L over 2. As you can see here, the final distance is here is 1 over 2 for length L. So over length L equals 1. There. All right, here I just boxed this in and wrote that in. So now we have this. So each book has the same mass. So assume it's all the same exact book. So if there are n copies of this book, or just n books of the same mass and same length, then the center of mass of the x coordinate equals to the weighted average. So m of the book x1 of the center mass of that plus m x2 plus dot 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 plus m x3. So the total mass times the length, all divided by m. Alright, so this m divided by m times by the total number of books. So in other words, we get, the total mass. So basically, we're going to basically have an average mass. We have the total mass times by the average position of all of these. And these are all weighted by the mass. And each one based on how far they are. And how far they are, this is based on the x coordinates we set up here. So starting from here, so this would be x1 would be here, like that, and x2 would be over here. Those are the centers of mass, and you're going to see the average center mass of the entire books. All right, so then we have this, and we could factor out, or we could actually just divide out m on every single term like that. So it's not dependent on mass because they're all the exact same. So this equals to x1 plus x2 plus dot 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 plus x. This is this one's xn. This goes to xn like that. All divided by n. And now this all equals to. Let's put this 1 over n over here. And now x1 is equal to. Well, that's x1 is just over here. L over 2. So that's the first one, L over 2, plus, now x2, that is L over 2 plus, the next one is L over 2 and minus 1. And then L over 2 and minus 1, like that. All right, and then that is that's x2. The next one is, just for completeness, L over 2 plus L over 2 n minus 1 plus, this is going to be L over 2 n minus 2, like that. So this is our x3, this is our x2, and this is our x1, like that. And then it keeps going on and on. So plus, all right, plus, dot, 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 plus, and then we're going to have now our xn, L over 2 plus L over 2n minus 1 plus dot 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 all the way until L over 2, like that. And this whole thing is our xn, like that. And you can see that that's over here, that's our xn, like that. And now we could start simplifying and noticing some patterns. And that pattern as well, if you look at here, so there's an L over 2 here, L over 2 here, L over 2 here, and then all the way here to L over 2. In other words, there's n L over 2. So we could write this as, let's write this as, first write this 1/2, a 1/n. So 1 over n, times it by, now we have here n times L over 2, n L over 2. And now the next segment is this is here. This appears here. This appears everywhere except the first one. So that means we're going to have plus n minus 1 times of L over 2n minus 1, like that. And then similarly, you could see over here, there is right over this next one is going to be L over 2n minus 1, minus 2. And this appears everywhere except on this on x2 and x1. So that means we're gonna have it all the way across here, plus n minus 2 times L over 2 n minus 1. And then lastly, plus dot dot dot, plus all the way across here. And then this last one is just by itself, L over 2. And you can see that here. So this one adds it all, and then we removed all of them as part of this this dot dot dot, and the last one is just this L over 2. Yeah, because we have first we have L over 2 times n minus 1, that cancels. So everything cancels until the very end is the nth one, and that nth one, yeah, and that last one just occurs just once. And you can see that in this pattern here. So notice this L2 occurs in here, but not this one. This one's by itself. This one occurs and did this. Then this one occurs in this, and then you're always left with a 1 by itself. So in other words, we're going to be left with L over 2 there. So this becomes L over 2, like that, and put a square bracket. All right, so what we have now is, well, notice all these all just cancel. Cancel, cancel. This is actually n over 2, not 1. Minus 2, so that's this one right here, and it all cancels. So this all cancels, and we're just left with that. And what we get is equals to 1 over n times it by n L over 2 plus L over 2 plus L over 2 plus dot 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 plus L over 2 in this last one. And then the total number of these L over 2 is all the way across here. This is n minus 1 times. So that's how many times it occurs. And you could see that here. So if you have this x2 L over 2, get that separate. So we're ignoring all the L over 2s in the beginning. That's for this n L over 2. And notice here, there's 1 here. And there's a 2 here for this x3. And there's going to be n minus 1 for this xn all the way across there. Yes, which is quite fascinating. And we can see the number 1, 2. For x4, we'll have 1, 2, 3. Yeah, 1, 2, 3. This is 1, 2 for x3. And this is 1 for x2, and so on. All right, so we have all that. So this means this equals to 1 over n, and then we're going to have a n L over 2 times, or plus n minus 1 times it by L over 2, like that. All right, so now what we'll do is factor out the L over 2. I mean this L right here, factor out this L out of there, and then we have the common denominators too. So we'll factor out the L, and then we're going to write this as, so then it's going to be n plus n minus 1 over 2, like that. And this combines together, we get L over 2, and then 2n minus 1 over 2, like that. Actually, this is not a 2, this is n. Yeah, n2, they look similar. So like that. Yeah, so in other words, we get here L over, and there's a 2 there, so L over 2n times it by, or actually put the L by itself. I'm going to put this 2n in front. So 2n minus 1, and put this 2n together, 2n, and then put the L like this by itself here. And now this top part is less than this one. So this is less than 1 because this 2n minus 1. Yeah, 2n, put this, not a, it's not a, yeah, so this is 2 times n less than 1. And that is less than 1, so that means that this is less than L because you have a less than 1 number times by L. So it's going to be a less than L, that, like that. So that means that the weighted average is less than L, so it does not extend outwards. Yeah, so it's going to be less than L, where L is this. So the average of all these, the mass is going to be less than L. So in other words, it's not going to be tipping over, which is quite fascinating stuff here. Yeah, so this shows that no matter how many books are added according to the given scheme, the center of mass lies above the table, so it doesn't go over the edge. So that's quite fascinating. So it remains to observe that the following series is divergent. In other words, it's a harmonic series. So the distances, if we look at the distances here, so this distance 1/2, 1/4, 1/6, 1/8, etc. So notice that half set up here. So if we have that, so let's say we have 1/2 plus 1/4 plus 1/6 plus 1/8, and it keeps going on and on. Yeah, plus 1/10 and so on, 1/10, so on, plus dot dot dot, all the way. This equals 2. So then if you factor out 1/2, we get a 1/2 times it by, and then this times it by up to infinity, starting from n equals 1 of 1/n. So initially is 1 over, this one is 1/2 times, yeah, this is 1/2 times 1. This next one is 1/2 times 2. Next one, 1/2 times 3, etc. And it keeps going on and on. And yeah, so 2 times 3 is 6 and so on. So this right here, this is divergent. It's a divergent harmonic series as per my earlier video. And yeah, so here, this is divergent. I'll just write this down, divergent. So in other words, this total goes to infinity, so distance can be as far as you want. So recall that the harmonic series is a divergent P series with P equals 1 from my earlier video. So the P series, summation from n equals 1 to infinity of 1/n to the power of P, is convergent if P is greater than 1, and it's divergent if P is less than or equal to 1. And in our case here, n is to the power of P. N is equal to the power of 1, where P equals 1. So thus we can make the top book extend as far as we like beyond the edge of the table if we add enough books. We got infinite books, and so on. Alright, so let's continue further and now look at problem 13. And this one states, if the curve below is rotated about the x-axis, the resulting solid looks like an infinite decreasing string of beads. And where the curve is y equals e to the negative x divided by 10 times it by sine of x for x is greater than or equal to 0. And in part A of the question, we're asked, find the exact volume of the nth bead. Yeah, so when we rotate it about the x-axis, we get a string of beads. So the nth one, we want to find the volume. And then it says we're given a hint, use either a table of integrals or a computer algebra system. And yeah, this is the calculus book is a bit old. They could just use an online calculator instead, because there's a lot of powerful ones out there. So, and then part B says, find the total volume of the beads. Alright, so let's jump right into the solution. So let's look at solution to A first. And this says, first let's graph it out first. So this is the curve y equals e to the negative x over 10 times sine x. So here's the curve, and I'm using Desmos calculator. If you graph it out, it looks like this. It's just a just squiggly line that's decreasing. And if you rotate about the x-axis, so this is the x-axis, rotate it all the way across, you're going to get something that looks like this in 3D. In 3D, yeah, so you have a bunch of beads in 3D. It's a bit hard to visualize like that. Yeah, and then, yeah, so if you graph it out and rotate it, you have a bunch of you had a bunch of beads. And in fact, so the solution manual didn't graph it in 3D, but I have. So if we rotated the curve about the x-axis, we can graph the resulting shape using the amazing GeoGebra 3D calculator by representing the curve as the radius of a circle. So this link right here illustrates this concept. So geogebra.org right here. So any cross section parallel to YZ plane has equation y squared plus z squared equals to f of x squared. In other words, this is just the equation of a circle, where this is r. Yeah, so that's r, and then you're squaring it. So this is just r squared. So if you have this here, and if this is the y, and I believe, yeah, this is the z. So that's y, this is z, this is x. And then x is then you'll have the radius is a variable function, f of x. So radius is a variable function. As you move, as x changes, you're going to change it, and then you're going to draw a different circle, and so on. So you get a 3D shape. So what you can do is in GeoGebra solve for z. So you'll have z equals 2 plus or minus square root. Now let's do this, plus or minus square root of f of x squared minus y squared. So move this over and square root it, and then you'll get this plus or minus, and then those correspond to the top and bottom of the curve. So the top and bottom, and here I've graphed it out. So solving for z, we get 2 square roots, which corresponds which correspond to a 3D surface. Yeah, so we have here GeoGebra. Here's a link right here, and here's our f of x. So you could write f of x equals to e to the power of negative x over 10 times sine x, and then you could plug this inside. Here's the first function, a of xy equals to square root the positive f of x squared minus y squared, and the next one is negative. So same thing but negative, and you get this bottom half, and then there's the top half and bottom half. And you graph it in 3D, it looks like this. It's just quite fascinating. If you click here, just open it up just to illustrate this calculator, which is quite amazing. And it's a bit slow because I'm using my Surface Pro as opposed to my PC, my computer or desktop. So it's a bit slow and lagging, but you can see it's pretty cool. And you can move it around, rotate, and play around with it. And absolutely fascinating stuff here. And yeah, so it looks like infinite string of beads, and you just keeps on going and on. Alright, I'll just leave here. So yes, that is the curve. And notice the zeros here. Well, the only place that can be 0 is the sine function. Sine function is the only way it can be 0. E to the negative x over 10. That only approaches 0 as x goes to infinity because of this negative power, but never actually equals it. The only time it equals 0 is when sine of x is equal to 0. So then, in other words, we can find the nth bead based on the zeros of the sine function, or the endpoints of each bead. So as we can see above, the solid looks like an infinite decreasing string of beads. Now let's determine the volume of the nth bead. So the x-intercepts of the curve occur where sine of x is equal to 0. Alright, so the x-intercepts of the curve when a sine of x equals 0, well, let's write that out. So we'll just draw it out. So here's the sine, and we're only dealing with x is greater than or equal to 0. So this is x, and this is our sine of x, the y, the vertical axis, the y-axis, sine of x, and this is like this. And it keeps going on and on. So this is pi. This is 2 pi, and let's make this a bit better. And it keeps going on and on. So that's 2 pi. Yeah, that's good enough. And then there's the 0 there. So it's 0 at, so I'll write this at sine, I'll just put this on here, sine of x equals to 0 at x is equal to n pi, which equals to 0, pi, 2 pi, etc. So in other words, n is an integer right there. And I'll just put n equals integer. And in this case, a positive integer because our x is our x is positive. Alright, so thus, recalling the formula for disks we have, and we just go up to pi, or n pi each time. So what we'll do is, and I'm going to write this as, so here is the x and y. We're going to do this in 3D actually. So this is, I'm just going to make this straight line. This is our x, this is our y, and now we have our z like this. So that's our z. I'm going to draw this like this. Make it slightly decreasing. Like that. So then at this point here, I'm going to call this n pi. And then the one behind it, I'm going to call this n minus 1 pi. So just the one before it. So it just generically wherever we are. So it could be at, yeah, this could be n, and then over there is n minus 1. And so on. So that's where the beads are. So we're just going to look at it over here. And then now what we'll do is I'm going to take this shape and rotate it. So let's just pick a generic point here. Let's do generic point x here. And at this point, we're going to, let's say, all the way up above here. Rotate that, and then it has a thickness. Or actually, instead of putting it over that side, I'm just going to grab this. So we're going to rotate this all the way across, like that, and then rotate across here, dot, 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 and then put this around here. Yeah, so we have this 3D shape like that, where this height is y, so all the way to the bottom, x, and this thickness is dx. So it's thickness dx, so in other words, the volume, so this volume right here, this full volume dv, we'll call this slice there, that disk, is equal to, well, we know that it's going to equal to pi r squared. Y is r, so pi y squared times by dx, times by the thickness. So in other words, this is area equals pi r squared. This part right here. So that's just area equals pi r squared, and then dx is the thickness. So that's the slice of the volume. And yeah, and also just for completeness, I'm going to put over here, this at this segment here, this is at n plus 1 over pi. So yeah, at each 0, we're always going to be incrementing by 1, and then pi, like that. Alright, so that's dv. And now what we'll do is put in our nth one. So the the volume of the nth bead is equal to the summation, I mean not the summation, the integral. We're going to integrate from n minus 1 pi all the way to n pi of dv, of that slice. So we're going to go from here all the way to here. And then this equals to integral from n minus 1 pi, like this, n pi, and right over here, pi, then y. Well, we know y is our function. So y is our function over here, e to the negative 10 over x times sine x. So that's our y function. So we'll put it over here and write this down. So e to the negative x over 10 times by sine, e to the negative x over 10 times by sine of x, all squared, dx. Yeah, now dx is over there, so we just plug that inside, and now we're going to do some, well, slight simplification. This equals to, take the pi out, this equals to integral from n pi, and then from negative 1, n minus 1 pi, up to n pi. And now this is going to be e to the negative x over 5. Yeah, that's because it's 2. So when you have this x to the 2, then divide by 10 is 5. So x to the e to the negative x 5 over 5. And then times it by sine squared x. X all dx, like that. Let's put this neater. Alright, so that is our Vn. I'm going to put this Vn equals 2 and box this whole thing. Alright, so now that we have this formula right here, well, it's still just an integral. We want to solve it and solve the integral. So again, we were asked to use, the hint was use table of integrals or a computer algebra system. So we want the exact volume of it. So we'll just use a computer algebra system on line 1. So we can now use the computer algebra system from integral-calculator.com. So going over here, we'll have, and then you plug that inside. So integral from -1 minus n minus 1 pi times n pi of pi times e to the negative x over 5 sine squared x dx. And then you get this giant one here, this plus c. Yeah, this is just the indefinite integral or antiderivative. And now if you want the definite ones with the plug in this n minus 1 pi into and this n pi, we get this right here. So we get this right here, and then plug this inside and subtract it from the bottom one. We get this whole setup, and then this simplifies it down into this giant one. But we can simplify the resulting formula even more, because note that there's a sine 2 pi n, and in our case for integers this equals to 0. And this one right here, this equals to 1, and we can see that. So we can simplify the resulting formula. Again, recall, we always draw our cosine and our cosine. Let's put this theta like this. So recall right here our cosine and sine. So I'm going to put this like this. This is cosine is at 1, and this is at 0 value. This is at over here is pi over 2, but then right here is pi. But the only one we care about is the 2 pi's, because we have this cos 2 pi n there. So this is the 2 pi there. This is 0, and this is cosine theta. So notice how this one goes all the way across to the 1. And it keeps going on. And likewise the sine. So sine's going to go here. If it's there, it's here. And then this negative is going to be over here. And then it goes to 0 here. So just the opposite of that. So this one goes to there, goes to here, goes here. So if it's a max cos, it's minimum. It's at 0, 10. I mean sine. So sine theta. That's 0 and 2 pi. So in other words, what we have is cosine of 2 pi n, where n is integer, this equals to 1. So all the 2 pi's, 4 pi, 6 pi's, all equal to 1 for cosine. And it equals to sine, for sine 2 pi n, this just equals to 0 for integers. So those are all, because remember we're dealing with integers, and so then this can go vanish, this can go to 1. And let's write this out. So, alright, so thus, let's put this all together. So thus our volume Vn at the nth bead, which is this is what we're solving for. Because remember, that's our Vn equals this giant integral, which equals to this, and it's simplified. So write 5 pi. So write this out: 5 pi over e to the 5 pi minus 1. E to the 5 pi minus 1. I mean pi over 5 minus 1, like that. So that's this part right here, times by e to the negative pi, then there's an n over 5, and now times it by, so and then this is all divided by first 202. 202, so that's all divided by 202, and let's go here. So this part right here, times by 10 sine 2 pi, that just goes to 0. So times it by 0, and then this becomes minus cosine 2 pi n, this is 1, minus 1, and then this is plus 101. Plus 101, like that. So then this becomes 100. Yeah, it's 100, and this is a negative sign to the power of. So this is 100, and then 100 times 5 is equal to 500. So this is 500 pi over 202. And then this part right here, we can multiply this inside, and that becomes, this is times it by e to the pi 5. And this is, this is pi 5, this is pi over 5. So what we could do is factor out this negative pi over 5 out of there. So we go negative pi over 5. And then that makes it, when you take it out, this becomes n, positive n. And this becomes negative 1. Like that. and minus, and there's a minus 1 here, so e to the negative pi 5n, like that. And as you could see, this is a telescoping sum right here. Well, yeah, there's a telescoping sum when we sum it to infinity, when we take the series. So this is Vn. So here's the exact one right there. So 500, actually, well, we could simplify it even further. This 500 divided by 202 divided by 2 on each side. This becomes 250. So I'll remove this. This becomes 250 pi over 101 times it by e to the negative pi over 5 n minus 1 minus e to the negative pi over 5 n. And Vn, like that. Just put Vn here. Vn equals to this. Like that. Alright, so we got the solution to part A. So let's go back to the question and look at solution part B. Or look at the question of part B. So that was the nth, that's the exact volume of the nth bead. So now we're asked to find the total volume of the beads. Alright, and also here, because this is just the integral, not the exact, we solve it, I'll just box this out, not the end there. I'll remove this. Yeah, just so yeah, it doesn't. We're not emphasizing it as much. So now we got to find the total. Yeah, so now we got to find the total volume of the beads. So in other words, take the sum to infinity. And again, that's because this function, the function we're looking at, is going towards. Yeah, it's just for x is greater than or equal to 0. So we're going to sum this up all the way to infinity. So this means, so that's the nth bead is this. So we're going to have infinite beads. Alright, so let's take a look at the solution to B and find the total volume. So method 1 is a telescoping sum, as per always. Alright, so the total volume is, using none other than the telescoping sum, is, so this is the nth one, but I'll just write it all out from the integral part. So this is the integral of the nth bead, but we're just going to go from integral from 0 to infinity. So we're going to go from the beginning all the way to the end, and then just yeah, write it over here. So the total volume is V equals to pi, take pi out of there, 0 to infinity of e to the negative x over 5. Yeah, so e to the negative x over 5, then times it by sine squared of x and all dx. And let's just double check that here. So yes, that is right here. So e to, yeah, from 0 to infinity of pi e to the negative x over 5 sine squared x dx. So this equals to, yeah, this equals to the summation, yeah, the summation of the nth bead from n equals 1 all the way to infinity. So we get infinite number of beads. So Vn, and that is our top part right here. Just put this all together. Yeah, then this will be summation up to infinity. N equals 1 of 250 pi 101 times, and then e to the, yeah, e to the negative pi over 5 times n minus 1 minus e to the negative pi over 5 times n. Alright, so this equals 2, and let's just write this out again. It's going to be the telescoping sum. Take the 250 out. 250 pi over 101. This is going to be times by the limit as n approaches infinity of, yeah, of the nth partial sum, which is, we'll just plug in this inside. Yeah, for n equals 1, we'll have 1 minus 1 is 0, so we'll have e to the negative pi over 5, yeah, times 0. Let's put this like this, times it by 0, minus e to the negative pi over 5 times 1. So that's this one right here. Again, we're going to get the telescoping sum in a bit. So next one is put n is equal to 2, and we're going to get, put bracket e to the negative pi over 5. 2 minus 1 is, well, just 1. And then minus e to the negative pi over 5. And then 2 minus, then this is just 2. And notice what we have here. This is right here. This cancels with this. That's just e to the negative pi over 5 times 1, and so on. And then the next one, let's go n is 3. We'll get plus e to the n minus 1 is going to be 2. It's pi to 5, and then times by 2 minus e to the negative pi over 5 times by 3. And then this cancels with this, and obviously dot 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 all the way to the nth one. We get e to the pi over 5 n minus 1 minus e to the negative pi over 5 times it by n. And then I'll close bracket, and then again this will eventually cancel with this using the telescoping sum, and we're left with just this and this. So this equals 250 pi times by, or divided by 101, 101 times it by limit as n approaches infinity of e to the negative pi over 5, and this is just 1, e to the 0, that just becomes 1, minus, and then it's just a minus right here, e to the pi over 5n. And instead of writing it like this, because there's a negative exponent there, I'm just going to put it at the bottom. So e to then make it positive. So e to the positive pi. So 1 divided by e to the negative, e to the positive pi over 5 times by n, like that. And then notice that this part right here, what we get is a 1 over e to the infinity as n approaches infinity, which is again 1 over infinity goes to 0. So in other words, this equals to 250 pi over 101 times by 1 minus 0. Yeah, so in other words, the total volume approaches 250 pi over 101. So it's equal to 101, like that. Alright, so that is the volume, but that was the method 1 using telescoping sum, but we could also use another method, so solution to be method 2 using the geometric series. So if we start off by using the volume in part A at the start of our simplification, we can notice a geometric series. Yeah, going all the way up over to here. So starting from here, yeah, if we just start from here, and so there's 100 right here, multiply that by 5, you get 500 over here, and so but simplify it to 250 pi over 101. So we'll start off at this position here, and then notice we can get a geometric series out of it. So let's just write that whole thing out. Actually, I'm going to write the summation from infinity, starting from 1 of 250 over 101, and then we're going to have pi times it by, and then if you recalled how that looked, it's key to make sure everything is correct. So e to the pi divided by 5, minus 1 times it by e to the negative pi n over 5, and then we'll have this 250 pi over 101. So this is pi positive pi over 5 minus 1 times it by e to the negative pi over 5n. And now compare that with a geometric series, which is the summation, and we're starting from n equals 1. So we're going to write it down as this. So if we recall geometric series, infinity, n equals 1, and it's a r n minus 1 equals 2, and then this equals 2. When you plug in 1, you get, well, a. So a, and then r 1 minus 1 is 0, then plus ar plus ar squared plus ar cubed plus dot dot. Yeah, dot dot dot. So that's key. Dot dot. Alright, so we're starting from n equals 1 on the top one as well. So what we can do is, well, first of all, note here, or I'll put this arrow like this. E to the negative pi over 5n, is equal to, what's equal to is, well, I'll just put a pi over 5, so n minus 1 plus 1, so that we can get the n minus 1 set up. This equals 2 e to the negative pi over 5 times it by n minus 1 and then plus 1, and yeah, it's going to be a separate over here, plus, but then there's a minus sign out there when we multiply that inside, pi over 5. Yeah, minus pi over 5, like that. And this just equals to e to the negative pi over 5 and minus 1 times it by e to the negative pi over 5. So in other words, we can multiply this inside this that bracket right there, and then what we're gonna get is, the summation up to infinity from n equals 1 of 250 pi over 101 times it by, and multiply that inside. So e to the negative pi times e to the pi over 5. So there's pi over 5. Those just add up and those go to 0. They cancel. So we're just left with 1. And then minus e to the negative pi over 5. Like that. And then times it by e to the negative pi over 5 and minus 1. Like that. Yeah, so in other words, what we have is this is our a. So that's our a. And then this is our r, e to the negative pi over 5. And that is our r. Let's put this arrow here. And that's our r. And yeah, so note our r equals to, our r equals to e to the negative pi over 5. And then this is the same thing as writing e to the pi over 5. And this is less than 1, because this e number is bigger than 1. So then this means that, this is going to be converges. Yeah, so the geometric series converges. And yeah, so this is less than 1. And again, note here, let's put a note, or recall. Let's put a note. Note e to the x is greater than 1 for x is greater than 0, because if you recall the graph for e to the x, if this is x, this is y, or e to the x. Yeah, let's put this as y, and this is at 1. E to the 0 is 1, and as the number as you go negative, you're going to be that's going to be dividing by a large number, and that goes downwards there, and this goes up like that. This is y equals e to the x, and it's exponential curve like that. So this is greater than it there. So note, it's yeah. So put that here. Yeah. So hence 1 divided by a number greater than 1 is gonna be less than 1. Yeah. So thus, yeah. So go over here. So thus, the volume v is just going to be equal to the geometric series, just a over 1 minus r. And then a, we know, is equal to, a is equal to 250 pi over 101. So this whole thing, then times by 1 minus e to the negative pi. 1 minus e to the negative pi over 5. Divided by, and then yes, divide this all by 1 minus r. And r is also equal e to the negative pi over 5. And this is going to be e to the negative pi over 5. So in other words, the top and bottom cancel. Yeah, so then this whole thing cancels with this. So we're just left with equals 250 pi over 101, exactly as our first solution. So yes, that's pretty fascinating stuff. Alright, so we finally finished problem 13, and now let's continue further to problem 14, and this one states, if p is greater than 1, evaluate the expression 1 plus 2 over p plus 1 over 3p plus 1 over 4p plus ... Put another dot here. Oops. And then all divided by 1 minus 2 to the power p, 1 plus, and then plus 1 divided by 3p, minus 1 divided by 4 to the power p, and then plus, minus, etc. So notice how the even numbers right here, so this one, even numbers here have a negative, the odd have a positive, the even have a negative, and so on the denominator. Alright, so now let's take a look at the solution. So first notice that both series are absolutely convergent when you make these all positive, all the terms. And again, this is because these are p series with p is greater than 1, because we're given that p is greater than 1. So this p series is p greater than 1. So they're all absolutely convergent and therefore also convergent. And also recall from an earlier video on absolute convergence. So a series summation of an is called absolutely convergent if the series of absolute values, this summation of the absolute values of it is convergent. So see these negatives, we make these all positive instead. If a series, the summation of an is absolutely convergent, then it is convergent again from an earlier video. So therefore this is convergent and this is also convergent as well. So you're dividing a convergent series by another convergent series. So now let's give, right here, let's give, or actually, just let the given expression be called x. Then what we end up having is, so let's write x equals to, well, the top is 1 over 1, 2p plus 1 over 3p. Let's take a look over here. Yes, 3p, 4p, and so on, plus 1 over 4p, and zoom in a bit. Alright, so that's what we have. Divide this by, and then this goes again, plus dot dot dot. And now notice the pattern for the other ones. This is x equals 2. And then the bottom one is 1 minus 2p. So all the evens are negative and all the positives are, all the odds are positive. So 1 minus 4p, and then plus minus dot dot dot. And now we're going to do some next level manipulation right here. So we want this 2p, this negative side here, on this part here. So what we can do is, we'll write this as 1 plus, and I'm going to multiply, well, we could just have, multiply this by 2. Yeah, so I'll just put a 2 over 2p, subtract that by 1 over 2p, so that we're not changing anything. So 2 minus 1 is just 1. Alright, so we have this, and then the next one, well, it matches up with the bottom, so we don't need to do anything special there. So 1 over 3p. So, and then we'll do this again for the 4p, and that's because there's a negative 4p at the bottom. So we want to have this negative here. So we have a negative here, matches here. And we'll do that again, it's for all the even powers there. So 1 over, so then we'll do this here, 2 over 4p minus 1 over 4p, and this again, this just equals to, when you subtract them, just equals to 1 over 4p. So we're not changing anything. So it's still this, and then it keeps going on and on, plus dot dot dot, and then we'll do the same for all the even powers. For 6, we'll have 2 over 6p minus 1 over 6p, and so on. And then all of this divided by just the denominator, 1 over 2p plus 1 over 3p minus 1 over, plus 1 over, so no, never mind, this is minus 1 over 4p, and so on, plus, minus, dot, dot, dot. And now what we'll notice is that, notice in every single bracket we have this negative power. There's negative 1 over 2p, then we have a negative 1 over 4p, and so on. So we'll take all of those separately. So what we'll do is write that in a bracket. So move that over, so move these all out. So we'll have a 1 minus 1 over 2p, and then this will be minus 1 over 4p. 1 over 4p. Well, actually, yeah, but we'll include the odd powers as well. So then we'll include this as well inside this bracket. So plus 1 over 3p minus that. And this keeps going on and on for all of the, for all the terms. 1 over. So we'll take all the positive odd terms, and then take all the negative even terms inside there, and then this keeps going on, plus, minus, dot, 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 and then put a bracket, and then we'll take all these separate, all of the even powers that have a 2 there separate. So then that means we will have, and then factor out the 2, plus 2, and then 1 over 2p plus, it's 1 over 2p, plus 1 over 4p, and then we'll do the same for the 6, and so on. 1 over 6p, and then it keeps going on, plus dot, 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 and then put a close bracket. And then we will divide all of this by, again, the bottom, and the bottom is just as is, 1 over 2p, plus 1 over 3p, minus 1 over 4p, like that. And then it keeps going on, plus, minus, dot, dot, dot. And now what we'll do is, well, if we look at this one, put in a bracket so it matches this whole thing, well, it doesn't necessarily care. You could divide it in, it cancels, but it just becomes 1. So if we divide this all in, this becomes 1. This whole thing just cancels out with each other and becomes 1. Plus, so we're just dividing this into both, and then plus, and what I'm going to do now, well, actually, before we simplify further, I'm just going to put that regular term inside. So this is 1 plus, and I'll put the 1 in the middle like this, 1, and then plus, and put the equal sign here, 1 plus, and put this whole thing like this, 2, 1 over 2p, plus 1 over 4p, plus 1 over 6p, plus dot, 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 and like that, and then over just the denominator, so 1 minus 1 over 2p, plus 1 over 3p, minus 1 over 4p, plus minus dot, dot, dot. Alright, so now that we have this, and what I'm going to do on the top, I'm going to multiply this by 2p over 2p, to the power of p, So 2 to the power of p, so just so we have a whole bunch of cancellations. We have this 2p there, and we want to make this, not just this even powers, but also make it pretty much the same as this, has all the powers, even and odd, so even, odd, etc. Because this is all even, so multiply the top by 2p, and then divide it by 2p. And also notice here, this is power 2 to the 1, so we could subtract that over to this side here. And then what we're going to get is, so let's write this out, this equals to 1 plus, and put a giant, like that, line, and then the top's going to be 1 over 2p minus, minus 1, and then that's again this 2 to the power 1 divided by 2 to the power p, and then multiply this all out. What we get is when we multiply this 2p over here, this becomes a 1, so 2p over 2p. The next one's going to be, well, this is the same as writing 2p times 2p to the power p, and then so we'll have one of those cancel. This becomes 1 over 2p. Same with this one here, is just 2 times 3, so one of those cancels, and this becomes 1 over 3p, and so on. This keeps going on and on. The next one's going to be 1 over 4p plus dot, dot, dot. And here, let's move it down here, and I'll just put a note for completeness. So when we have this 1 over 3p, that's from the 2p over, this is over 6p. This just equals to, again, you could just factor out the p there. So this just becomes 2 over 6p. It just equals to 1 over 3p, like that. So so we can just factor out. So every single one's going to be dividing it out. So you're dividing every single one of these by 2, and it becomes like that. So we have every single term, and notice the bottom is our 1 minus, I'll write it over here, 1 minus 2p plus 1 over 3p minus 1 over 4p plus minus dot, dot, dot. So in other words, this whole setup here, put a bracket here, so from here to here, ignoring the first part, this is equal to x. This is just our starting point. Remember, this is just our starting point. 1 plus every single one of these positive, this is power p, and then it's 1 minus plus 1 minus plus, etc. So we have 1 plus all the terms, and then 1 minus plus, 1 minus plus, etc. So in other words, this whole thing equals to, and I'll bring the x down. So remember this whole term, x equals to 1 plus, and then we'll have this 1 divided by, or just better yet, I'll just put this as x, divide this by 2p minus 1, like that. And then we can put this on the top by making the power a negative. So this equals to 1 plus 2, 1 minus p. So we just make it negative. So the negative 1 becomes positive. The p becomes negative there. And then x, like that. So that is fascinating. And since we are solving for x, we could, well, move this over to... Yeah, so if we just move this whole thing actually just to the other side, what we end up having is, x is equal to, actually x minus 2, 1 over p times by x equals to 1. And then what we'll do is we'll factor out the, you factor out x out of there, so x 1 minus 2, 1 over p equals to 1, divide this out. We get, finally, x is equal to 1 over 1 minus 2, 1 minus p, which is quite fascinating. Yeah, and this looks similar to a geometric sum. All right, yeah, so that is the expression, or that giant division right here. So this series over this series equals to 1 divided by 1 minus 2 to the power of 1 minus p, which is pretty amazing. All right, so now let's take a look at problem 15. So suppose that circles of equal diameter are packed tightly in n rows inside an equilateral triangle, and the figure illustrates the case n equals to 4. So there's 4 rows, 1, 2, 3, 4. Notice how they get bigger and bigger. You start off with 1, 2, 3. So if you have the fifth one, will be at 6. Actually, yeah, it will be 5. Yeah, I mean, we'll have 5 balls on the fifth one, 6 and 6 ones, etc. So notice that's the perfect triangle set up there. And you can see the equilateral triangle because there's 4 on this side, 4 on this side, 4 on this side. So if A is the area, so here, this is case n equals 4. So if A is the area of the triangle and AN is the total area occupied by the n rows of circles, show that the limit as n approaches infinity of an divided by a equals to pi over 2 times square root of 3. So again, an is a total area. A is the area of the triangle. So an is a total area by the n circles. So this is an. So all that together is an. This, yes. And then the total one of the triangle is just a. All right. Alright, so now let's take a look at the solution. So if L is the length of a side of the equilateral triangle, then the area is, and again, recall equilateral triangle, let's just write it out for completeness. This becomes like this, and let's put this better. Alright, so we have a triangle, side lengths are L, and we have this height here. This height is H, and then the base is B equals to L. So it's all the same. And over here, this from here to here is L over 2. So again, recall Pythagoras. We have L squared equals to H squared plus L over 2 squared, which equals 2H squared plus L squared over 4. And then move this over to the other side, and then all the way to the end. And then square root, we'll get H equals to plus or minus square root L squared minus L squared over 4. Again, this is 4 over 4 times 4 over 4. This just becomes, again, only take the positive because we're dealing with this, but I always put that just because technically it is plus or minus on the square root. So what we'll have is square root L squared, if this 4 minus 1 is 3. So we'll have 3L squared over 4, like that, over 4. And then square everything in there. This becomes square root 3 over, and then this is a 4 there. Yeah, square root 3 over 2 is 4, square root 4 is 2. And let's put this over the whole thing. Then L squared, square root of that is L. Like that. Alright, so this is our H. And then recall the area is just equal to base times height divided by 2. So base is equal to L. So we'll have L times it by h square root 3 over 2 times L, and then divide this all by 2, and this equals 2. Well, we'll have a L, this is going to be square root 3 by itself, and then 2 into 2 becomes 4. Then we have an L squared like this. Alright, so this is a. I'll just put this equals to A like this. And since we're asked to find the ratio AN over A, well, let's just write L squared as A. So this is and L squared equals to 4 over square root 3. So move everything over to the other side, move it there, etc. So we'll get a 4 over square root 3A. So that is what L squared is equal to. So we have that A as part of L squared. Alright, so now let's take a look at the circle. So let R be the radius of one of the circles. When there are n rows of circles, the figure shows that. So if you have this figure like this, so this distance from here to here is R, and then what we have is from here to here is also R, so it's all radius. So in other words, from here to here is R. And then continuing over here, this is going to be 2R now. Now we'll have it as 2R. Let's put it here, 2R, and then keep going further. There's another 2R. So that's just a diameter. And then we have an R, like that. And then this is at the center here. And now we have a point. And then we can draw a line like this. I'm going to draw it like this. So the idea is we want to get, so that's 2R there. Now we want to get this distance across here. So this distance and so on. And this one here. It's going to be the same. And notice that, well, if this is R, so this height is R, and this right here, so this equilateral triangle, so that means is this angle, this is pi over 3 or 60 degrees. So then this right here, you're dividing this in half. Again, it's all everything's symmetric. So this one has to be right here. This is pi over 6. And then we can, it's just pi over 6. So then what this means is, well, if we have pi over 6, so we recall the triangle, the equilateral triangle looks like this. So we have this. I'll put this here. So we have this. Alright, so if we have, this is all pi over 3 angle, like that. This is pi over 3. And then if we cut this in half, I'll just draw this a bigger line. Cut this like that, a thicker line. So this is going to be, and if this is pi over 6, and if this is R, so this is this part here, then this hypotenuse is 2R, because it's all the same. So this is R. So in other words, this has to be the same. So this full length is 2R. And it's all equilateral, so this is 2R, like that. So in other words, if this right here is 2R. And same for here, this is 2R, like that. And thus we can calculate this right here. This is our height, or I'll call it lowercase a, so that's our A. And we could just solve that, and again, A is equal to plus or minus square root, and we're just going to take the plus. Again, I always do the plus minus just for completeness. So then hypotenuse squared minus the base right there, or the adjacent. Well, it depends on where the angle, just that side R. So I'm going to move this better like that, this like this, and this like that. So just minus R squared, like that. So A is equal to, A is equal to, in other words, 4R squared minus R squared, which equals 2, this just equals to 4, so square root 3 actually, so it's going to be, well, before that, but this becomes 3R squared, and this equals 2 square root 3R, like that. So that is our A. So we know that full length is there. So now we can solve this. This A is equal to square root 3 over R. So we'll square root 3 by itself, and then times it by R. And similarly on this side here, square root 3 times by R, like that. So then the full length of the side in terms of r, yeah, so in terms of r, so this whole height, or this whole length is L. So we have L. Alright, so we have here, so this is for n equals to 4. So what we have is, thus, I'll just put first L4 is equal to for the n, for n is 4. I'll just put that instead here. So 4, for n equals to 4, we have L is equal to, square root 3, square root 3 times r plus, and then what we have is an r plus 2r, r plus 2r, plus 2r times, I'll just put this as, plus 2 times 2r, and then plus r, or I'll just put this all together actually. So plus r, 2r plus 2r plus r, and then plus the last one, a, is square root 3 over square root 3r, like that. And in fact, so the only key part that we need to worry about is this part, or just to analyze further. So this part here could be written as 4 minus 2r, which equals to times it by 2r. 4 minus 2 times 2r, which equals to, in this case, 2 times 2r, like that, which equals to 4r. So that's for n equals to 4. So for, just for general, for n, in general, like this, so for Rn in general, this is going to equal, L equals to, well, we have the square root 3 times r, and then these just add up. You could just add those up. It doesn't change anything there. But just for completeness, I'm going to write that. So we're going to have this segment. So square root 3r plus, then we always have this additional r before we have all these two r's. Plus r, and then plus here, this is 4 minus 2. In other words, that was n is 4. And this keeps going on. And then, so the next one for n equals to 5, we're going to have 3 of these. So in other words, we'll have a 5 minus 2. So what we'll have is, this could be as, this will be n minus 2. So for n is 5, we'll get 5 minus 2 is equals 3. So we'll have 3 of these big circles inside there for n equals 5. So n minus 2 times it by 2r. So plus r, and then the last segment is this plus r, and then times square root 3 over r. Like that. And now, so that's 2r. So now we can just combine all the like terms. So this becomes equals to 2 square root 3r plus 2r, and then plus, well, this one we can just multiply this inside there, and here. So this becomes plus 2 nr, and then minus 4r. Like that. So that's what we have. And now what we'll do is we'll add these two together, and that becomes, well, minus 2r, and also factor out the r. So r times it by 2 square root 3, and that becomes right here. We'll first put the 2nr, or actually put this first. I'll put this one first, and then this will be 2. We're factoring out 2n. And then we're going to factor out the r. So plus, and the next one is 2 square root 3. And then this one here, combining these two, these would be negative 2r. We factor out the r. So negative r. Negative 2, like that. And now this equals 2, factor out the 2 now. So 2r times by n plus square root 3 minus 1. Like that. And now this whole thing equals to L. Remember, this whole thing, this was just our length L. So now if we solve for this R, so we'll have to divide this out, move it over, and the 2 move it over. So what we get is R is equal to, and this will be L, so L over 2 times n plus square root 3 minus 1, like that. Alright, so thus we have here, and just added the word thus, we have r equals to all this. All right, L equals to L divided by 2 times n plus square root 3 minus 1. So that's what we have for R. All right, now that we have the radius of each circle in terms of L, we could solve the area for it, but first let's count the number of circles. So the number of circles is, I'll put this number equals 2. Well, for n equals to 4, we have 1 plus 2 plus 3 plus 4. So yeah, we have, well, 1 plus 2 plus 3 plus 4. And again, for n amount, we're going to go plus dot 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 all the way to n. And this just equals to, well, the sum of integers. This is the sum from I equals 1 up to n of I. So sum of positive integers. This just equals to, well, n times n plus 1 as per my earlier video. So that's the number of circles. And here for n equals 4, we'll have 4 times 5 divided by 2. Well, that'll just be 10. And we can count that here. So this can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And yes. And yeah, so here, recall this formula. So recall that the above formula is for the sum of positive integers. Let's write positive integers, which I went over in my earlier video. So here's a link to my earlier video. So a summation from n equals 1 to n, from I equals 1 up to n of I equals 1 plus 2 plus 3 plus, etc. all the way to n equals to n times n plus 1 divided by 2. All right, so then we can calculate the total area. So thus, the total area of the circles is, and we'll call this AN. So this is going to be A sub n. This equals to the total number of circles, n times n plus 1, over 2 times it by pi r squared. So area of a circle, pi r squared. And this equals to, well, we're going to write this in terms of L. Remember, we want the ratio of AN over n. So this is what we want, AN over AN over A. And we know that L squared is in terms of A there. And we can write this whole formula AN in terms of L because we know R is in terms of L there. So this equals to, I'll move the pi in front, or we'll move it after actually, just to show where the R fits in. So over 2 times pi, and then times it by this formula right here, L over 2, and then n times times n plus square root 3 minus 1. So over L, and then we have a 2, but then we're going to be squaring it. So this, but then since we're squaring it, we'll put a square on every single one, and 2 squared is going to be 4. So this becomes 4 times by n plus square root 3 minus 1, and then squared. And now before going any further, well, notice there's an L squared there. So we have this L squared, and well, we know that L squared, we wrote that earlier in terms of A. So L squared equals 4 over square root 3 times A. And again, we were asked to find the limit as n approaches infinity of AN over A. So we could replace this L with A. Yeah, so this will be 4 times square root 3 times A. So this equals 2, and let's put this all together. Well, let's keep it as is, n plus 1 over n, over 2 times by pi times this by, and this was 4 over square root 3. This is our, let's see if I remember that. Again, so 4 over square root 3 times A, like that. Yeah, times A. And that is going to be, again, times this all by, times by 1 over 4. And again, this is our L. I'll just circle that so that they line up. And then n square root 3 minus 1 all squared. And I'll extend this. And now we'll do some cancellation. So this 4 cancels with this. And we're left with, and let's just do some simplification. So this equals 2. We'll put the pi in front, and we'll multiply this inside. And then we'll do that in a bit. So we'll have pi right here. So pi, and actually before I even do that, I'm going to take this A, I'm going to divide this out so that we get AN, just make it simpler. So AN over A is equal to, and then there's the pi over 2 square root 3. So we got rid of this. So we have this, this, and this. The next one is this multiplies inside, and this 4 is gone. And then this becomes like this. Make the n's by themselves. So n squared plus n over n plus square root 3 minus 1 over 2. And now since we're going to take the limit, we want to multiply top and bottom by n, because otherwise we'll have an infinity over infinity. So multiply top and bottom by n, by 1 over n squared, like this, divided by 1 over n squared. So then that means we can put this inside this squared square power, because the same, that'll be the same power. And then this equals to, let's put this all over here, equals to pi over 2 square root 3. At 2 square root 3 times it by, this will be n. Actually, no, n squared divided by n cancels. So we'll have 1 plus and then 1 over n. Because this will be cancel out with this. And we're left with, at the bottom, it's going to be this 1. Because then when you divide this out, we'll just divide by n inside this square. Plus square root 3 minus 1 over n, like that. Let's put it like that. All right, and now we can take the limit. Yeah, so we can take the limit, so thus the limit as n approaches infinity of the ratio an over a, and just move this a bit to the bottom. So thus, move this here, equals to the limit as n approaches infinity, or actually instead of the limit in front, put the pi 2 over square root 3, the constant, out of the limit, so n approaches infinity of 1 plus 1 over n over, right here, 1 plus square root 3 over 1, and this is all squared, over n squared, like that. And now as you plug in infinity, we'll get this 1 over infinity goes to 0. Similarly over here, this becomes 1 over infinity goes to 0. So it's, it goes to 0, like that. So in other words, this whole thing is equal to pi divided by square root, 2 over 3 times by 1, 1 plus 0. 1 plus 0 over 1 plus 0 squared. So in other words, this whole thing just goes to 0 right there. So it's multiplied like that. And this all just becomes 1 over 1. That becomes just 1 over 1 there. So 1 plus 0 is just 1. So in other words, this all just cancels. It goes to 1. So what we get is limit as n approaches infinity of an over a equals to pi over 2 square root 3. And this is exactly what we were asked to solve. And we can go scroll up to see our question. And so it says show that limit as n approaches infinity of an over a equals to pi divided by 2 square root 3. And that's exactly what we just showed. All right, so we have just solved problem 15. So now let's take a look at the next problem, and that's problem 16. So a sequence an is defined recursively, or just going, just feeding in the previous result and so on, and keep going and on, by the equations a0, a sub 0 equals a1 equals 1, and the second one, n times n minus 1 times an equals to n minus 1 times n minus 2 times a sub n minus 1 minus n minus 3 times an of, n minus 2. So that a sub n minus 2. And then we're asked to find the sum of the series an, in other words, this right here, and sum it up to infinity, or sum up as n goes to infinity. All right, so now let's take a look at the solution. So given the above, we can calculate the next few terms of the sequence. Well, first of all, let's write this out. So given that we know that a0 equals a1 equals 1, and so those are both 1, and then an, so an is equal to, well, we got to divide this out. So divide it out over there. And what we get is n minus 1 times by n minus 2 times a n minus 1 minus n minus 3, a n minus 2. All divide this by n, put this in the center, n minus 1. Yeah, so solving for the next one, a2. So we have a2 is equal to, because we know a0 is 1, a1 is 1, so a2 is equal to, yeah, let's plug in the numbers. So n minus 1, so 2 minus 1 is 1, times it by 2 minus 2 is 0, times it by a2 minus 1 is 1, a1. Minus, and then we have n is 2, so then we'll have a negative 1. Yeah, so this will be 3. So we'll have a negative 1 times it by a0, n minus 2 is 0. Like that, all divide this by n is 2 times by n minus 1 is 1. Like that, so just add 2 times 1. Like this. So in other words, this becomes, well, this a0, this one right here is a 0. So 0 minus a0 is 1. So we'll have, and this negative times negative 1 is positive. So it just becomes plus 1 over 2 times 1 is just 2. So in other words, this equals to 1 over 2. So that's the first one there. And let's look at the next one. So the next one is going to be a3. So a3 is equal to, and then put the 3 inside. 3 minus 1 is 2. 2 times, and then 3 minus 2 is 1. Times it by, and then we have over here a 2, then minus 3 minus 3 is 0, times it by a 1. So this is 3 minus 2. And then divide this out by 3 times n minus 1 is 2, so 3 minus 1 is 2. So what we have here, this goes to 0, a2 is 1/2, so this equals to 2 times 1/2 over 3 times 2. So this cancels, and this becomes just 1 over 6, like this. So this is 1 over 6, like that. And now the next one, let's do one more. You can see the pattern that's looking like it's arising. So there's a 2 there, 1 over 2, 1 over 6. In other words, this is a 3 times 2, this is a 2 times 1. And yeah, so the next one is a 4. This equals 2. So n minus 1 is 3, times it by n minus 2 is 2, times it by, this is going to be a 3. You can just see the pattern. This is minus 1, so 4 minus 1 is 3. Minus, and then this is 4 minus 3 is 1. Minus 1 like that. I'll just put a 1 without the bracket. Minus 1, times it by 4 minus 2 is going to be a 2, like this. All divided by 4 times 3. 4 times 3, so this top part equals 2. There's a 3 times 2 there, and there's a 1 over 6. So this becomes 6. Oh, yeah, 6 times a3 is 1 over 6. Like that. Yeah, that's like that. But then this a2 is 1/2, so minus 1 times 1/2 is just 1/2. And this becomes, again, 4 times 3 is equal to 12. So what we get is, the next setup is, this one is 1 minus 1/2. That's just 1/2. So in other words, this is 1/2 divided by 12, which equals to 1 over 24. So this just equals to 1 over 24. Yeah, so, and now we can just box this in like that. Yeah, box that in. And again, notice that there's a 2 there. So in other words, there's 12. This is the same as writing 1 over 4 times 3 times 2. Yeah, so in other words, that's factorial there. So 1 over 4 factorial. And this one right here is 1 over 3 factorial. This is 1 over 2 factorial. And then even these top ones here, this is the same as writing 1 over 0 factorial. This equals, by definition, just the same as 1 over factorial, which both equal to 1 over 1, which equals to 1. So by definition, yeah, 1 factorial is just 1, and then 0 by definition is also given as 1. So those are all factorials. So it seems, so thus, I'll just say thus, it seems, key is seems because we haven't proved it, we just noticed a pattern, seems that, yeah, that a sub n is equal to 1 over n factorial. Yeah, because you can have this 4, then there's a 4 factorial, 3 factorial, 2 factorial, like that. So it seems this. Alright, so now continuing further, so now to confirm this pattern that an actually is equal to 1 over n factorial, we can use induction or mathematical induction. So recall from an earlier video, mathematical induction, in proving statements that involve a positive integer n, it is frequently helpful to use the following principles. The principle of mathematical induction: let Sn be a statement about the positive integer n, and suppose that S1 is true and Sk plus 1 is true whenever Sk is true. Yeah, so basically saying, suppose we have the first case is true, and then Sk, and then also suppose that whenever this is true, the next one is also true. Then Sn is true for all positive integers n. And this is reasonable because since S1 is true, it follows from condition 2 that S2, yeah, with k equals 1, that S2 is true. Then using condition 2 with k equals 2, we see that S3 is true. And again, using the condition this time with k equals 3, we have S4 is true, and so on. This procedure can be followed indefinitely, so it's true for all n, for all positive integers n. So the first step is already done. We already know that this equals to 1 over n factorial, so a0 and a1. So that's already done. So we assume that ak and ak minus 1 are true. So assume are true. Yes, the key part is we're assuming it's true, and then we'll solve for ak plus 1. And if that's true, then by induction it is all true. So assume that ak is equal to 1 over k factorial, and ak minus 1 is equal to 1 over k minus 1 factorial. Yeah, then, now we'll see if it's true for ak plus 1. Then ak plus 1 is equal to, and let's plug it into our recursive formula. That's, again, this whole setup divided by n. Divided by n times n minus 1, or is this right here? So n minus 1, n minus 2, and then there's an n minus 3 there. This is minus 1, 2. Alright, so n minus 1, so we'll have it as bracket k plus 1 minus 1 times it by k plus 1 minus 2, and this is going to be and let's see that again. This is going to be n minus 1. So k plus 1 minus 1, and then subtract this by, the next one is n minus 3, and then n minus 2 there. So n minus 3, so we get a k plus 1 minus 3 times by a, and then the next one is n minus 2. So k plus 1 minus 2, all divide this by n, which is k plus 1, times it by, and then k plus 1 minus 1. So n minus 1. K plus 1 minus 1, like that. Alright, so now we get to simplify this further. So this equals to, well, the top part is going to be k plus 1 minus 1, that's just k, times it by, so that's k. The next one, k plus 1 minus 2, that becomes k minus 1. And then this one right here, ak plus 1 minus 1, that's just ak. And then this minus right here, k plus 1 minus 3, this becomes k minus 2. Or that this becomes k minus 2 times it by a k plus 1 minus 2. That becomes a k minus 1 there. And then this part right here, just put this better bracket. K plus 1 times it by k. And now if we simplify this even further, well, actually, before we simplify that, we'll put this ak and inside there. So we know ak is this, and ak minus 1 is this. So we can put those inside here and here. So this equals to k times k minus 1, put the equal sign somewhere here, equals, this one here, k times k minus 1 divided by k factorial. And then this is going to be subtracted by k minus 2. Divide this by k minus 1 factorial. And this is all divide this by k plus 1 times by k. And now we could simplify the factorial. We can expand that actually, so we can do some cancellations. So we have k, I'll put this equal sign somewhere here, k times k minus 1 over, this is just k, times it by k minus 1, times it by k minus 2 factorial. Actually, instead of doing that, let's keep this here. And yeah, so notice this k minus 1 factorial will have the same common denominator. Yeah, because notice that this cancels with this. So then we'll just have it as a factorial there. So we'll not cancel the top part yet. Alright, so subtract this by k minus 2 over k minus 1 factorial. So just keep that in there. And again, all divide this by k plus 1 times by k. And now we could do some cancellations. Oh well, because before that we look at this right here, we could just add these top because those are the same common denominator. So this equals 2. Put it like this. Yeah, let's put it like this. Equals 2. And yeah, so it equals to that. I'm also going to bring this k minus 1 downwards. Because yeah, we don't need to deal with that double fraction there. So put the k minus 1 here. Or actually, before that, I'm just going to put this here at the bottom. K plus 1 times by k. Yeah, times by k minus 1 factorial. And then now we're going to have this and this. Subtract them. So we're going to go k minus 1 minus k. And then put the negative inside. That becomes plus 2. Like that. So in other words, this cancels with this. And yeah, we don't need this giant arrow. Yeah, that cancels with that, and then this 2 minus 1 is just 1. So I'm going to move this over here, and this equals to, yeah, just 1. This equals to 1, and then this right here, this is just k factorial. K plus 1 times k minus 1 factorial. This is just equal to k plus 1 factorial. So in other words, this whole thing equals to k plus 1 factorial. And this is our ak plus 1 equals ak plus 1. So therefore we've proven the induction. Alright, so thus the induction is complete, and this means that our series is equal to E as per our earlier Maclaurin series table, with e to the x equals to e to the 1. And let's just scroll to the table. Alright, so here is the table. It's teleported over there. So remember that e to the x equals 2x to the power of n divided by n factorial. But if x is 1, then it just becomes 1 over n factorial. Then all these becomes 1, 1, 1, etc. And radius of convergence is r equals infinity, and so on. Yes, in other words, it just equals to e. So yes, let's go and yeah, so basically we have yeah, e to the x equals to e to the 1, and that is just the same setup there. So thus we have summation of from n equals 0 if an equals to the summation 1 over n up to infinity from e equals 0. In other words, this just equals e to the 1, or just e, like that, which is quite fascinating. Alright, so now that we're done problem 16, let's take a look at problem 17. And this one states, taking the value of x to the power of x is 0, at 0 to be 1, in other words, 0 equals 1, and integrating a series term by term, show that we'll get the integral from 0 to x of x to the power of x dx is equal to summation from n equals 1 to infinity of negative 1 to the power of n minus 1 divided by n to the power of n. Alright, so let's take a look at the solution now. So as in my earlier video on representing functions as power series, we will have to integrate the function x to the power of x by integrating series. We can rewrite, I think it probably just same thing as writing it like that, rewrite x to the power of x by using the Maclaurin series for e to the x from the earlier table above, again, which we just went over there, but I'm going to go scroll up to it just in case someone uses the timestamp to problem 17 right away. So let's go all the way up. Alright, so teleporting here, we have e to the x equals to the summation from n equals 0 to infinity of xn over n factorial. In other words, we'll get a 1 plus x divided by 1 factorial plus x squared divided by 2 factorial, and so on, where r is equal to infinity. Alright, so teleporting back here, we have e to the x is equal to the summation up to infinity from n equals to 0 of xn over n factorial, which this equals to, well, 1 plus x squared divided by 2 factorial, etc., plus dot dot dot. It keeps going on and on. Or I'll just add the other 3 just so it looks like it. 3 factorial plus dot dot dot, and so on. And then I'm going to put r equals to infinity. Alright, so now that we have this, and what we can do is manipulate this x to the x. So the reason we chose this is because it has that power to the power of x. This one is just x to the power of x. So what we'll do is we could rewrite this as e to the ln x. If you recall the natural log rules, those are just the same. That just becomes x. I'm going to multiply this by, then this is to the power of x, where this inside here is just equal to x. And then we could put this x inside, so we get e to the x times ln x, so like that. So we have that, and I'm just going to recap right here. Let's put it here, actually. Recall that e to the y, if e to y is equal to x, then by definition we have ln x equals to y. Yeah, so in other words, if you plug in the y back in here, or I'll just put a recall bubble like this. And then if you put this y back in there, we have e to the ln y equals to x. No, I mean e to the y is e to the ln x. So e to the ln x, not e to the ln y. E to the ln x equals to x, like that. And that is exactly the same thing we have here. So e to the ln x, just x. In this case, e to the ln x, just x. So what we get, is thus, we'll put it like this, thus, or without even thus, I'll just put it like this. Thus we have e to the x, or actually, I'll just put thus. Thus e to the x, or just put the thus like that, and then, so just remove the arrow. Thus, x to the power of x equals to e to the power of ln x. And then we could just throw that inside here. So replace x with x to the ln x. So this equals to the summation up to infinity from n equals 0 of x times ln x. And then this is going to be to the power of n over n factorial. And now if we just multiply that inside, we'll get a summation up to infinity, n equals 0 up to xn. So we'll have x to the power of n times by ln x, that'll be to the power of n, ln x power of n over n factorial. So that is what we have. And now continuing further, so as with power series, and in fact this you could write this as a power series because you have the power there. And yes, this whole thing's as a power there. Yeah, you could rewrite this as a power series. In fact, this e to the x was derived from, a Maclaurin series, which is a type of a Taylor series, and that is a power series. So anyways, we can integrate this series term by term. In other words, we could take the integral from 0 to 1 of x to the x dx is equal to then the integral of the inside. Summation from n equals to 0 of every single term. In other words, integral from 0 to 1 of xn ln xn over n factorial. Like this, and then dx. Like that. So integral of every single term. And what I'm going to do now is I'm going to remove this n factorial out of the integral because there's no x inside, because we're integrating in terms of x. So this goes to infinity, n equals to 0, n factorial, 1 over n factorial, times it by an integral of x to the n ln x to the n dx, integral from 0 to 1. Alright, so now that we have this summation and this giant integral there, or this giant summation with this integral inside, what we can do is we can apply the integration by parts and take a look at this segment separately right here, as per my earlier video. And if you recall integration by parts, how it's derived, basically if you have the derivative of fx times g of x, it becomes this fx g prime of x plus g prime plus g of x times f prime of x. Then you integrate that just becomes the integral of this is equal to, of this whole thing is just equal to f of x times g of x. And then integrate inside and then rearrange for this one here, or for this, move this over to the other side, we get this setup over here. And then if you replace this with u and dv, so this could be dv, and this is u, what we get is a uv, and then integral right here of, this is v du, like that. So we can have this set up here. So u dv equals to uv minus v du. And then we have this right here. So there's a product right there. So we could use integration by parts there and to solve this integral and simplify it further. All right. So thus, let's take a look here. So let's look at this integral. So I'm going to put right here, integral from 0 to 1 of x to the n times it by ln x to the n dx. And what I'm going to do is, well, I'm going to look at the one that I want to take the derivative of is this, because this involves a ln x, and we know the derivative of ln x is 1 over x, and the integral is not that simple. So I'm going to actually rearrange this just so it looks a bit better. I'm going to put this in front, ln x n times x n dx. And I'm going to choose this to be u and this to be dv. So it matches u and dv like that. So what we'll do is let u equals to ln x to the power of n. Then this means that du is equal to, well, n, and then ln x, n minus 1, and then times it by the chain rule derivative of ln x is just, it's just 1 over x. So we'll just divide this by x. This whole thing, just divide this by x, like that. And so we let that end, we let dv equals to x and dx, so that the integral of it becomes, well, integral of this just becomes, right here, let's put an arrow. V equals to, integral there is going to be x n. Yeah, actually, instead of just going that, let's go more completeness. I'll just write integral of dv like that, just to show that off. All right, and then the equals to v equals to, and then integral of this is just x. Well, we have to put the, actually, we'll go above. So the integral of xn is xn plus 1 divided by n plus 1. And then it's just the antiderivative. So if you take the derivative, n plus 1 cancels, and subtract 1, you get x to the n. And as always, you're always going to have a constant. So I'm going to have a constant c, and let c equals 0 here. Yeah, let c equals 0, even if it's someone else, it's going to cancel out when we're doing this definite integral there. Yeah, so thus we have, well, v equals to xn plus 1 over n plus 1, like that. Yeah, thus, putting this all together, we have, thus the integral from 0 to 1 of ln x n to the power of n, so that's just right here, that's u, times it by x to the n dx is equal to, and here I'm going to take a limit, and this is because, well, ln of 0, you can't just plug in ln of 0, that is actually goes to negative infinity. So we're going to have to put a variable as t approaches 0. I'm going to write from the right side. So this plus means approaches 0. So the plus means approaches from the right side. Approaches from right side, from the positive side. But in this case, well, it's positive because it's 0, but from right side, like that. And this is and now this is going to be of the integral t, so replacing this 0 with a t up to 1 ln x to the power of n x n dx. And again, the reason for this is, well, just recall the function of ln x. So recall that ln x looks like this. This is x, this is y, ln x looks like that. So this is our ln x, and at this point it's at 0 there, but then as here it goes to, right here is approaching negative infinity. So yeah, so this is going towards negative infinity. Let's put an arrow like this. Approaches negative infinity, so hence we're going to go from the right side. It's only defined from the right side. So 0 right. Approach it from the right side as opposed to the left. It does not exist here. It does not exist from the left side. Alright, so it's approaching 0, and it doesn't actually equal 0 there, so we'll just approach it there. Alright, so thus, let's take the limit. So thus what we have is limit as t approaches 0 from the right side of the integral t to 1 of ln x n xn dx is equal to, it's equal to uv, but in the, since we're doing the definite integral, it's going to be, well, we're going to be writing first ln t approaches 0 from the right side of u. So u is going to be, yeah, ln x, it's still ln x then. So this is u, and this is dv. So this is going to be ln x n to the power of n, that's u. And then dv, remember that one is just x to the n plus 1 over n plus 1. Like that. And yeah, this is our v. So remember that's our v over here, x to the n plus 1 divided by n plus 1, like that. And we're going to go take it up from t, evaluate it from t to 1, like that. And then what we'll do is subtract this by the limit as t approaches 0 plus, and this is going to be, yeah, another integral, so integral from t to 1 of, so t to 1 of, now it's v du, so xn plus 1 over n plus 1, this is again our v, and yeah, so let's put that, that's our v, and then du is going to be, so this is our v, put this a better straight line one more time, and then du is, that's just our times by n ln of x n minus 1 over, this is over, yeah, over x, like that. And then times it by dx there. Well, it's a dx there. And again, this is our, this whole thing, including the dx, is our, this is our du. Alright, so now let's start evaluating this. So that equals 2. So this whole thing is equal to, and let's just put the limit here. T approaches 0 from the right side, and this is going to be, yeah, this is going to be now evaluated. So put like this, and then ln 1, so put the 1 inside, and then subtract them all. So again, it's going to be ln 1 to the power of n times it by 1 to the power of n plus 1 over n plus 1, and then subtract this by ln t, and then n. This is going to be now t n plus 1 over n plus 1, like that. Alright, so then this right here, and now the next setup is, okay, so that's this right here, t, and just, let's see this. And I'm just going to ignore this limit there. I'm not going to evaluate the next one. I'm just going to go subtract this by, from 0 to 1, I'm 0 to 1. Because we're not going to evaluate it right now, we'll just write it as a general form there, or just a simplified form. And actually, before we get to that, I'm going to put this this n over n plus 1, take that out of the derivative, the integral, n plus 1, and then integral again from 0 to 1. We're not going to evaluate it, so we'll just leave it like this. When we do evaluate it, we're going to put the limit in, and so on. So then this is going to be xn, this is power of 1, so those just subtract, so that becomes xn. xn, and then ln. Yeah, this is going to be, the next one is going to be just ln, so that's xn, those cancel, and then this is going to be ln xn minus 1 dx. Alright, so now we have this, and I'm going to evaluate this part right here. So when we plug in 1 here, well, ln 1 is 0, we already know this. So this whole thing vanishes, becomes 0, because you're going to have a 0 over, 0 over any number here is always going to be 0. It's not, the thing is not approaching a limit, this actually equals to 0. Yeah, so then that vanishes to 0, and then we're going to have to subtract by here. So what I'm going to do is look at this limit right here. So we'll put that inside. So what we'll get is limit. So put it right here. So put a line like this. And I'm going to take this and then do this all separate and take this in. So we're going to get limit, or so this right here, n plus 1. I'm going to take this out, and I'm going to write this as, because it's n plus 1, because it's not part of the limit where t is approaching 0. So just take that one out, and then we're left with limit as t approaches 0 from the right side of this ln t to the power of n times by t n plus 1. Now if we take a look at this limit, so as t is approaching 0 from the right side of this one, again that goes to negative infinity. So we have a scenario of negative infinity to the power of n. Again, we're going to have an infinity and times it by this part right here, t to the n plus 1. This is approaching 0. So this is indeterminate. So we want it in the other format, either 0 over 0 or infinity over infinity, to get a, and I'm going to put plus or minus because we're not exactly sure if it's going to be plus or minus because there's power of n there. So we're not, we want it in the form of infinity over infinity or 0 over 0, so we could use L'Hopital's rule as per always. Alright, so now after trying to solve this, the solutions manual just went to the answer. They didn't actually do this, they just said they did it. It took me a while to figure out how they solved this. So first what I'm going to do is note that this right here is equal to, so this part right here is equal to t times n times it by t. Or tn times tn to the power of 1, like that, so you can add those up. I'm going to do that, so then what we could do is, this is equal to, I'll put this equal to 1 over n plus 1 times limit as t approaches 0, as t approaches 0 from the right side. And I'm going to put this t in front. I'm going to, we'll do that actually after. I'm just going to put it like this. I'm going to put this t inside this one here because it's t to the power of n. So that means we could do a t times ln t to the power of n and then times it by t. And now what this part equals to, this whole thing is equal to, I'm going to write this as 1 over n plus 1. So 1 over n plus 1 times limit as t approaches 0 from the right side. Well, in this case, it doesn't matter where you're approaching it for this regular t, but I'm going to just keep it to the right side. So t, like that, that's going to 0, times it by, times this by limit as t approaches 0 from the right side of, and I'm going to take this ln t times t, but again, this is 0 times by infinity, so what I want is I'm going to put this at the bottom. So I'm going to do that by ln t over 1 divided by t. So it's the same thing. So this still equals to this. It equals same exact thing. And then this is also to the power of n. It's all to the power of n, but again, we're taking the limit as t, so it does not matter what n is. And I'm going to do this like this, times it by, and put this all under this bracket. So all above it. So it's the power of n like that. So now, this part right here, this whole part right here, I'm going to look at this segment. This is equal with a h on top. In other words, we're doing the L'Hopital's rule here. So this part is equal to limit as t approaches 0 from the right side, and I'll just move this to the bottom. I'll move this lower so we can put an arrow. So put the arrow, or just put an arrow here. And then this whole thing becomes, and now we take the derivative of ln t. So derivative of ln t is just 1 over t, like that. And then the bottom one, that's just equal to t to power -1, and bring that negative down. And then subtract the power will be t to the -2. So in other words, the derivative is going to be t squared, like that. 1 over t squared. 1 over t squared. Yeah, so just like that. 1 over t squared is derivative of 1 over t. So then this cancels with this one. So what we get is equaling 2, and there's a negative t, bring that on top. This just equals 2. Limit as t approaches 0 from the right side is negative t, like that. And this just equals 0. So when you plug in t, it goes to 0. So in other words, this is approaching 0, so then this whole thing equals 2, 1 over n plus 1, just for completeness. Limit as t approaches 0 from the right side. Well, actually, to save time, we don't even need to do that in space. We already have this limit as t approaches 0 of this one. So then this whole thing becomes, I'll just put this whole thing becomes equals to 1 over n plus 1. And then this goes to 0. 0 times it by this right here is 0. 0 and 0 to the power of n, because to be complete, so the power of n there, and which is all just 0. So everything is just 0. So this whole thing becomes 0. So then that means this whole limit, if we scroll up, this whole thing goes to 0. And this is all approach 0. And this is 0, this is 0, so then all we're left with is just this. This is all we are left with. And just another note here, note this part right here, just because I found it interesting. So if you look at this one, I'm going to put another note. So then now we have it all 0. I'm going to put note also, or just put a note like that, because we don't have another note. So note that, limit as t approaches 0 from the right side of t times ln t. So t times ln t, or this part right here, without that n there. This just equals 2. Again, using the log rules, t goes to the power of that. So this becomes limit as t approaches 0 from the right side of ln t to the power of t. And remember how we were initially defined that x to the x, remember x to the x at 0, 0 to 0 equals 0, equals 1, equals 1. So in other words, this setup here is approaching, ln 1. It says t over t is defined as 1, so it's approaching ln 1, in other words, it's approaching 0, so this equals to 0. So could have just done it that way, but that was using that definition. I wanted to do the actual L'Hopital's rule set up there, which is all works out fine, so it's pretty amazing stuff. Alright, so let's put it all together. We have thus the limit, or the integral from 0 to 1 of ln x, like this, of n times by x n dx. That is our starting point. Let's go back above here. So this whole thing here, we're not evaluating, so we don't need to add the t. So we can just do integral from 0 to 1 ln x to the power of n times x n dx equals 2, and this whole thing vanishes. This all goes to 0. So 0 minus this setup right there, and I'll just put it for completeness, equals 0 minus, and let's just write this down. So n over n plus 1, integral from 0 to 1. So this will become n over n plus 1, integral from 0 to 1. And notice how we have an xn and then a ln x to the power of n plus n minus 1. xn ln of x, let's put a bracket actually, ln x n minus 1, then dx. Alright, so now if we repeat the integration by parts, we can see a pattern. Because notice how this one here, we go from x or ln x to the power of n, and then the n minus, then the n lowers to n minus 1. So we could do this again. So what we'll do is write integral from 0 to 1, and I'm just going to look at this part right here, and just ignore the, well actually I was going to ignore it, but I'm just going to keep that there. So let's just put it all together. So move this xn in front, as it was originally. So xn ln x to the power of n dx equals to negative, I'm going to write this negative 1 such like this. I'm going to put negative 1 to the power of 1 times by n, and then n plus 1, like that. And then times this by, this is going to be, yeah, it's a negative 1 like that. Integral from 0 up to 1 there. So yeah, so integral from 0 to 1 of xn, and then I'll put ln x n minus 1 dx. So now what we'll do is, well, I'll just let k equals to n minus 1 here. So if we let that equals to n minus 1, and then what we'll get is, we could just repeat the by parts again. We'll get integral from 0 to 1 of xn, so this part right here, ln x to the power of k, right here, dx. And now we could do by parts again, pretty much the exact same setup we did over here. So we did this, we used by parts, integral from 0 to 1, or limit as t approaches 0 from the right side of t right there. So then we'll have u is this ln x power of n, instead we'll have it to the power of k. And then what we'll get is, yeah, if that's u, then dv is the same here. So we're going to get the same x n plus 1 divided by n plus 1. And then divide this by here, multiply by this, and instead of n, this will be k. And this will be k minus 1 divided by x. And then this x n plus 1 just becomes x to the n again. And we're going to get the n plus 1 here, but instead of n, this becomes k. And then this integral is also going to go to, this, when we evaluate this uv, this also goes to 0. It's going to be the exact same thing as before. Instead of n, this will be k. That's the only difference. And k is just n minus 1, so we can manipulate it such that we'll have the exact same integral here. The exact same limit here, use L'Hopital's rule, and etc. And it just solve it. So to save time, because it's literally the exact same thing, I'm going to write equals, and again, but by parts. So we can do by parts again, so you can do that n times actually total. This becomes, I'll put a bracket here, so this becomes negative 1 again, 1, so this will be the exact same thing here, so this k, this n, becomes this right here, yeah, this becomes a k there, over the n plus 1 remains, because that n plus 1 is derived from this xn right there, or this xn right here. Yeah, if this is dv, then the integral is x n plus 1 divided by n plus 1. And then there's a cancellation, so that's why there's xn there. And then integral from 0 to 1 of xn times by ln x to the k minus 1 dx. And note here, this k minus 1, that's just, k minus 1 equals to n minus 1 minus 1 equals to n minus 2. And we could repeat this whole integral by parts, repeat until, or repeat by parts, or instead just write this, repeat n times total until, yeah, all the way until we get a scenario such we have ln x of n to the n minus n, which equals to ln x to the 0, which again, anything power of 0 is just equals to 1. So then we don't need to do by parts anymore. So when this is n when this is n minus n. So, yes, so if we combine all of these steps, and then let's take this integral right here, and then solve it such until we get rid of this ln x variable, or ln x term, so we don't need to do by parts anymore. We will get, so thus combining these steps, we get integral from 0 to 1 of xn times ln x n dx is equal to, and we'll see how many times. So we do this a total of n times. So yeah, so notice this n minus 1, this is pretty much a counter, so that's the first. This next one's going to be n minus 2, that's the second, all the way until n minus n, so we do that n times. In other words, we have this negative 1 n times, so we're going to have a negative 1 n times, and then over here is an n, and then this becomes k, which is n minus 1. So what we'll get is n times n minus 1. And notice this one, this is n minus 1. So this is 1 bigger than this one. This k is n minus 1, this is n minus 2. So when this is n minus n, this is n minus n plus 1. So that's 1 more than it. So then this is going to go times it by n minus 2 times dot 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 all the way until n minus n plus 1. And again, we could see that this k, we could just write this as our k1, and this could be our k2 if we keep doing that by brute force. Just if we just keep doing the parts by parts integration, we'll get that. So anyways, this all the way over here, so dot dot dot. And then this is divide this by, well, we have this n plus 1. So this is n plus 1 there, n plus 1 there, and we're going to have that n times. So it's n plus 1, it's n times. So I'll just put a n plus 1. Yeah, let's put this n plus 1, n times total. And then we're going to take the integral from 0 to 1 of x n times ln x n minus n dx. Where again, this part right here goes to 0, or goes to 1. That's this part right here. That's just our ln 0 right there. So I'll just put this here, ln x 0 equals 1. So that's out of there. So now we can simplify this. This is going to be negative 1 n, and now this n times n minus 1 times n minus 2 all the way to here, that's just n minus n cancels, that's just 1. That's just n factorial. Divide this by n plus 1 n. And now the integral of xn, well, we know that that's just going to be xn plus 1 over n plus 1, like that. And we're going to evaluate that from 0 to 1. So what we get is, put this here, negative 1 n times n factorial over n plus 1 to the power of n, times it by, and put the 1 inside, we'll have a 1, n plus 1 over n plus 1. Again, 1, it just makes everything 1 there. Well, actually, the top is just 1 divided by n plus 1. And then we're going to subtract, put the 0 inside. 0 to the power of n plus 1 over n plus 1. That's just 0. So I'll put it over here. This just equals to negative 1 over n plus 1 power of n times it by 1 over n plus 1 minus 0. And here I just forgot the n factorial. I'll put the n factorial there. So then this all becomes negative 1, and there's a power of n. So negative 1 power of n factorial over, so n plus 1 to power of n, this is going to be n plus 1 power of 1. So n plus 1 to power of n plus 1. Alright, so now this right here, let's put this down here. This is our integral 0 to 1 of xn ln x to the power of n dx. And now I'm just going to bold this like that, or just square it. Alright, so that was just this integral. Now let's go back to what our question was this whole time. So thus, we're going to go back to the integral we're dealing with was integral from 0 to 1 of x to the x dx. And now this was equal to, if we scroll all the way back up, and just to get sight of what we were even asked to do, which was over here. So we were asked to find that integral from 0 to 1 of x to the power of x to the power of x dx is equal to the summation from n equals 1 to infinity of negative 1 to the power of n minus 1 divided by n to the power of n. And then we showed that x to the power of x is equal to this right here, equals to e to the x ln x, which equals to this. And the integral over here. So this is the integral we got up to here so far. So integral, so the summation from n equals 0 to infinity of, so then we'll have 1 divided by n factorial times this integral, which we just finally solved. So let's put that in here. So thus, this equals to the summation. So summation up to infinity from n equals 0 of 1 over n factorial. And then times by our integral 0 to 1 of x to the n ln x to the power of n dx. So now let's plug that inside there. So this equals to, yes, plug in our answer for that. N equals 0. We have a 1 over n factorial. So we get this over here. Negative 1 n times by n factorial over n plus 1 to the power of n plus 1. All right, so we get this, and then this cancels with this. And we are left with, we are left with right here, summation erase this. I'll put this here like this. Summation from n equals to 0. Fix this again one more time. That's a very good one. Okay, so -1 n over n plus 1 to the power of n plus 1. Yeah, so notice here, so that if you plug in 0 here at n equals 0, we get 0 plus 1 to the power of 0 plus 1. And then, at the top is going to be -1 to the power of 0. So instead, start at, just to make it like our question, start at n equals 1 instead. N equals 1, so what we'll do is, we will shift this over by 1. So instead of n plus 1, we'll just go with n. So that this is 1, 1, 0, this will just be n minus 1. So I'll just erase that, actually. And instead, I'll just write here. So start at n equals 1. Or start at. Just because we don't have to, but the question had it as starting at 1, actually. So if we scroll back to the top, so we got the answer, but the question said specifically, make it show that it's from n equals 1 to infinity of -1 to the power of n minus 1, and then n to the n. So yeah, that's all we do. We just switch it up so that it's written starting from 1. So that's all they're doing, start at 1. Yeah, so when we do that, what we get is, put this in here, thus we get the integral from 0 to 1 of x to the x dx is equal to summation up to infinity from n equals 0 of -1 to the power of n minus 1. So when we start at 1, will be 1 minus 1 is 0, same as n is 0 there. And then over n to the power of n. So that when it's 1, it just becomes 1 over 1, as opposed to when it's 0, it's still going to be 1 over 1. So we're not changing anything. So we just write it like that notation, and this is exactly the same answer we were asked to find. Alright, so now we're finally done this. Let's continue to problem 18. Again, 18 of total 26 problems, and then including example that we already did. So starting with the vertices P1, which is 0, 1, and P2 is 1, 1, P3 is 1, 0, and P4 is 0, 0. Of a square, we construct further points as shown in the figure. So we'll have this figure here. So we'll have P5 is endpoint. So notice here, P4 is at the 0, 0. So this is 0, 0, and so on. P3 is at 1, 0, and so on. And then P5 is the midpoint of P1, 2. So this one's going to be at 0.5 or 1 over 2. Yeah, 0.5 and 1, and so on. And then P6 is the midpoint of P2 and P3. So P6 is over here. That is at 1 and 1/2. And then P7, notice how P7 is here. This is at 1/2 and 0. So vertical axis is 0, horizontal is 1/2. So yes, and notice how it keeps going in between each half. So this one goes in between these, and then this 9 goes in between. So it cuts into the half, and it keeps zigzagging all the way across in a perfect spiral, in a jagged spiral. And we're asked, so P7 has been midpoint of P3, 4. So P7 is the midpoint of P3, 4. Yeah, P6, P2, 3, and so on. And we're asked here, so the polygonal spiral P1, P2, P3, P4, P5, P6, P7, etc. approaches a point P, so it's approaching a point P inside. And we're asked if the coordinates of Pn are at the nth P are x and yn, show that 1/2 xn plus x sub n plus 1, and then xn plus 2 plus xn plus 3 is all equal to 2, and find a similar equation for the y coordinates. And then we're asked find the coordinates of P, so basically as the limit goes to infinity, which is quite an interesting problem here. All right, so let's continue on to the solution. So solution to part A. So part A says if the coordinates of Pn are x and yn, and we're asked to show that 1/2 xn plus 1 plus xn plus 2 plus xn plus 3 is equal to 2. And also find a similar equation for y coordinates. So since Pn is defined as the midpoint of Pn minus 4 and Pn minus 3, or that line right there, we have, so yeah, notice here. So if we have Pn, so if, for example, P5 is the midpoint between P1 and P2. So in other words, this one right here is, if this is n is 5, this equals to 5 minus 4, and this equals 5 minus 3, which equals to 2 there. And then P6 is the midpoint of 2 and 3. So we just increment those. This equals to 6 minus 3. And this over here is equal to 6 minus 2. 6 minus 2. Actually, not 6 minus 2, 6 minus 4. So they're all 6 minus 4, 6 minus 3. And then P7. So P7 is between P3 and P4. This equals to 7 minus 4. 7 minus 4, yeah, 7 minus 4. And this 4 is equal to 7 minus 3. So it's always a minus 3 or minus 4. Yes, so we have Pn is defined as the midpoint of Pn minus 4 and Pn minus 3. Yeah, so we have, well, for n equals to 5, we get P5 minus 4, and then P5 minus 3 is equal to P1, P2, etc. And this, it keeps going on for the other one. Alright, so what we have here now, so that's what we have for P5, or for n is equal to 5. And then if we were to draw this out in a square, and we could write a formula for xn. You have particular x5. So let's say we have this. Alright, so we have this, and this is right here. This is our P4, is at 0, 0. P3 equals to 1, 0. And then P2 equals to 1, 1. And then P1 is equal to 0, 1. And our P5 is going to be right here. This is our P5. P5 is right there. And again, our P5, this is just going to be at 1/2 and 1. And so what we have for the xn position, xn is equal to 1/2 of xn. So we take the coordinates here. So what we'll do is we'll take this right here plus this divided by 2. So basically the average distance from 0 to 1. So this is the xn of this coordinates, or the pnth coordinates, or the xn coordinates, or just for the n spot. Yeah, for pn. So then we'll have the xn coordinates 1/2 times by, this is xn minus 4 plus xn minus 3 divided by 2. So in other words, the average. And this is all for n is greater than or equal to 5, because there's only halfway points beyond the square. And also note that for n equals to 5, we get x5 equals to 1/2 times by xn minus 4, which is x1 plus xn5 minus 3 is x2, which again, this equals 2, 1/2, 0, so that's a 0 right here, and then 1 plus 1. So in other words, we just get a 1/2. Alright, so then this just equals to 1/2, as we already had in between here. So like that, that's just our 1/2 right there. And here I just wanted to illustrate that was the halfway point, and there's our 1/2 right there. Alright, so moving forward, we could actually use mathematical induction. So using induction, we can prove this equation that we were asked to solve. So we could prove that. So we can prove that 1/2 xn plus xn plus 1 plus xn plus 2 plus xn plus 3 equals to 2. So we could prove this. Alright, so in induction, first we have to consider the first case. So let's look at n equals 1. So the case n equals 1 is immediate. We just plug that inside. So what we'll get is So for n equals 1, we have 1/2. So xn is x1 plus x2 plus x3, and then plus x4 equals 2. Well, let's solve this and move this down here. Yeah, this equals to, well, let's move it over here to have some more space. X1 is 0. And then X2 is 1. So X2 and X3 are 1. So what we get is 1 plus 1, and X4 is 0. X4 is right here. So what we get is equals 2. This becomes 2, 1/2 plus 2. So times by common denominator, 2 over 2. This equals 2. Let's put it over here. We're actually, no, I think we're getting ahead of ourselves. This is 0. So this just equals to 2. Yeah, so 1 plus 1. So yeah, there's a 0 there. That's just 0. So this just equals 2, 2. So that is true. So the first case is true. All right, so let's assume that the result holds for n equals k minus 1. I'll just put a check mark because that's indicating it's true. So this equals to 2 there. So, and then solve for the case n equals k. So what we'll do is we will assume that, we will assume that for k minus 1, so 1/2 of x k minus 1 plus, this is going to be, yeah, that's k minus 1, that's n there. This is going to be plus 1, so this is k plus x, this will be plus 2. So this is k plus 1. And then plus k plus 2 equals to 2. So assume it's true for that. Again, as per mathematical induction that we went over earlier in the earlier problem. All right, so if we assume it is true, then for n equals to k, so that was k minus 1. So notice this n plus 3, yeah, when k is k minus 1, we'll just subtract that, so that's k plus 2. So for n equals to k, we have 1/2 x to the k, oops, this is x, not k, this is x. So n is k, then plus 1 plus 2 plus 3. And then this is going to be, the next one is k plus 1 plus k plus 2 plus k plus 3 equals 2. Then we got to solve this one. Like this, plus 3. Alright, so we want to solve this, and this is a pretty next level solution that the solutions manual gives. So what it does is, well, it considers this right here. It says k plus 3. It doesn't show up into this assumed equation, but it shows up once here. So it doesn't show up this one, but these ones, well, yeah, all these ones do. K plus 1, k plus 2, and k, but not k1, k minus 1 there. So what it does is it does this. So it takes this assumed one, so we start off here, and it replaces, yeah, so it replaces, or I'll just say replace. I'm doing the solutions right here. So replace k with k plus 3 minus 3. So we're not changing, well, we are changing this one. We're starting from k there. So it's saying write this out. So then what we get is 1/2 x, and then k plus 3 minus 1, that becomes minus 4. Plus x to the k, which is k plus 3 minus 3. And actually the solutions manual doesn't even explain this. They just, they mention this, but they don't actually do it. They just skip all the steps and then go straight ahead to the pretty much the answer. So I am doing this. Well, I'm assuming this is what they were talking about. So then the next one is plus k plus 3. So k plus 3 minus 2, and then there's a plus 2 there. So then this will be plus kx, k plus 3 minus 1 equals to 2, like that. All right, so if you see the pattern here, and then it does this again. So we'll call this equation 1. And then what you could do is, because notice the pattern here, and then when we could subtract and get a whole bunch of cancellations. If we do another step here, replace k with k plus 3 minus 2. Remember, it will just be shifted by 1. And when we do this, we're basically adding another one. This will end up with a k plus 3 here. This is a k plus 3 minus 1. So what we get is equation 2, 1/2 x k plus 3, and then there's a minus 1 there. So there's a minus 1 that becomes minus 3, like that. Plus x k plus 3 minus then it becomes plus 1. This just becomes k, So plus 3 minus 2. And the next one's going to be plus 1. X k plus 3 minus 1, because we're adding 1 here. And then finally we get a x k plus 3 plus 2. So then plus 2, then we're left with this. So notice this k over here, x k plus 3. Now we have this right here. So what we'll do is, so now subtract. So we're going to subtract the 2, subtract both equations like this. And yeah, we could have started from the other one. If we did this one first, we'll subtract that from the other one, or the other one from it. But we'll just do it this way. So what we're going to do is subtract equations 2 minus 1, so that we're left with this x k plus 3. So we have this term there. So what we'll get is, so when we subtract them all, so with this minus this, we'll see what we have. So this right here, this is 1/2. This lines up with this, that's 1. So we're subtracting that. That's going to be equals to negative 1/2 x k plus 3 minus 3. And then the next one here, so we have this k plus 3 minus 2. That is, this right here. So this will cancel. So we'll just cancel this out. Yeah, so that just cancels. And then the next one is right here, k plus 3 minus 1. So we have one here. This also cancels. And then we're left with, this right here, x k plus 3. Well, actually, before we get to that, we have this one here. So we have this. And we have this right here, but we're subtracting that. So we'll just subtract it. 1/2 x k plus 3 minus 4, and then plus this. Plus x k plus 3, and then 2 minus 2 is just 0. Like that. And now what we'll do is we'll move these over to the other side and factor out the 1/2. And what we get is x, and then solve for this one by itself. So x k plus 3 is equal to 1/2. Factor that out. These are going to be additions now. And we're going to be adding x k plus 3 minus 3. Like this. Minus 3. Or we'll do this one in front, actually. Yeah, just so the numbers get bigger. So this is minus 3. So we'll do this one first. Minus 4 plus x k plus 3 minus 3. And then if we solve this out, or just simplify this. This becomes 1/2 x k minus 1. So 3 minus 4 is 1. And then this one is going to be plus xk. Plus xk, like that. So this is the equation for xk plus 3. Alright, so now that we have this, what we can do is, let's go start off with our case n equals k right here. So we have this 1/2 xk plus xk plus 1, then plus xk plus 2, then plus xk plus 3. And then we could insert this inside it. So thus we get 1/2 xk plus xk plus 1 plus xk plus 2 plus xk plus 3, and we're going to throw this inside there. This equals to 1/2 xk plus xk plus 1 plus x k plus 2 plus 1/2, and then 1/2, and then we just get our x k minus 1 plus k xk. I'll move this here, plus xk, like that. Alright, so I just moved it over here so it fits all into this column. So we have this, and now if we expand this out, we get, and I'm going to move the smallest term on this side. So this equals to 1/2 xk minus 1. And then now we have a 1/2 xk right here. So I just move this over to here. And now this plus this 1/2 xk. Well, I'll just add it just for completeness. 1/2 xk plus 1/2 xk, and then plus xk plus 1 plus xk plus 2, like that. This equals to 1/2 xk minus 1, and now these add up, plus yeah, this just becomes 1, so xk, and then plus xk plus 1 plus xk plus 2. So in other words, this right here, this is the case, yeah, this is a case of, yeah, case n equals to k minus 1. So that's k minus 1. Look, that's exactly what we assumed. This right here. So that equals to 2 then. So in other words, this whole thing equals to 2. And we have just proved it. So then this equals to 2. And that's check mark, because this is the case for n equals k minus 1, which we assumed is true, and then the k version, or the case for n equals k, is also true. So hence we proved by induction. All right, yeah. So thus our induction is true, and I'll make some room for it. Yeah. So the our induction hypothesis is true, and similarly, the same argument holds true for y. Except 2 is replaced by, yeah, so we can do the exact same steps, but we're going to replace this 2 by, well, we're going to take that same equation, so this right here, 1/2 xn plus xn plus 1 plus xn plus 2 plus xn plus 3, and then instead of 2, we're going to solve for what it should be. So I'll write 4 n is greater than or equal to 5, and then yn is also going to be the average. So yn is equal to 1/2, again, just going to be 1/2 yn minus 4 plus yn minus 3. So exactly the same thing, because it's a square. Remember, it's a square. So then we look at case for case n equals to, or yeah, for case, instead of 4, for case, the first case, n equals to 1, we get 1/2 y1 plus y2. Remember, k plus 1, yeah, so that's k plus 1, k plus 2, or n. So this one is going to be for n equals 1. So for n equals 1, and yeah, for next one's n, for n equals 1 there. So y1, then it's going to be n plus 1. Yeah, so we're going to go over here. So n plus 1 plus 2 plus 3. So then this becomes plus 3 plus the next one is y4. This equals 2. Well, let's look at our square. So y1 is 1. So the y1 and y2 are 1, and y3 and y4 are 0. So there's 0, the y coordinates. This is 1, 1, and 0, 0. So we could just throw this inside. So this 1/2, this becomes 1/2 times 1 plus y2 is also 1. Then y3 is 0, plus y4 is 0. So this becomes, this becomes 1/2 plus 1. In other words, multiplied by top and bottom by 2. So we get a 2 plus 1 is 3/2. So if case 1 is, case for n equals 1 is true, and then we can do the same thing by induction, and then it's true for all of them. Exactly the same thing. The only difference is that constant number. Instead of 3/2, instead of the other one was 2, we get 3/2. Alright, so thus we have, so put it all together, thus 1/2 yn plus yn plus 1 plus yn plus 2 plus yn plus 3 equals to 3 over 2. And we can bold all this or circle this whole thing like this. Alright, so now that we have this, and also I just want to put a note for all n. Yeah, this is basically for all integers n is greater than or equal to 1. Like there, because yeah, it applies for 1, 2, 3, etc. Alright, so we have this. Now let's look at the solution to question B. And if we scroll up to question B, this states find the coordinates of P. So in other words, when n approaches infinity. Alright, so, well, to solve this, it's actually fairly straightforward. So we are asked to find the coordinates of P, not Pn. Yeah, so in other words, the coordinates of P, and then basically we can take the following limit and solve for xn. So in other words, yeah, the coordinates of P are the limit as, well, we can just write this, the coordinates of P are the limit as n approaches infinity of Pn, just the nth P, which are xn and then yn. So in other words, we can solve for this by taking the limit there, and we have equations for xn and yn. So we have this equation for yn, and we have it for xn, this setup here. Let's go back to the full equation. So we have it for this right here, 1/2 xn plus 1 all the way there equals to 2. So what we'll do is, and it equals to 2, so then if we take the limit, that has to equal to 2, because it's already, because it's equal to 2. So we could do a limit as n approaches infinity of 1/2 xn plus xn plus 1 plus xn plus 2 plus xn plus 3. This equals to 2. So we know the limit is 2 because all that equals to 2. So we could do, now we use our limit rules and write this all as separate limits. Limit as n approaches infinity of 1/2 xn. I'll just take this x, I'll take the 1/2 out. 1/2 limit as n approaches infinity of xn plus limit as n approaches infinity of xn plus 1 plus limit as n approaches infinity of xn plus 2, and then we get plus limit as n approaches infinity of xn plus 3, and again, all this is equal to 2, but that's pretty straightforward. So that all equals 2, but then these are all the same limit. So as xn goes to infinity, sub infinity, they're all approaching the same one, because once you're going to infinity, the n plus 1, infinity plus 1 is still infinity, and this one plus infinity is still infinity. So in other words, all of this, these are all the same limits. All the same limits. This means then that, this means that we could factor out xn from all of them. They're all the same limits, so it's the same way, same thing as writing, well, just factoring it all out. Same thing as writing 1/2 plus 1 plus 1. Yeah, so we have 1/2, just factor out everything, and this will be 1, 1, 1 plus 1, another 1, and then times it by the limit of just one of them, and we'll just take the first one. Limit as xn approaches, as n approaches infinity of xn. So this is equal to 2, and then this right here, 1/2. This is going to be, well, 1/2 plus 3, and we can multiply top and bottom by 3 over 3. Actually, we don't multiply that. We multiply this by 2 over 2. So that's the same common denominator, and then that becomes, well, 6 plus 1 is 7. 7 over 2. So then this becomes equals to 7 over 2 limit as n approaches infinity of xn, which equals all to 2. So then we can move this over to this side. So in other words, what we get is limit as n approaches infinity of xn is equal to, so 2 times 2 is 4, so we get 4 over 7, which is quite fascinating. So that is 4 over 7. And then similarly, we could do the same thing for the y, but instead of it equaling to 2, similarly, we could do this for, similarly for the y, it's going to be the exact same thing, but instead of this equaling to 2, we're going to get, so similarly, we're going to get, I'll just leave it like that. Similarly, we'll get a we'll just have a 7 over 2 limit as n approaches infinity. Because remember, it's the exact same thing, but it equals to a different number. Instead of 2, it equals to 3 over 2 of yn. This is n, not 2. Yn. So make sure I got it all right. Yes, yn equals to 3 over 2. So that's the only difference. 3 over 2. And then we divide this out. Well, this cancels. So move this over. The 2's cancel. We'll have 3 over 2. So then we get limit as n approaches infinity of yn is equal to 3 over 7. So yes. So that's what we get. Yeah, so then this means, then, let's put it all together, thus, limit as n approaches infinity of Pn, which is xn, yn, is equal to P, and it equals to 4 over 7 over 3 over 7, which is quite fascinating. So those are the coordinates of P. Alright, so now that we've solved this, now let's go over to the next problem, and that's problem 19. And this says, find the sum of the series, and it's the summation from n equals 1 up to infinity of negative 1 to the power of n divided by 2n plus 1 times 3 to the power of n. Alright, so let's jump right ahead to the solution. So notice this right here. So from the earlier table, the Maclaurin series for inverse tan of x is, and if we go back to our table, so basically notice this one. So this is 2n plus 1, and then we have this negative 1 power of n, and there's a 3n there, but we're missing the x value. We can sort that out. So we'll look at the tan one. Alright, here. So if we teleport above here, so there's inverse tan. This equals to the summation from n equals 0 to infinity of negative 1n divided by, it times by x, 2n plus 1 over 2n plus 1, which is x minus x cubed divided by 3 plus x over x5 minus, divided by 5 minus x to the 7 divided by 7 plus, etc. ... And r is, and the radius of convergence is 1. So let's take a look at this and put that inside our function or our stuff. So let's say we go here. So if I equals this, let's teleport backwards. And we teleport all the way back here. And alright, so now let's write that down. Alright, so let's writing that down. We get tan negative 1x is equal to the summation from n equals 0 to infinity of negative 1n over, and then we'll have x 2n plus 1 and then 2n plus 1 at the bottom like that. So just 2n plus 1. And then this equals 2. When you plug in 0, this just becomes, 0, that's be power of x. This is positive. And this becomes 1. So this becomes x, and then as per before, x3, when you plug in 1, this becomes 3, 1 is 3, this one's negative. So 3 over 3, then becomes x5 over 5, and then it keeps going minus x7. So minus x7 over 7, and then goes plus minus ... And radius of convergence is r equals to 1. Like that. Alright, so now that we have this, and now in particular, notice there's an x there, but there's no x here, and there's a 3 there in power of n, and so on. So whenever you have a 3, and especially 1 over 3, and you're dealing with tan, we have to jump back to our triangle. So in particular, notice that, so for x is equal to 1 over square root of, so 1 over square root 3, we have our trusty triangle. Let's just draw this here. Our equilateral triangle. Like this. So this is, let's say, so if we look at our trusty equilateral triangle, let's say the lengths are 1, 1, then divide this into 2, we get a 1/2 right here. Now this angle is pi over 3, this angle is pi over 3, now this angle is pi over 6, because it's pi over 3 divided by 2, pi over 6, and now this length right here is square root 3 over 2, and we can solve this by just using Pythagoras. So square root 1 squared, again, plus or minus, take the plus. So take the plus is 1 minus, and then we're gonna get this over 1/2 squared, like that. So then this becomes, well, square root 1 minus 1 over 4. Like that, and this is just 4 over 4 minus that just becomes square root 3 over 2. So yes, that becomes that. Alright, so now we have that, and if we look over here, so there's a square root 3 over 2, and there's 1/2, and we can cancel out those 1/2s by taking the tan. So tan of pi over 6, again, opposite over adjacent, tan of pi over 6 is equal to opposite, which is 1/2, divide this by the adjacent, square root 3 over 2. Again, this is opposite over adjacent, like that. So then these cancel. So those are canceled, and we get tan of pi over 6 is equal to 1 over square root of 3. And then what this means is, well, we could take the arctan, or the inverse tangent. So inverse tan is just basically switching up the x and y coordinates of 1 over square root 3 equals to the angle. So that's why it's arc or inverse, arc for the arc, etc., for the angle. And now let's put this like that and like that. Anyways, this becomes pi over 6. So we just switch them up like that. Alright, so let's just bold this. Alright, so we have this, and what we're going to do now is plug that inside here. So for tan, so notice there's a 1 over 3 over on this, the summation that we want. And then we have this tan, throw that inside, and we're going to get something similar. So I'll put a thus pi over 6 is equal to inverse tan of 1 over square root 3, and this equals 2, plug that inside the giant summation with x is equal to 1 over square root 3. This equals 2, let's put this all nicer, equals 2 summation up to infinity of, from n equals 0, negative 1n, so negative 1 to the power of n, so let's write that here, negative 1, and then this x is going to become, 1 over square root 3 over 2n plus 1. Yeah, so 2n plus 1, all divided by 2n plus 1. 2n plus 1. Alright, so now we can do some simplification. So this will equal to, move it over to this side here. So then, yeah, just put this equals to here. And now this equals to the summation. I'll put the summation better. Like that. Summation from n equals 0. And then we'll have this negative 1. Negative 1 like this to the power of n. Times it by, and I'm going to move this to the bottom. Yeah, this is divided by square root 3. I'm going to move it to the bottom and get rid of that square root, make it just a power of 1/2. So we get a 2n plus 1 times it by 3 to the power of 1/2, and then times it by this part over there. Yeah, times it by, so there's 1/2, and then I'll just put a 1/2 like this, and then put this 2n plus 1, like that. Alright, so we have this, and I'll write this like this. Let's move this by itself, 1 over 1, like that. 1 over 2n plus 1, and then 1 times it by 1 over 3, 1/2, and then 2n plus 1, like that. And now we can further simplify by multiplying that inside. So this equals to summation from n equals 0 up to infinity of -1 n, again 1 over 2n plus 1. And then we have this part right here. We'll multiply that inside 3, so half multiplies becomes n, plus, and then 1/2 times 1 is just 1, like that. Alright, we can continue to simplify this further. I'm going to bring down that pi over 6. So this pi over 6 is equal to, and now let's simplify this. This is right here. This equals to 3n times it by 3 1/2, which equals to 3n times by square root 3. And then we're going to take out this square root 3. Again, it's 1 divided by square root 3. So we'll take that out. This will equal to 1 over square root 3. And then summation from n equals 0. Yeah, n equals 0. And then we have 1. Actually, we have the -1. Yeah, let's put this on top. -1n over 2n plus 1 times it by 3n. Now if we scroll up to our question that we're asked, well, we have, this is pretty much it, but then this is starting from n equals 1. So, and then we have is -1 to the power of n, and then it's 2n plus 1 times 3n. Yeah, and this is exactly what we have here, but we need to start from n equals 1, and also move this over to this side. And basically what that means is we're going to have to get the zeroth term out of there. So what this becomes is square root 3 over 6 pi, square root 3 over 6 pi equals 2, and then put the 0th term inside. So we'll have a -1 to the power of 0, so put the 0 inside there, over 0 plus 1 times by 3 to the 0, like that. And then plus, then we go to the next step up here, summation from n equals to 1. Yeah, from n equals 1 there. And then we'll have this -1n, 2n plus 1, and then 3n, like that. And now this part right here, this is -1 to the power of 0, that's just 1. Yeah, so then this just becomes 1, and then this is just 1 times, this is also 1 right here. So this whole thing just becomes 1. Yeah, so the number to the power of 0 is defined as 1 almost always. Alright, yeah, just had a bit of lag. So then, yeah, this goes to, yeah, this right here also goes to 1. So approaches 1, or yeah, equals 1. And what we get is now this whole thing becomes, yeah, well, we're going to move this over to the other side. That just becomes 1 over 1, which is 1. And yeah, let's put this here. This all equals to 1. So now move this over to this side and solve for this. We get, I'll just write thus. Thus we have the summation. Yeah, and put this nicer. Summation from n equals to 1 of -1n over 2n plus 1, 3 times 3n. Put this line all the way across. And this is equal to, and then this minus this. So square root 3 over 6 pi minus 1, because we moved this over to the other side. So this is what it equals to. Or you could write this in a different way. Just the solutions manual usually does this. My calculus book usually does this a lot. They want to get rid of this, yeah, this square root 3 on top. They want to put it on the bottom for some reason. So then this becomes, also basically, yeah, I think that's what they want to do. Yeah, so then this becomes equals 2. I'll just write this square root 3. So then I'll write this as 3 1/2 over 2 times 3 to the power of 1. Well, I just want to simplify the number of the numbers there. So then this one here is 2, so instead of the 6, we want to make it simpler, 3, yeah, we'll have it a 3 and a 2, dealing with smaller numbers, pretty much breaking everything down. Pi, like this, and now we can subtract this. This 1 minus 1/2, that just becomes 1/2 at the bottom. So then minus 1, this equals 2 pi over 2 square root 3 minus 1. So we got rid of the 6, made it as simple as you can. So you could do this one, that's what the solutions manual gives. Alright, so now that we have this, so we're done problem 19. Now let's go over to problem 20. And problem 20 states, carry out the following steps to show that 1 divided by 1 times 2 plus 1 divided by 3 times 4 plus 1 divided by 5 times 6 plus 1 divided by 7 times 8 plus etc. Equals to ln 2. So now it's given us steps to follow to show that, so that's pretty good. So part A, use the formula for the sum of a finite geometric series to get an expression for, so this right here, so 1 minus x plus x squared minus x cubed plus plus 2x, plus x to the 2n minus 2 minus x to the 2n minus 1. And then part B says integrate the result of part A from 0 to 1 to get an expression as an integral for 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus plus 1 over 2 n minus 1 minus 1 over 2n. And then we're asked in part C to deduce from part B that the absolute value of 1 over 1 times 2 plus 1 over 3 times 4 plus 1 over 5 times 6 plus plus 1 over 2n minus 1 times 2n minus the integral from 0 to 1 of dx over 1 plus x is less than the integral from 0 to 1 of x 2n dx. It's a whole lot of mumbo jumbo. And then part D says use part C to show that the sum of the given series is ln 2. Alright, so let's jump right ahead to solution to part A. So let's just jump to the solution. So part A says use the formula for the sum of a finite geometric series to get an expression for this. So we have this 1 minus x plus x squared minus x cubed plus plus x to the 2n minus 2 minus x to the 2n minus 1. So, and then it says use the finite geometric series. So recall the sum of a finite geometric series. If we have the sum at the nth partial sum equals 2, Sn equals a plus ar squared plus ar n minus 1, and then Sn is equal to a times 1 minus r power of n, all divided by 1 minus r. So in our case, we have, well, let's just write the general one here. Sn equals to a plus ar, so plus ar squared plus plus ar n minus 1. Yeah, and then this equals to, I'll just put this whole thing here. So a1 minus rn over 1 minus r. Alright, so that is just a general, the general nth partial sum for a finite geometric series, and there's the equation for the sum of it. And now let's write this out and see how we could use that formula. So we have 1 minus x plus x squared minus x cubed, and also notice the way they write it, 2n minus 2 and then 2n minus 1. So we get here, so in our case we have 1 minus x plus x squared minus x cubed plus and yeah, I think that's what we wrote. So yeah, minus x plus x squared minus x cubed plus and then plus 2x plus x 2n minus 2 minus x to the 2n minus 1. Alright, now we need to see what matches up. Well, we have here a is 1, So we just write our a equals to 1. Like that, I'll just put the arrow above here. So a equals 1. Now the r, well, the r is right here. So if a is 1, then this r is right over here. And yeah, we forgot to add the AR. So let's move this all the way to the right side. Plus AR plus, yeah. So that lines up. So AR plus AR squared, etc. And then we have this R. So A is 1. R is going to be here. R equals to just negative x. Yeah, so that's just r is negative x. And then what we'll have is, well, negative x times negative x is going to be here r squared. That just becomes positive x squared. So that's this one here. And we could see that. And then notice here, this n minus 1, this matches up with, if this is the n minus 1, supposed to be this. And then notice how there's a n right there. Yeah, and basically what's happening here is this n is, in this case we have n is equivalent to 2n. Or another, basically this n, this one right here, this n. I'll just put that again. So the n is equivalent to 2n. And the reason I'm putting this 3 lines because the variable is already there, n and n. And we're not saying the same thing, we're just saying that it's equivalent to. So this n is replaced, is equivalent to this 2n in this formula. Because right here I could write a equals 1 because there's no other a variable. And I could do r is equal to negative x, there's no other variable, but this one is already n there. So this means that we'll get the sum is going to be 1 is our a, times by 1 minus negative x 2n. So we're not going to put n there, so the n becomes 2n. So there's a 2n there. And I'll remove this line like this. So put this 2n, and then I'll divide this by 1 minus negative x. So this means is this whole summation is equal to, do a bunch of simplifications, 2n there is, well, this is always going to be positive because it's always an even power, and so we're just going to be left with this minus by itself. So it's going to be 1 minus x to the 2n over 1 plus x. So that's what the sum of this finite geometric series is. Alright, so now let's take a look at the solution to part B. So part B says integrate the result of part A, so this one here, from 0 to 1 to get an expression as an integral for this setup here. Alright, so which is 1 minus 1/2 plus 1 cubed, plus 1/3 plus 1 over 4 plus ... 1 over 2n minus 1, and then minus 2n, and minus 1 over 2n. So integrating, so solution to B, integrating the result from part A from 0 to 1, we get, so put this in the integral. So we're going to go integral from 0 to 1 of 1 minus x plus x squared minus x cubed plus ... and then minus, this is going to be, actually no, it goes all the way to plus. Let's see how it goes. Yeah, this the way it's written, yeah, it goes minus here, then eventually it's going to be a plus there, minus there. So plus all the way to x 2n minus 2 minus x 2n minus 1. Like that, dx. And now this just equals to, well, integral from 0 to 1 of our sum of the finite geometric series, 1 over x 2n over 1 plus x, and then dx. Alright, so what I'll do now is, well, I'm going to integrate all this and evaluate it, as well as this as well. I'll just separate that into 2 integrals. So what we're going to get is, this is equal to, the integral of 1, or the antiderivative of 1 is just x. So we're going to go up, this is going to be x. This next one's going to be x over 2, yeah, like that, 2 over 2, like that. Again, using power, just the antiderivative power functions and antiderivatives or integrals. And again, this is x squared. This is going to go 3 to increase the power divided by 3. Next one's going to be x4 over 4 plus dot dot dot. The next one is going to be here, so we're going to subtract we're going to add a power, so x 2n minus 1, and then divide by that, 2n minus 1. The next one here, add a power, minus x, this is going to be 2n over 2n, like that. And we're going to be evaluating this from 0 to 1. Now this whole thing equals 2, and I'm going to put it on the right side now. So that was the left side. This is the right side. We can just divide this 1 plus x into 1 and into negative x 2n. So we get a 0, 1, then 1 over x, 1 over 1 plus x. So we get two integrals, 1 over 1 plus x dx plus, or actually minus, because of minus sign, an integral from 0 to 1 of x 2n over 1 plus x, and then dx. So that's what we have. And now we're going to evaluate this. We're going to put the 1 in each one and then subtract from 0 in each one. When we put in 0, well, we just have 0 to the power of whatever. Those all vanish. So all that matters is this right here. It's just the 1 is all that matters. So we get equals 2, 1. So when you put in 1, it just becomes 1. 1 over 1 over, 1 minus 1/2 plus, then we get the x cubed, just 1, plus 1 over 3 minus 1 over 4 plus dot dot dot, then plus, then this becomes 1 over 2n minus 1, and then minus, this becomes 1 over 2n, and that equals to the integral on the other side, 1 over 1 plus x dx minus integral 1x 2n 1 plus x dx. Yeah, so we have all this. I'm just going to box this out like that. And there's a 0 here that got messed up somehow. Like that. Alright, so that is the 0. I'll move this a bit lower. And this a bit higher. Alright, so now we have expression. Yeah, or the expression for the one that we were given, and this equals this integral. So then we can solve question C. So let's go back to this. So again, we were told integrate the result of part A from 0 to 1 to get an expression as an integral for this. So yeah, so we wrote this 1 divided by, 1 minus 1 over n plus 1 over 3 minus 1 over 4, etc. All this as an integral, and now we're asked in part C to deduce from part B that the absolute value of 1 divided by 1 times 2 plus 1 divided by 3 times 4 plus 1 divided by 5 times 6, etc., and then all the way to 1 divided by 2n minus 1 times 2n, and then subtract this by integral from 0 to 1 of dx over 1 plus x, less the absolute value of all this is less than the integral from 0 to 1 of x to the power of 2n dx. Alright, so let's take a look at the solution to part C. So part C, the part C, we gotta get it in this giant absolute value sign, and notice this 1 divided by 1 times 2 plus 1 divided by 3 times 4, and notice the square root from 0 to 1 of dx 1 plus x, and that we have this set up here. So we have this. So the idea is if we can write this in that form I was asking, so solution to C, notice the following. So if we take this segment here, so let's just take that segment. So notice that if we have 1 minus 1 over 2, well, it's the same thing as writing, I'll just write it in extra detail. So if we have 1 minus 1 over 2, this equals to, well, 1 over 1 minus 1 over 2, just for completeness, just to show you the pattern. And this again equals to, multiply the top and bottom by 2 over 2. So 2 over 2. Then we're going to get a 2 minus 1 over this, 2 times 1 is the denominator, or just 1 times 2, like that. And this just equals to 1 over, yes, and this just equals to 1 over 1 times 2. And the reason I'm writing that is because that is in this form here, so 1 times 2 there. And then as you can guess, I'm going to do that the same for the 1 over 3 times 4 and 1 over 5 times 6, and so on. So that's that. And also now if we look at this segment, so right here, let's look at that now. And 1 minus 3, 1 over 3 minus 1 over 4, this right here, is equal to, and again, multiply the common denominator on this side. I'm going to multiply this one by 4 over 4 and this one by 3 over 3. So in other words, we're going to get a setup that looks like this. This is 4 minus 3, and then the common denominator is 3 times 4. So multiply top and bottom from both sides, and then when you multiply it on this one, 3 times 4, yeah, the 3 cancels, and this one, the 4 cancels. And notice here, this equals to 1 over 3 times 4. So in all the scenarios, we are going to get, notice this is 1 times 2, or this is 1 over 3 times 4. Let's do, well, there's no more there, but you can see it's pretty much the exact same thing. Then if you continue all the way over to this side and see what happens there, so dot, 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 so then we get 1 over 2n minus 1 minus 1 over 2n, like this. This equals 2, well again, multiply the top and bottom by each other, so we get the same common denominator. So in other words, we get a setup here, 2n minus 1 times 2n. This equals 2, or we multiply the top and bottom, so this one will cancel, we're left with 2n minus, and then this is going to be minus 2n plus 1. So in other words, minus 2n minus 1, so the minus becomes positive. And this equals to, well, this cancels, and yeah, we don't need to go any further because that's what we were asked to show. That just remains it like that. So then those cancel, and we're just left with 1 over 2n minus 1, 2n, like that. Alright, so now that we have this, so thus we see from part B, so we could write this all in that form that we were told in the question C. So we get this all here, and also notice here, I'm going to move this over to the other side. So I'm gonna take this and move it to the other side. So we get a negative, negative integral from 0 to 1 of 1 over x dx. And basically I have this side there. So basically we're gonna write this out, but before we get to the absolute value sign, so that's what we get is a 1 over 1 times 2 plus 1 over 3 times 4, and then plus dot 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 plus the nth one here. This is 2n minus 1 times, oh, let's make this whole thing. So 2n minus 1, write this neater. 2n minus 1 times by 2n, 1, like that. And this equal, and then subtracted by. So we're moving over, moving this over to the other side, subtracted by 0, 1 over x dx. And now this equals 2, and now we're just left with this negative integral from 0 to 1 of xn divided by 1 plus x. Negative 0 to 1 x 2n 1 plus x dx, like that. Alright, so now we have this. We have a bunch of negative, well, we have two negatives there, or this negative there. So what now we'll do is take the absolute value and then show that it's less than this setup there. And we can see that. So what we'll do is, thus, the absolute value, let's write this, thus, neater. Thus, the absolute value of 1 over 1 times 2 plus 1 over 3 times 4 plus dot 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 plus 1 over 2n minus 1 times 2n minus integral from 0 to 1 of 1 over 1 plus x dx. Absolute value, yeah, so absolute value here is going to be, well, this negative is just going to be positive, and this is going to be, this just becomes, well, the positive of it. So we could, and this one, x to the 2n is always going to be positive, and also the 1 plus x is always positive because x is greater than or equal to 0 there. So this means that this is just going to be positive side. 1 over x2n 1 plus x dx, like that. And now this whole thing, well, is going to be less than integral from 0 to 1 of x, also there's a 2n there. So forgot the 2n there. Yeah, so x2n dx. And that's because, well, this 1 plus x, for this integral of 0 to 1, it's always going to be greater than or equal to it. So you can write, so it's less than that since, it's right here, since x to the 2n over 1 plus x is less than x to the 2n for, and I'll put this here, for x is for x is greater than 0 and less than 1. So, but you're integrating from the whole area. When it's when x is equal to 0, then they just both equal each other, 1 and then equals 1. But then every other value, it's all less than it, and when you're summing it up, it's going to be less than it. All right, so that is what we have. So I'll just box this whole thing because we showed that it is less than that. So that expression that we were asked to show in the question, and we just did. I'm going to move this absolute value higher. I'm going to box this out. And let's just go take a look at that question C again. So integral from 0 to 1 of xn of x2n dx. And this is a whole setup like that. And that is exactly what we were asked to show right here. There's integral from 0 to 1 x2n dx. And then part D says use part C to show that the sum of the given series is ln of 2. Alright, so let's jump into the solution to part D, and basically says use part C to deduce that, use part C to deduce, see that again, use part C to deduce, to show that the sum of the given series, which is this right here, and that's going to be inside here, is equal to ln 2. So let's take a look at this. So note that, well, we know these integrals, we can solve these. So the integral from 0 to 1 of 1 over 1 plus x dx, well, the integral of this 1 over 1 plus x, that is, well, we know the integral of 1 over x is just ln x, and this is the same thing, it's just this, but dealing with 1 plus x. And you could use substitution and so on, but this is going to be ln of 1 plus x, like that. Because you can see this antiderivative, the derivative of ln 1 plus x is just going to be 1 over 1 plus x. And this is from 0 to 1. So yes, evaluate from 0 to 1. This equals to ln of 1 plus 1 minus ln of 1 plus 0 is just 1. And we know that ln 1 is 0. So this part here, this one goes to 0. So this becomes ln 2. So this is, ln 2. That's what we have there. Alright, so that's ln 2. And now let's solve this integral right here. Yeah, so we don't need to do any advanced integration for this one. We'll just do it for this one here. So this is integral from 0 to 1 of x 2n. So we have this, put an arrow, and we have this integral from 0 to 1 of x 2n dx. This equals to the this becomes the antiderivative of x2n is x2n plus 1. So I'll put it like this, x2n. So we add a power divided by 2n plus 1. And then evaluate from 0 to 1. So this equals 2, put the 1 inside, we're going to get a 1 to the power of 2n plus 1, that's still going to be 1, divided by 2n plus 1, and then subtracted by, when we put in 0, and then divide whatever, it's just going to be 0. So in other words, this equals to 1 over 2n plus 1, and we can box this out. Alright, so thus part C becomes, and we look at part C, we got this entire giant term, and then we'll have this then it's going to be subtracted by ln 2, and then it's going to be less than 1 over 2n plus 1. So let's write this all out. So this becomes 1 over 1 times 2 plus 1 over 3 times 4. And then plus ... And then let's see, it keeps going all the way until 1 over 2n minus 1. 2n minus 1 times 2n, like this. Yeah, just fix that up. And now it's going to be subtracted from this integral right here is just ln 2. And then this absolute value is less than 1 over 2n plus 1. Yeah, and going further, so in other words, the nth partial sum Sn of the given series satisfies, and yes, if we call this inside term, this summation that we want, if we call this Sn, so that's the nth partial sum, so what we get is the absolute value of the nth partial sum minus ln 2 is less than the 1 over 2n plus 1. So in other words, we can just take the limit here. So what we'll do is limit as n approaches infinity of the absolute value of Sn minus ln 2. This right here is less than the limit as n approaches infinity of 1 over 2n plus 1. And we know this one right here, you're just going to go over, well, 1 over 2 times infinity, that's just infinity goes to 0. So in other words, this equals to 0, like that. Yeah, so this absolute value is going to 0, and then we can get rid of that absolute value sign. This basically means that this Sn is approaching ln 2. That's the only way that this can be 0. And yeah, ln 2 is a positive number. So what we'll get is thus the limit as n approaches infinity of Sn, nth partial sum is equal to, and move this over to the other side, ln 2, and we can box this in. And then solution manual just puts a whole term there. So that is, we'll have 1 over 1 times 2 plus 1 over 1 divided by 3 times 4 plus 1 over 5 times 6, etc., plus 1 over 7 times 8 plus ... is equal to ln 2, which is quite amazing. And let's box this whole thing. Alright, so now that we've solved this, let's continue on our march towards all the problems. So let's look at problem 21. This one states, find all the solutions of the equation 1 plus x divided by 2 factorial plus x squared divided by 4 factorial plus x cubed divided by 6 factorial plus 6 to the power 4 divided by 8 factorial plus ... equals 0. And we're given a hint. Consider the cases x is greater than 0 and x is less than 0 separately. Alright, so let's dive into the solution. Let's using the hint. So let f of x denote the left side of the equation. So this whole thing is f of x of the given equation. So if x is greater than or equal to 0, then f of x is greater than 1 and there are no solutions of the equation. That's because if you put in x is a 0 here, all these go to 0 and you're just left with a 1. And if you put in a number greater than 0, this all becomes just a positive number, and that just equals to 0. So in other words, we have 1 plus 0 or another positive number. 0 or, let's put number greater than 0. So in other words, this is going to be, well, greater than or equal to 1. And this is not equal to 0, so it's not a solution. Yeah, so not a solution. Alright, so now if we continue further, so basically, yeah, for x is greater than or equal to 0, it's not a solution. So now let's look at when x is less than 0. So note that, first note that f of negative x squared is equal to the Maclaurin series for cosine x. And we'll show that, and then we'll just need to find the zeros of cosine x. And note that, since we're converting this, or transforming the f of x into f of negative x squared, note that this has to be less than 0. So a negative x squared is less than 0 for, and this is for, well, all of these new transformed ones. So this one is our equivalent of our x equivalent, put 3 dots, just means that it needs to match up with this. So if we're looking at for this fx is less than 0, this negative x squared has to be less than 0. So this is for x is, well, for all x, it's actually for all x except not equal to 0. Because if you put in 0, then that equals to 0. So negative x, 0. But here if you put in if you put in x is equals to 10, so 10 squared is 100, is 100, then there's a negative sign, so it'll be less than 0. So for all x not equal to 0. So I'll just unbox that. So we have that. Now if we plug this inside, f of negative x squared inside here, then you could see that here, because this is x right there. Yeah, x, but we want this to the power of 2. This one, we want this to the power of 4, this to the power of 6, and so on. And that will match up with the Maclaurin series for cosine x, as I will go and look back at the table. So let's write this down first. So f of negative x squared is equal to 1 plus, and then the next setup is x becomes, well, that's x, that's an odd power, the negative stays. So negative x squared over 2 factorial. And then the next one is x squared. So negative becomes positive. Yeah, so negative squared even power becomes positive. So x to the 4 over 4 factorial. Then the next one is going to be minus. It's going to be x cubed. And then x cubed, yeah, it should be the negative x. Yeah, whoops, get this out of the bracket like that. So negative x squared, all squared, this is going to be 6 factorial, because that's going to be over here. So this is x cubed, and the negative is going to be to the odd power, and that becomes still negative. The next one's going to be x8, so x to the 4, and then 4, x squared to the power of 4 is 8, and negative 1 to the power of 4 is positive. So this becomes like that, and then goes minus plus dot dot dot. And this equals to cosine of x. Now here I just quickly teleported to our table above. So here's our cosine x right here. And the radius of convergence is infinity. So r is infinity, converges for all values of x. So we have here this cosine x equals to 1 minus x squared divided by 2 factorial plus x to the power 4 minus divided by 4 factorial minus x6 divided by 6 factorial, and then plus x8 divided by 8 factorial, and so on. Alright, so here I quickly teleport it back here. So now that we have this, now we just need to find the zeros of this cosine x there. So the solutions of cosine x equals 0 for negative x squared is less than 0. So yeah, so remember, this x is a product of this transformed one. And the solutions manual even got it mixed up, I believe. So anyway, so we gotta get the solutions for cos x equals 0 for negative x squared is less than 0. So it matches up with our earlier one here. So basically when x is not equal to 0. That's the only way that this negative x squared term is less than 0. So this is given by, and let's just graph our cosine function. So recall the cosine looks something like this. It goes up and down and down, yeah, and like that, and keeps going on forever. Where this is at 0, this is 1, and then this is pi over 2 is at our 0. And then this distance right here is pi. And this distance, yeah, is pi. This is going to be 3 pi over 2. Or in other words, 2 pi over 2 plus pi over 2 is going to be 3 pi over 2. And then over here is negative pi over 2. And yeah, so it's negative pi over 2. This is separated by pi. So in other words, and this is our, let's just put our x, and this is our y, and this is our cosine x. So in other words, this is separated by pi. Yeah, this is separated by pi, or you could even just go from here to here. It's a bit easier to see. Negative pi over 2 to pi. Yeah, so that's pi, like that. Yeah, so thus what we have is f of negative x squared equals to cosine x equals to 0 at x is equal to pi over 2, and then we'll just have a plus pi k. Yeah, and where k is any integer, actually. Yeah, so where k could be positive or negative. Doesn't need to be positive. The solution manual said positive because I think they got messed up. Where k is an integer. Yeah, it could be negative. For example, if it's -1, we'll have it over here. All right, so yeah, so that is the solutions for cos x equals to 0 is that x equals pi over 2 plus pi times k, which k is any integer. And again, you can, this can go over here, you can go over here and add another, you can add, you can add as many number of pi's and it will always be 0 because of the periodic nature of the cosine trig function. We'll make this a bit bigger. So that's for cosine x, or f of negative x squared. So the solutions for f of x equals 0 are, and this is in our case, well, because we solved this one here, f of negative x squared, this equals to 0 for x is equal to pi over 2 plus pi k. In other words, this throws it inside here. Yeah, I'll throw this inside here. This becomes, this is basically writing it as or. Let's put an or. Yeah, or, and just throw that inside. Or f of negative, and then negative, put that all inside. Negative pi over 2 plus pi k all squared. Like this. Let's put that better. So f of, and then this bracket. Like this. Instead of this, we'll put this one here, the box brackets, this equals to 0, like this. Yeah, so when we put that inside here, so now this part right here is our equivalent value for that f of x we want. So that is, let's put it all together, that is f of x is equal to 0 for this, and now we'll have x is equal to negative, this whole thing here, negative pi over 2 plus pi k squared, like that. And k is any integer. Yeah, where k is an integer. Alright, so now that we have that, I just want to make a note. Note that I deviated from the solutions manual because it assumed that x is less than 0 even after it was, I'll put it was transformed to negative x squared. That is, they considered cos x equals 0 for x is less than 0. And this does not necessarily always have to be the case, because if x is greater than 0, the transformation is still negative x squared is less than 0. And a simpler example is, for example, we have an example right here. For example, let's say we have fx is equal to x. Yeah, let's say fx equal to x. Fx equals to x. And this is less than 0 for x is less than 0. If we transform it, but, let's put it, but f of negative x is equal to negative x, and this is less than 0 for x is greater than 0. So in this case, we have it all on the opposite. Yeah, so notice how this one here is, and not, in the transformed case, not for x is less than 0. So that's the only way it can be less than 0 is if this x is positive. So yes, you have to consider what you're transforming, etc. So yeah, so I believe I believe the solutions manual was not giving the proper solution. All right, so now that we've covered this, and yeah, we're done this problem. Now let's jump right ahead to problem 22. And this one states right-angled triangles are constructed as in the figure. So you have point P there. So you have point P, and now you have a right-angled triangle. In this case, length 1, and then this opposite is 1. There's a right angle, and then it extends outward. So this doesn't have to be 1. And notice how the next hypotenuse becomes the base. This is the base, base, etc. All right, and each triangle has height 1, so that's the height, and its base is the hypotenuse of the preceding triangle. So if this one right here is the hypotenuse, it becomes the base for this one here, and it is the hypotenuse of the preceding one. and show that this sequence of triangles makes indefinitely many turns around P by showing that the summation of this angle, this theta sub n, is a divergent series. In other words, it can turn infinitely amount because the angle keeps getting bigger and bigger that you're rotating around. Alright, so now let's take a look at the solution, and solution goes from here. So suppose that the base of the first triangle has length a. So let's say instead of 1, let's say it's a. So that base. And then by repeated use of the Pythagorean theorem, we find that the bases of the successive right angle triangle are... Alright, so let's start here. Let's say we have a triangle. Make a table. Alright, so we have triangle and then we have the base. I'm going to put like this. That's triangle number. And then this is our base. Alright, so that's the base, is the hypotenuse, is a hypotenuse of the preceding triangle. So each one. So let's say we have, this is triangle 1. So this triangle 1 here, and then the base is A. Instead of this, they just put an A in the solutions manual. So A, and there's the opposite is 1. So then we could solve for the hypotenuse there as using Pythagorean theorems. But first we have the base there. Then triangle 2. Yeah, so triangle 2 is, this is the new A, or yeah, this is a new base right here. So this is the new base, and this is the hypotenuse of this. In other words, B is equal to square root of 1 plus A squared. A squared, yeah, 1 squared plus A squared, etc. And this, because this is our A. And then we can keep doing that as well for the new base, and it's always the hypotenuse of the preceding one. So this becomes square root 1 squared plus A squared, which equals to, well, square root 1 plus A squared. And now the third triangle is going to be, well, instead of squaring this A squared, this is the new base. So this becomes, again, it's going to be another 1 squared because all the heights are 1. And then plus, I'll put this plus this one here squared. And that's going to be, I'll put this whole thing like this. Square root of, and then, we'll square it as well. So squared of the square root 1 plus A squared, like that. And then square roots cancel because we're squaring it. This equals to, well, 1 squared plus 1. Yeah, this is 1 squared, that's just 1. Plus 1, and then plus A squared. Well, the 1 squared is just 1. So then this just becomes 2 there. I'll just add those up to 2. I'll just keep this for completeness. This equals to square root 2 plus A squared. And then if we do the next one here, the fourth triangle, we'll use this as the base. That's a new base. So it's, again, we're going to get a 1 squared. So I'll just leave that 1 by itself. So yeah, we'll just keep it like that. 1 squared is just 1. Which is the height, plus this squared, which is just going to be 2 plus A squared. Because we cancel out the square roots when we square it. So in other words, this equals 2, 3. So you can see the pattern now. So this first one is A. Yeah, the first triangle base is A. The second is going to be square root 1 plus A squared. The third is 2 plus A squared, all square root. And the third has a 3. So there's 1, 2, 3, and so on. And then if we continue all the way down, I'm going to make this longer down. Make this down. And then dot, 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 all the way to the end. Dot, 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 all the way to n. We get, this becomes n minus 1 plus A squared. Yeah, so n minus 1 plus A squared. And where? Yeah, so this n minus 1 is always 1 less. So if this is 4, this is 3. So if this is 3, this is 2. So if this is n, this is n minus 1. And now for completeness, let's just get the nth triangle. So this is the nth triangle. Let's just draw it out and get the hypotenuse like this. So nth triangle is going to look something like this. Let's say there's the point P, and it goes like this. Let's go over here. So we know the base of it is the hypotenuse of the previous triangle. So this is P, and this is right angle, like this. Let's do a right angle, better one. So here, just fix that up. So that's a right angle. We know that's the height 1. And then this right here is going to be our n minus 1 plus A squared. and this angle right here is our theta n. And now this hypotenuse, this h, is, I'll just solve this one, it's going to be square root of 1, the side, plus this over here. That's going to be plus n minus 1 plus a squared, because the square roots cancel. This equals 2. This cancels. We're just left with a square root n plus a squared, like that. So that's our h. And now what we could do is, well, let's write this this angle in the function. Well, we know that the tangent of this is, so thus tan of theta n is equal to opposite over adjacent. That's just equals to 1 over adjacent, which is square root n minus 1 plus a squared. And then we could just take the inverse. In other words, theta n is equal to tan inverse of that ratio. So 1 over square root, square root n minus 1 plus a squared. Because remember, we want to see the summation. This goes to infinity. Alright, so thus we wish to show that the following series diverges, basically the summation of this this angle right there. So what we'll write is the summation of, or summation from n equals to 1, because we'll start from the first angle, so n theta sub n, so in other words theta 1, this equals 2, so we have to show that this diverges. So this summation from n equals to 1 up to infinity of inverse tan of this giant number, or this giant fraction right here. Let's write this as 1 over square root n minus 1 plus a squared, then all bracket. Alright, so instead of having this n minus 1, because note here that the only n variable is over here, n minus 1. At n equals to 1, we get n minus 1 equals to 1 minus 1 equals to 0. So it starts off at 0 at this phrase. So we can get rid of that by starting at n equals 0. So this just changes it, just make it neater. So we'll write this as, and get rid of that negative 1 there. From n equals to 0 up to infinity of tan, inverse tan of 1 over square root n, just square root n minus, plus a. 1 over square root n minus plus a squared, like that. So it's the same thing. So at n equals to 0, this just becomes 0. At n equals 1 on this one, this becomes 0. So, and then you increment sequentially, 1 by 1 each time, so it's the same thing. Alright, so we wish to show this converges, but we'll first notice, because it's a bit complicated with this inverse tan and then 1 divided by square root n plus a squared. So first notice that the following series diverges by the limit comparison test. In other words, if we take a series of this inside function, this 1 divided by n, 1 divided by square root n plus a, this diverges by the limit comparison test, because, well, if we got rid of this a, then it was just a p series where p is equal to square root, or 1/2, and that diverges. So what we could do is, well, first notice the limit comparison test. Let's recall this. So recall from our earlier video, the comparison test is, suppose that summation of an and bn are series of positive terms. If the series bn is convergent and all the terms an are less than or equal to bn for all n, then the series an is also convergent. And likewise, if this is divergent and an is greater than bn, all the terms for all n, then an series is also divergent. So that's a regular comparison test. Just to recap, and now the limit comparison test is, suppose that the series an and bn are series of positive terms. If the limit as n approaches infinity of an divided by bn equals to c, where c is a finite number and c is greater than 0, then either both series converge or both diverge. So what we'll do is, so in our case, we're going to compare the series with that inside term, compare the summation from n equals to 1 up to infinity of 1 divided by square root n plus a squared. So compare that with something we know that either diverges or converges, or in this case diverges. Summation n equals to 1 of 1, this is just square root 1, oh yeah, square root 1 over square root n. And this is a divergent series. This diverges, yeah, this is a divergent p series. Remember, p series, the harmonic series is where p is equal to 1. And this is the divergent p series, in other words, p is equal to 1/2. And this is less than or equal to 1. And if it's less than or equal to 1, then it's going to be divergent. And here I quickly teleported to the earlier part where I mentioned this. So the p series, summation from n equals 1 to infinity of 1 divided by np is convergent if p is greater than 1, and divergent if p is less than or equal to 1. Yeah, so it's divergent for this. It's only convergent if p is greater than 1, and divergent for all other cases. Alright, so that's teleporting back here. So we know this is divergent, and now what we'll do is we'll take the limit comparison test. So we'll take this an over this bn right here. So let's take that test right now. So thus, let's put thus limit as n approaches infinity of the an term is this, the one we want, and then this is the comparison one, the bn. And then an is, let's just write this here, 1 over, I'll put this like this, 1 square root n plus a squared over 1 divided by square root n, like that. And then whenever you're dividing by a division, this just goes on top. So then this becomes equals to the limit as n approaches infinity of square root n over, let's put this better, square root n over square root n plus a squared. So that those ones go down there. And now what we have is, yeah, these are all square root. We can just combine them all together into one giant square root. So this equals to limit as n approaches infinity of square root n over n plus a squared. And then what I'll do is times the top and bottom by 1 over n, and then 1 over n, so that we don't have an infinity over infinity situation. Now this equals to, let's see, where should we put it? I'll put it right over, I'll put it right over here. This equals to limit as n approaches infinity of square root, and then the top becomes 1, the bottom becomes 1, then this one becomes a squared over n, like that. And then this part right here, this approaches 1 over infinity, which approaches 0. So then this equals to, well, this is equals to square root 1 over 1 plus 0, which equals to, well, just squared 1, everything's just 1, so it just becomes 1, like that. Alright, so this, limit equals to 1, and if we recall here, so it equals to c, 1 is just a finite number, and it's greater than c, it's greater than 0, then either both series converge or both diverge. So this is greater than 0, so in other words, since this series diverges, this also diverges, because by limit comparison test, they both have to be the same thing. Thus, summation from n equals to 1 up to infinity of square root n plus a squared also diverges, like that. And now we can apply the limit comparison test again, but this time with our original series. So the series we want is this right here. So we'll compare this with this one right here. Alright, so let's compare that. So we're going to compare, I'm going to write the whole thing out. So summation from theta right here, this is up to infinity from n equals 1. This equals to what we had solved it, summation from n equals 0 of right here, the last one we had was inverse tan, and then 1 divided by a square root n plus a squared. Then this is going to be inverse tan, and then 1 over square root n plus a squared, like that. And we are going to compare that with, compared with the series we just solved over here. So compare that with, with a summation up to infinity, and we can start from 1 in this case. start from 1 right here, n equals to 1 of this top part right here. No, I mean not 1. We can start from 0 here. Let's just start from 0. It doesn't matter if we start from 0 or 1. It's still going to infinity. So this one, so it matches up with this part right here. So this is going to be 1 over square root n plus a squared, like that. So we know that this is divergent from earlier. So we know this is divergent from limit comparison test. And now we're going to do limit comparison test again. Thus, limit as n approaches infinity of an, our new an is this. So that's going to be tan, inverse tan of 1 over square root n plus a. I'll divide this by, and then this is going to be 1 over square root n plus a squared, like that. And we can simplify this by, I'm going to let this, let z equals to 1 over square root n plus a squared. So then, in other words, this will equal 2. And now, yeah, this is the same thing as writing, well, limit as n approaches 0. I'm going to write from the right side. This is from the right side. So terms are positive. And then this is going to be inverse tan of z, like that, over z. And this is because, well, as this goes to infinity, we get a setup where this is approaching 0. I.e., z is approaching infinity. I mean, z is approaching 0 as 1 over n plus a is, yeah, or I'll just do that here. Note, so note here, note as n approaches infinity, then 1 over square root n plus a, you're dividing by infinity, this approaches 1 over infinity, approaches 0. In other words, z approaches 0, and it's from the right side, because all the terms are positive. Positive. Positive, like that. And then this right here, well, this equals to the scenario of, well, this is as you plug in this 0 plus, you're going to get a tan, inverse tan at 0 divided by 0. So you get a 0 over 0, which is indeterminate. So we could use L'Hopital's rule. Indeterminate, like that. And just a recall on tangent, inverse tangent recall. So we had earlier, but just again recalls for this question. So if we have, if this is theta, this is y, and let's say we had our tan, this is tan. So this is our tan theta, is that 0? Yeah, so that's our tan theta. Now our arctan, or inverse tan, is going to be something like this. So if this is pi over 2, draw this better. Here, this is pi over 2. This is negative pi over 2. So instead we're going to go, so in the 0, 0, basically we switch the x and y, so 0, 0. Let's do this again. This is pi over 2 at this point. Then you're going to flip it around. So this pi over 2 is 0, so we're going to go 0, pi over 2. And for the red one, I'll draw this in red. So then this is going to be, the asymptote line is going to be across here. This is pi over 2. And this is negative pi over 2 is 0. It's going to be now over at the bottom. Yeah, draw it over here. This is going to be at negative pi over 2 at the bottom. And then as this is going to pi over 2 infinity, instead, it's going to go to infinity and pi over 2. So it's going to go like this. And then this one is 0, 0, still 0, 0. And it's actually below it. Like that. And likewise, it's going to go all the way across there. So, and this is our tan theta, inverse tan theta. And go back to here. And this, again, I'll write this over here, nicer, tan theta. So in other words, at this point is 0. So both these are 0 there. All right, so let's block it out. So again, it's approaching 0 here. So 0, 0, 0, 0, it's indeterminate. So what we'll do is, and I'll also put it over here, 0 over 0, like that. So it's 0 over 0. So then now we could just solve L'Hopital's rule. So using L'Hopital's rule, put this equal sign. So this limit right here is equal to, well, I'll put it all together here. So we're going to go limit as z approaches 0 from the right side of inverse tan of z divided by z. Again, that's 0 over 0. This equals to equals with the L'Hopital's on top, so take the derivative. And the derivative of tan, inverse tan, recall, is just going to be 1 over 1 plus z squared. Now, I'll recall this in my earlier video. So then the derivative of z is just 1. So in other words, this just equals to that. And then when you plug in 0, that just becomes 1 over 1 plus 0, which equals to 1. And this is also greater than 0. Yeah, so thus by the limit comparison test, then this has to diverge as well. Because this is divergent, this has to be divergent, again, as per the limit comparison test. And C is a finite number greater than 0, then either both converge or both diverge. So then they both diverge. Yeah, so that's greater than 0, thus, so we could put this all together, thus the series, which is again all coming back at the beginning, summation from n equals 1 up to infinity of the angle theta sub n is a divergent series. So in other words, it's going to rotate forever, like that. So you're going to have infinitely number of turns around this triangle setup here. So going back up here, so this is going to, when you sum it all up, it's going to go to infinity, like that. All right, let's erase this and continue to go further. And just a note here, so recall the derivative of inverse tan of x from my earlier video. So this is that derivative there from my earlier video here. So d over dx of inverse tan of x is equal to 1 divided by 1 plus x squared. So that's that derivative there. So yes. Anyways, let's continue further. And now let's look at problem 23. So consider the series whose terms are the reciprocals, you're dividing by, of the positive integers that can be written in base 10 notation without using the digit 0. And show that this series is convergent and the sum is less than 90. Now this is why it's called Problems Plus. It's pretty next level. Alright, so let's take a look at the solution. So let's call this series, again, whose terms are the reciprocals of the positive integers that can be written in base 10 notation without using the digit 0. So let's call this series S, and we can group the terms according to the number of digits in their denominator. So S is going to equal to, so the first set, again, has to be without a 0. And in the reciprocals of positive integers. In other words, we're going to have a scenario 1 over 1. That's a reciprocal of 1, it's just 1 over 1. And then plus, and then the second is number 2, positive integer. Divide that, so reciprocal of that. Plus, dot, dot, dot. Then we're going to get a plus 1 over 8. Plus 1 over 9. And this, if we can't get any further, we can't go 1 over 10. That's a 0 inside. So we'll stop this. I'm going to call this segment G1. And now the next one's going to be plus, and now we skip the 10. So it becomes 1 over 11 plus dot, 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 all the way until we get 1 over 99. So we get, so we get 11, 12, 13, 14, 15, 16, 17, 18, 19. Then we skip the 20, then we go to 99. And this one we'll call this group 2 or G2. And so on. The next one's going to be with 3 digits. With 3 digits, the lowest one's going to be 1 over 1, 1, 1 plus dot, dot, dot plus 1 over 9, 9, 9. And then it keeps going on and on. This is G3. And now here I just made it smaller to fit in here, and then we're going to write plus dot, dot, dot so you see the pattern. Alright, so now let's continue further. Now let's count up the number of terms. So now in group Gn, since we have 9 choices for each of the n digits, so each one of these, for example, this 111, each of these could be 9 different choices. In the denominator, there are then 9 to the n terms. For example, I'll just write IE. So for example, for G1 has 9 to the 1, which equals to 9 terms. And this is just, well, 1, 2, 3, ... Yeah, this goes all the way until 9. So this is 9 terms to illustrate it. This is 9 terms. I'll just put that here. We get 9 terms. Alright, and so that's what we have there. And then G2, so the second group has, well, has 2... It has 2 digits in each of the denominator. So then this has 9 to the squared, which equals to 81. Yes, in other words, it's going to have similar to the other one. So the first one's going to be 1, 1, 1, 2, 1, 3, ... until 1, 9. So it's 9 terms there. And then it's going to go, well, the next one's 21, and then ... all the way until, well, 29. And then it goes all the way down until we get 91, ... all the way until we get 99. In other words, this all the way down here, this is how many rows? This is 9 rows. So we have 9 rows of 9, so 9 times 9. 9 rows. And yeah, you can see that. And then similarly to G3, you're going to add another dimension to it. So this has 9 cubed, which equals to, I'm not going to solve that, just go 1, 1, 1 here, then ... all the way until 119, and then we have 1, 2, 1, ... all the way until 129, and then this goes all the way down. Yeah, then this goes all the way down. Total is 9 rows, or better yet, just make it all the way down here. So ... all the way until 191, and then ... all the way until this is 199. So that's 9 rows. So we have 9 times 9, and yeah, I'll just say this is 9 rows. And we gotta do this again. Then do starting from 211 all the way down until 291, and then that's again 9 times. Then do 9 again. Yes, so 9 rows, 9 times again. Yeah, do this 9 times total. Yeah, and then yeah, basically do that each time. So this is 9 times 9, and then times the 9, and then as you can see, this keeps expanding, and so on. All right. So furthermore, each term in the group Gn is less than 1 divided by 10 to the 10 to the n minus 1, except for the first term in G1. In other words, well, let's just look at this. For n equals to 1, we have 1 over 10 to the power of 1 minus 1 equals to 1 over 10 to the 0, which equals to 1. Yeah, so thus we have the first term is 1 equals to 1, which equals to 10 to the n minus 1. But we have the next term is 1 over 2. Yeah, the next one 1 over 2. So notice this one here, 1 over 2. So, but 1 over 2, yeah, is less than 1. So it's less than 1, and then ... we also, then the last term is 1 over 9. It's also less than 1, because you're dividing by a number bigger than 1. So, and then for n equals to 2, what we have is 1 over 10 to the 2 minus 1. This equals to, yeah, so for n is 2, yes, then we'll have 10 to the 1. Yes, in other words, this is just, yeah, 10 to the 1. And what this means is, well, the first term in that group, 1 over 11, this is less than 1 over 10, because you're dividing by a bigger number. And then all the way till 1 over 99, this is less than 1 over 10. And then you can keep doing this on and on. For the n equals 3, it's going to be less than 100, or 10 to the 2. 10 times 10 is 100. So I'll put a etc. etc. Thus Gn is going to be less than 9 to the power of n. That's a number of terms. So I'll put this here. All right, so this is 9 here. This is number of turns. All right, number in each group, number of terms. Yeah, so that's the number of terms, and then basically it's going to be, well, times it by the max size, that is 1 over 10 to the n minus 1. In other words, every single term is less than 10 to the n minus 1. So then we can just multiply the total number of terms. So each group will be less than total number of terms times here, and this is our max size. That's only for G1. I'll put this here as, let's put this as max size here. So that's the number of terms times by the max size. Or better yet, I'll do this. Max size, and it's only for the first term, so everything else is going to be less than it. And yeah, so then yeah, that is that. Then we can simplify this further, or just write the 9n right there as 9 times 9 to the n minus 1. So this is 1, so you can add those up, this becomes 9 to the power of n. This is times it by 1 over, or I'll just divide this by 10 over 10. 10 to the n minus 1, which equals to 9 times 9 over 10 to the n minus 1. And here I just move things around just to make it a less congested. So that's what we have so far. And now note that S, the sum is well, you could write it as summation of from n equals 1 up to infinity of Gn is less than a convergent geometric series, which is this right here. And that's because this absolute value of r is less than 1. So in other words, I'll write this all out. S is equal to the summation from n equals 1 to infinity of Gn is less than the summation from n equals, we'll go n equals 1 of 9, up to infinity of 9 times 9 over 10 to the power of n minus 1. And if you just write this out, if you put a 1 inside, this goes to 0 of a 9 plus, and then put a 2, this is power of 1 there, we'll have a 9 times 9 over 10, and then plus the next one 9, then if you put a 3 there, that'll be squared. 9 over 10 squared and so on. Put a 9 over 10 squared plus dot dot dot, and it keeps going on and on. In this case, this is going to be our A, and this is our R, which equals 9 over 10, which is less than 1. So in other words, this is convergent. Yeah, so it's less than 1, therefore the whole thing is convergent, like that. And then we could write this using the formula. So in other words, S is less than the sum of a geometric series, 1, which is A divided by 1 minus R, and then this equals to A is 9, and then divided by 1 minus 9 over 10, and then multiply this by 10 over 10, so we can subtract, which again, that'll just be 10 minus 9 is 1, so basically we get this equals to 9 over 1 over 10, and move the 10 on top, that becomes, I'll just move this downwards. Or better yet, I'll just move this out of the way and then move this R there, move the convergent over there. So this equals to, move the 10 on top, equals 90. Yeah, so there's our answer. And this is exactly what we were asked to show. We were asked to show that the sum is less than 90. Well, I just put a check mark there and just go review that again. So going all the way back up here. So again, we were asked to show that the sum of the series of the reciprocals of positive integers that exclude the digit 0, and in base 10 notation, show that this series is convergent and the sum is less than 90. So it's convergent and it's less than 90, which is quite fascinating there. Alright, so now we've solved that. Now let's look at problem 24. So then this is the third last problem we'll do, is it's up to 26. Alright, so part A says, show that the Maclaurin series of the function f of x equals to x divided by 1 minus x squared is the summation from n equals 1 to infinity of f sub n times x to the n, where fn is the nth Fibonacci number. That is Fibonacci number defined as, where you have f1, f sub 1 equals to 1, f sub 2 equals to 1, and then the next ones is going to be fn equals to fn minus 1 plus fn minus 2. So you add the next, you add the previous two. For n is greater than or equal to 3. So hint, and we're given a hint to write this function f of x. Yeah, so x over 1 minus x squared equals 2, and this is just the Maclaurin series starting point. So c0 plus c1 plus times x plus c2 times x squared plus etc. where these are the coefficients. And then we're asked to multiply both sides of this equation by 1 minus x squared. And then part B, by writing f of x as a sum of partial fractions and thereby obtaining the Maclaurin series in a different way. Find an explicit formula for the nth Fibonacci number. Yeah, so corrected that spelling mistake. Yeah, so which is quite fascinating stuff here. Alright, so let's take a look at the solution. Let's go over solution to A. So let's follow the hint given. And again, we're asked to show that this, the Maclaurin series of this f of x equals to x over 1 minus x squared is equal to this right here. Summation from n equals 1 to infinity of fn times xn, where fn is the Fibonacci number. And then, yes, we're asked to write this and multiply both sides by this setup over here. Alright, so let's follow the hint. So what we're going to do is, well, we're going to let this part right here, that's just f of x, and this is the Maclaurin series. So we're just going to let it equal to it. Let f of x is equal to, where f of x is, we're given this is 1 minus x squared. Let it equal to the Maclaurin series. So the starting point n equals to 0 of just the power series right here, where a, this is just Taylor series, or just the power series, where x minus a, where a is 0. So we have this equals to, when you plug in c0, we get c0 plus c1x to the 1 plus c2x2, c2x2 plus, and then one more plus c3x3 plus ... Alright, so I here just move things around, made it more compact. So we have this like that, and then the hint says multiply both sides by 1 minus x squared, or in other words, just move this over to the other side. So let that, then what we'll have is we'll have x is equal to, again, move this over to the other side, x is equal to 1 minus x squared times by c0 plus c1x plus c2x squared plus c3x cubed plus ... and then all like that. Alright, so now remove this, and now we're going to multiply this inside, basically multiply this all out, or just expand it all out or FOIL it out. So we're going to multiply this 1 by this, by that, etc. And then same thing for the negative x and so on. So what we end up getting is, well, pretty much 3 series. So we're going to have, when you multiply 1 by everything, we're going to get the same one. So we're going to get c0 plus, plus c1x plus c2x squared plus, and then I'm going to go all the way to the x5, c3 x3 plus c4 x4 plus c5 x5, and then plus ... This goes to plus ... And here I just made it more compact here, and so that's the first one. And then the next one is going to be negative x multiplied by c0. So this one doesn't have the coefficient without the x there, so we can ignore that. It doesn't have the x to the power of 0 side. So we'll line it up over here. So this is going to be negative C0x. And the next one is going to be negative. So it's going to be negative on all of them. But then there's a C1x minus x right here. That'll be negative C1x squared. So this is going to be C1x squared. Notice the pattern. The next one's going to be minus C2x cubed. And then plus, no, it's all going to be minus. Minus C3x 4 minus C4x5. So notice it's off by 1. Just 4, that's 5, etc. And then minus dot dot dot. It keeps going on and on. Then the next one is the next one is x squared multiplied by it, or negative x squared. So negative x squared, we'll line that up with this x squared over here. That's going to be negative C0x squared. And then the next one, C1. Yeah, C1 there. Let's put this like that. Multiply it there. C1, negative C1 x cubed. So you can see the pattern there. And then it's going to be, again, C2x to the 4 minus C3x to the 5 and minus dot dot dot. So we could see the pattern here. And then sum this all up. Yeah, we could sum all this up. We could just view it kind of like a summation right here. I'll put it like this. What we get is x is equal to, well, this C1, or we'll just remove this line actually. I'll just remove this out of there. Alright, so yeah, what we'll do is I'll just drag this down. So we're going to drag this down here. This becomes, and then we'll have an arrow here. So this is x is equal to C0. And now add these two together. So add, just factor out the each of the x terms. This is going to be C1 minus C0 x. And then the next one is all these line up over here. This is going to be plus C2 minus C1 minus C0. And that's going to be x squared. And likewise over here, it's going to be plus, you can see the pattern now, C3 minus C2 minus C1 x to the 3, and then plus dot dot dot. So you can see that pattern. Alright, so now that we have all this, and notice that this whole thing equals to x. So in other words, we're going to have to cancel out all the x squareds and even the constant right here. This has to be 0. Otherwise, it's not going to equal to x. So basically, we're going to compare. So comparing coefficients of powers of x. That is comparing the powers on the left side, which is x to the 1. That's all there is, x to the 1. With the right side gives us, so the only one that's not 0 is a C1 minus C0 is the combination is not equal to 0. So what that means is, well, we know that C0 has to be 0 because there's no coefficient on this side. So this one has to vanish. And then we also know that this right here has to be equal to 1, so that we have 1x to the power of 1. And so we have that, and we have C1 minus C0 equals to 1, and we know that basically solve for C1 by moving the C2 on the other side. So what we get is C1 is equal to 1, or just put a C0 in front, equals to, this equals to C0 plus 1. In other words, this just equals to 1. Because we know C0 is 0. So this equals to 0 plus 1 equals to 1. And then likewise, this right here, the coefficient, there's no x squared, so these have to cancel out. So what we get is C2 minus C1 minus C0. This is equal to 0. Yeah, so that means C2 is going to equal to, we'll move this over to the other side. Yeah, moving this over to the other side, that becomes, well, that becomes all positive. This just becomes C1 plus C0. And this equals to, well, C1 is 1, and then C2 is 0. C0 is 0, so this equals to 1. Alright, and now the next setup is, you can start seeing the pattern. The next one here, C3, so do this better arrow. Like that. Then there's C3 minus C2 minus C1 also is equal to 0 because there's no x cubed on the left side. So we get C3 minus C2 minus C1. This equals to 0. Again, move these over to the other side. We get C3 is equal to C2 plus C1, which equals to Well, yeah, 1 plus 1 equals to 2. And again, you can keep doing this on and on. It's going to be the same thing. Dot, dot, dot. We're going to get a Cn minus Cn minus 1 minus Cn minus 2 equals to 0. And then move this around. We're going to get a Cn is equal to Cn minus 1 plus Cn minus 2. And this is for, yeah, this is for n is greater than or equal to 3. And yeah, we'll make it for this right here, and this is because, or just, this is because, well, we have this one here, the C1 is actually equal to 1 plus C0. So actually, technically, this is still true for n equals n is greater than equal to 2, because you can see here this is C1 plus C0. Yeah, this is actually, yeah, this is true for this too, but the thing is, we're asked to show that it's equal to this setup here. Yeah, so I just made it match this, or the solutions manual just makes it match that, and we'll put this here, or n is greater than equal to 2. So yeah, that doesn't matter there, but just to match up with our, yeah, the our given hint there, or not given hint, given, well, pretty much a hint. Yeah, given that this Fn is the Fibonacci number, just match with the Fibonacci. Yeah, not the hint. Yeah, so continuing further, so thus, yeah, each Cn is equal to the nth Fibonacci number. That is, we could write this as summation from n equals 0 to infinity of, so we've solved Cn, so this Cn is just a Fibonacci number. This equals to the summation from Cn xn. This is equal to the summation from n equals 0 up to n equals 2. I'm going to start from 1, and this is since C0 is equal to 0. So we just ignore that C0. Yeah, ignore the C0, because if you see above here in the Fibonacci number, there is no 0. We just ignore that. So there's no f of 0. Just start from f of 1 is 1. This just becomes redundant. All right, this becomes Cn xn, which equals to the summation up to infinity of, from n equals 1 of fn x to the power of n, like that. Yeah, so that is what we got, and we can box this whole thing there. All right, here, yeah, so we just boxed it in, and yeah, that is the question A. So we showed that the Maclaurin series for that function, this right here, the Maclaurin series of it is equal to this summation from n equals 1 to infinity of the nth Fibonacci number times x to the n, which is quite amazing. All right, let's go further, and now let's look at question B. So question B says, by writing f of x as a sum of partial fractions and thereby obtaining the Maclaurin series in a different way, find an explicit formula for the nth Fibonacci number. So this is where things get a bit interesting. This is pretty amazing. You can actually find the exact formula for this nth Fibonacci number. So solution to B. Let's start with completing the square of the following equation. And this is basically finding the square for this f of x function here. So this right here, 1 minus x squared, just to illustrate how we can get some factors out of there, because we're going to write it partial fractions. So first, recall completing the square just means, recall that completing the square just means writing a function like this, x squared plus bx, so we had like this, plus c. I'll write b and c there just because typically there's an a there, but in this case we don't have anything in front of the x. This is a negative one, we could just make it all negative. So this equals to x plus d. So the idea is to make it into a square. So like that, x plus 2 squared, where this equals to x plus d times it by x plus d. And if you FOIL this out, we're going to get a scenario such as x squared, and then plus, now if you multiply, yeah, so x times x squared, x times d is xd, or dx, and then d times x is dx, and then d squared. So in other words, you're just going to get a 2dx, when you sum those up, plus d squared. So then the idea is, well, this b So this right here has to match this. So that means that we have b is equal to 2d. And then this right here has to match this right here. So in other words, C is equal to d squared. Yeah, so b equals to 2d, c is equal to d squared. All right, so in our case, so that's what we have. So now what we're going to do is recall or consider in our case negative of 1 minus x squared, and write this as equals to, well, equals to the negative x squared becomes positive, plus x squared plus x, and then we just have a negative 1. So consider this right here. So this right here has its b is equal to 1. So we have b is equal to 2d, which equals to 1. So in other words, solve this over, we get d is equal to 1/2. So if d is 1/2, then the c has to be, well, d squared, so 1/4. So, or 1/2 squared. So in other words, if that is that, so then we get our c is equal to, this is right here, but yeah, this is not c. That is, well, yeah, it's obviously not c. So our c is supposed to be, c is equal to c is equal to d squared, I mean. So we know what d is. C equals to d squared, which equals to 1/2 squared, yes, square all that, which is equals to 1/4. And this is not equal to negative 1. Yeah, so it's not equal to negative 1, so it's not equal to this. So what we'll do is plus and minus a 1/4. So plus 1/4 minus 1/4. Yeah, so then that means then this and this is completing the square, where the square is going to be over here, x plus d all squared, where d is 1/2. So thus what we'll have is negative, yeah, that's what we have. Well, not negative, because we already solved that over here. Thus x squared plus x minus 1 is equal to, now this is going to be, again, when we add 1/4 and then subtract 1/4, we're not changing anything. That's just cancel out, it becomes 0. So this becomes, and now I'll write this out as x plus 1/2 squared, because we complete the square. So that part is equal to x plus d squared, where d is equal to, equals to 1/2. Yes, in other words, this is our d equals to 1/2, like that. And now this is going to be, yeah, so we have this, and now this minus 1 and this minus 4, we can add those up. 1 is just 4/4, that just becomes minus 5/4. Just skip the step, just do that. Alright, so that's what we have now. And then going even further, what we'll notice, well, what we can write is write this as a square. So this is a square here. Now we can write this as a square. So then we can have some more, basically, algebra here. So what we'll have is this equals to this equals to x plus 1/2 squared minus, this is equal to, I'm going to write this as square root 5 over 2 squared. So square root 5 squared is just 5, and then square root 2 is just 4. I mean, the square of 2 is just 4. So we're not changing anything. And now what we'll do is recall whenever you have a scenario such that you have squares, recall that if you have a scenario such that you have a plus b times it by a minus b, that's where we get cancellations. So when you have this square and there's a square, this equals to, when you multiply this out, so this a times a is a squared. So that's an a squared. And then a times negative b is negative ab. And then you're going to have to do that with this over here. Plus b times a, that's just plus ab. So in other words, those will cancel. And then you're left with plus b times negative b, that's going to be negative b squared. So in other words, we could write this as this. So that is an interesting setup. All right, so that's what we have is, I'll write here as thus. Thus, this whole thing becomes, well, this first, right, let's write the beginning one. X plus x minus a is equal to, well, this squared, that means we can put this, if this is a, the inside. So that's a is x plus 1/2. So this is our b. This is our a. And again, not to be mistaken with the b over here, but this is just over for this setup here. Or better yet, I'll remove this and remove this. Let's go back. Okay, I'll just delete this like that. Delete that. I'm going to put this arrow right here. This a is on the other side. So this is our a, and then this is our b. So that means, well, we can write this as this setup here. Instead, we'll write a plus b. So this will be x plus 1/2 plus b plus square root 5/2 times it by, and then times this by x plus, so that's a minus b. So minus square root 5/2, like that. And this can add these up, and we're going to get a scenario. Just add those same common denominator, x plus 1 plus square root 5/2 times it by x plus 1 minus square root 5/2, like that. So that's what we have. And so now we have factors of this x squared plus x minus 1, which is, again, that's just the same thing as negative. That's a negative of this, 1 minus x squared. And then we have our, that's our f of x. So this is this part right here. So we'll have a negative x over those factors. And then we can write this as partial fractions. All right, so now we can write out f of x as, so let's write this out. So f of x is equal to x over, and this was 1 minus x squared. But now take out a negative, this equals negative x over x squared minus x minus 1. And then this equals to negative x over our factors. X plus 1 plus square root 5/2. And then times it by x plus 1 over square root 5/2. I mean minus square root 5/2. Like that. And here I just moved things around, just made it more compact here as well. So we have this, and now the factors in the denominator here are linear, so the partial fraction decomposition is, and it's linear, so in other words, there's no x squared, x cubed, etc., or square roots, or anything like that. We just have x to the 1. This is the highest power of x. So what we get is, we could write this in partial fraction decomposition form. So let's just write this out. Negative x of x plus 1 plus square root 5/2 is equal to, times it by, at the bottom, the x plus 1 minus square root 5/2. This equals to, alright, so this equals to, so now we have those factors, so so in partial fraction decomposition, it just means, well, if you have factors like this, you're going to have something that creates them that are composed of each separate factor. So this could be written as a over, pick the first one, a over x plus 1 plus square root 5/2. And then the next one is, well, we don't need a bracket because nothing else multiplying, plus b over just regular like that. Yeah, over bx plus 1 minus square root 5/2. And now what we'll do is, well, multiply both sides by this. So multiply it or move it over on the other side, and we're going to get a bunch of cancellations. So we get negative x is equal to a, and then these ones will cancel. So this will cancel, and we're left with this x like this, x plus 1 minus square root 5/2. And then plus on the b side, this one will cancel with this. So we're left with b, or we're not dividing, so put it here, b times x plus, so this will cancel, we're left with the positive one. 1 plus square root 5/2, like that, and square root 5. Alright, so now that we have this, what we could do now is, well, we could write if if x, so right here, we can get rid of this a by writing x equals to the negative of this one. So if x equals to negative 1 plus square root 5 over 2, yeah, then what happens is, well, a vanishes. So then this becomes 0, that gets out of there, and then we're just left with b. So then we can solve for b. So we get a negative of this, so negative of negative 1 plus square root 5 over 2 is equal to b, b times, and then we'll have inside there negative 1 plus square root 5 over 2, and then plus 1 plus square root 5 over 2, and then all bracket like that. And now we could just simplify this, or better yet, just cancel all the 2's. There's everything, there's a 2 everywhere, divided by 2. So cancel all that, and then get rid of this minus, and then this one becomes negative. So this becomes 1 minus square root 5 equals 2. So let's put another arrow. Let's make it like this. This becomes, 1 minus square root 5, and then we have a b right here. And then this right here, well, this same common denominator, well, those are all canceled anyways. And then this subtracts, so we have a negative 1 plus 1, that cancels. And then we have 2 of these square root 5s. In other words, we get, put that in front actually, 2, and then times it by square root 5 of b. So this means that b is equal to 1 minus square root 5 over 2 square root 5. And I'll just box this in. Alright, so that's for that. I'm just going to put a line here so that just to show that we are doing ifs now. So let's solve now. So that's if x is that. Now if if x is equal to, we'll make the b vanish now. So if x is equal to negative, right here, 1 plus square root 5 over 2. Yeah, so we'll put that in. So if x is equal to negative 1, negative square root 5 over 2. So the difference is this was negative 1 plus, because there's a negative there, square root 5 over 2. This one just becomes negative. Like that. If it's that, then what we get is, well, b vanishes. B vanishes, so this becomes 0. And now we're just left with this a right here and this negative x. So we get negative x, which is, well, x is here. Negative of negative 1 minus square root 5 over 2 is equal to a times that. So equals to a times it by, and put a bigger bracket, times it by negative, so this is going to be our x, plus 1 minus square root 5. So this is going to be negative 1, negative square root 5 over 2, plus 1 minus square root 5 over 2, like that. And all the 2's cancel, as always, so that cancels. And then get some simplification. This becomes, all these negatives cancel, it becomes 1 plus square root 5, and this equals 2. And now this negative 2 plus 1, negative 1 plus 1, those cancel. And now we're left with a negative square root 5 and a negative square root 5. So that means there's 2 square root 5s, but they're both negative. So we'll get a negative 2 square root 5. Let's make it so it's not like the 2 is the square root number. This is, negative 2 times square root 5 of a. So in other words, a is equal to, so a is equal to 1 plus square root 5 over negative 2 square root 5. Let's put the negative on the bottom there, just because the solution manual did that too. Alright, like that. So we can box this in. Alright, so thus putting this all together, we get, and I'll just put a line, thus, we get our x over 1 minus x squared. Remember, this equals to our, if we go back up, it equals to, scroll above here, so we have x over 1 minus x squared. 1 minus x squared equal to negative x over x squared minus x minus 1 equals all this, where this equals to a over this, partial fractions. And now we solved for a and b, so we can write it over this. equals 2a, which is 1 plus square root 5 over negative 2 square root 5 all over, and then the a, over this one here, x plus, and then this is a plus, 1 plus square root 5. So this is going to be x plus 1 plus square root 5 over 2, like that. And then this is going to be plus, this is our a, so this is our a right here. I'll just put this here. Or we can get rid of the line then. This could be our a right here. This is our a. Then plus, now our b is going to be equal to 1 minus square root 5 over 2 times square root 5. So 1 minus square root 5 over 2 square root 5. And this is our b. Like that. I'll draw this, the other one, this parentheses sign. So this whole top numerator is a and this one's b. And this is over x plus, the other one's going to be 1 minus square root 5. Yes, we remember this. Over 2, and let's just double check that quickly. And yeah, there is right over here. So x plus 1 minus square root 5 over 2. So that's what we have there. And here I just move this down a bit just so I can draw this line, this separator line, just so that we are onto this now. And now what we can notice is, well, in this top part we have this 1 plus square root 5, and this bottom has a 1 plus square root over 5. And there's also a 2, there's also a 2. So what we'll do is multiply the top and bottom of this by 2 over 1 plus square root 5. And in this one, same thing, but instead of plus, we do a minus, because there's a minus square root 5, there's a minus over there. So what we'll do is write this as equals to 1 plus square root 5 over negative 2 square root 5. Divide this by x plus 1 plus square root 5 over 2. Alright, yeah, so here I just made it a bit smaller. I'm going to multiply now the top and bottom by 2 over 1 plus, write this neater, so 2 over 1 plus square root 5, then divided by 2 over 1 plus square root 5, like this. So then what happens is, well, this cancels, this cancels, this cancels, and then this whole part cancels, it becomes 1. And then we'll do that after. Also, this cancels. So what we get is there. And the next one is if we look at this one here, let's write that 1 minus square root 5 divided by 2 square root 5 over like this, over x plus 1 minus square root 5 over 2. Yeah, like that, and then multiply this one by 2 over 1 minus square root 5. And then this is 2 over 1 minus square root 5, like that. Let's write this a better 5, like this. Alright, so then what happens is, this whole thing cancels, this cancels, or not the whole thing, just a 2 cancels. 2 cancels. Yeah, 2 cancels, and then this whole part cancels, this cancels. And now this one cancels with this part here, and then what we're going to be left off with is equal to, yeah, equals 2. Well, this one we're just going to be left with the 1 over negative square root 5. So this is going to be negative 1 over square root 5. But negative, just move the negative out of there. And then divide this by, this right here becomes, yeah, this becomes, and I'll write this, I'll multiply this one in first. I'll move that here, plus, and then we'll have an x, x or 2x. We'll have a 2x over 1 plus square root 5. That's on this side here. And then plus, the next one here is going to be 1 over square root 5. 1 over square root 5, and again, move the 1 in front, because this all cancels, and we're going to be left with the 1. Move that in front. 1 plus, and then a 2x, 1 minus square root 5, like that. So that is what we have so far. And here, let's move the 1 over 5s down, or 1 over square roots down. We'll move this, I'll call this right here negative 1 over square root 5, like this. Yeah, times it by 1 over 1 plus 2x over 1 plus square root 5, like that. Alright, here I just move that over to this side here because we're going to need more space. And then the next one's going to be plus 1 over square root 5. And the reason I'm writing it like this is, well, if we notice, we have two geometric series right here actually. So 1 plus 2x over 1 minus square root 5, like that. Alright. Alright, so now, yeah, notice that, or note that the above two fractions are in the form of the sum of a convergent geometric series. In other words, this right here is the sum of a geometric series, and this is 2. Because you have that 1 minus 1 divided by 1 minus r. Like that. And this. So this means we can write them as a geometric series. So again, recall geometric series. If you have the summation infinity like this, yeah, this equals 0 from n equals 0 up to infinity of arn, where this just equals to, remember, a, so n is 0, then plus r, n1, ar1 plus ar squared plus dot dot dot. This equals to just 1 over 1 minus r. And this is 4, absolute value of r is less than 1, like that. And here, I just put that in there right here. So absolute value of r is less than 1. And in our case, what we get is, yeah, so I'll put that in here. So thus, in our case, we have x over 1 minus x squared is equal to, well, remember this part right here, that's the sum of it. So x over 1 minus x squared is equal all to this. But now let's write this as a sum of a geometric series. So this equals to negative 1 over square root 5, and then times it by the sum of, or from n equals to 0, of now r, well, ar. So in this case, we have a is 1. So in both cases, we have a is 1. And then r is negative of this. So this is going to be a negative 2x over 1 plus square root 5 to the n, which is quite fascinating. So we can write that as a series. 1 plus square root 5 over to the power of n. All right, so in both of our cases, we have a equals to 1. And here, this is our r. That's the r for this case. And then the next one is, this is going to be now plus 1 over square root 5, this, yeah, it's just a constant over here, times it by the summation up to infinity from n equals to 0. And then this is going to be, a is also 1. And then this one's going to be negative of this one, is going to be our r. So negative 2x, so we'll put 2x, yeah, negative 2x over 1 minus square root 5, like that. And then, yeah, that is our negative r, yeah, that's our r right here. So this is our negative r, let's put a negative there, and this is going to be n, and this whole thing is our r. So there's our r for this case. So we got two series there. Alright, so now that we have this, we can simplify this by combining the series all into one, and still factor out the 1 over square root of 5, but move this in front and then make this subtracted inside there. So what we'll do is this equals to 1 over square root 5, and then summation up to infinity from n equals to 0 of, and then move this forward because it's positive and this one will be negative. So we're going to have, and also factor out the x n. I'm going to factor out the x out of there, so that's going to be both x to the power of n. So we'll have a giant function like this, negative 2, actually no, 2 is on the front. Actually no, this is correct, yes. We'll have a negative 2 over 1 plus square root 5, and just put the bracket around. This is going to be power of n. And actually we're going to do this one first. This can be, because this is positive, so that's positive right there, and then we'll subtract it by over here, so that's a negative 1. So subtracted by, and then this is going to be negative 2 over 1 plus square root 5, and that's what we have here. And what I'm going to do is, yes, power of n, and then this is all times it by, so we factor out the x to the power of n there, like that. Alright, so now that we have this, we can do some more simplifications, and I'm going to write this as equals to 1 over square root 5, and then again times it by summation up to infinity of, I'm going to start from 1, because when you put in n is 0 here, this becomes 0, this becomes this to the power of 0, which is 1. And this one becomes 1 minus 0, and this is all, then this one is just 1. So in other words, we get a scenario of, I'll just put it here, I'll say n equals 0 term is 0. In other words, we get a scenario of 1 minus 1, power of n, yeah, 1 to the 0, power of 0, equals to 0 there. So we just have it to the 0 there. Or I'll just have this, this to the power of 0. I'll just have a number 0 minus number 0, like that. And yeah, it all goes to 0. So that's this part right here to the power of 0, and everything else is 1. And this one will just vanish because you're multiplying it by 0. So that is the power of 0, like that. And now what we'll do is, we're going to multiply the top and bottom to get the same common denominator, and also multiply this n inside, and just do this all in one go. It should be pretty straightforward, especially if you've gotten this far in the video. You should do this in your sleep. So this will be the bottom. Is going to multiply, yeah, to get the same common denominator. So I'm going to multiply this top and bottom by 1 plus square root 5, and then this one times it by, and then to the power of n, and this one multiplied by top and bottom 1 minus square root 5 over, yeah, on the top and bottom. So this becomes 1 minus square root 5 times it by 1 plus square root 5, and then this is power of n. This is n, power of n, like that. Alright, just fix that up, and now this one here, we're going to have a negative 2n, and then the top's going to be the other one that doesn't cancel, and that's going to be 1. Actually, no, we don't actually cancel anything. It's just going to be just this part right here. Because we're getting the same common denominator. I'm just skipping a step. Just to, otherwise, this will take us forever. So this will be like that. And then minus, again, negative 2 to the power of n. Times it by the other one, which is this one here. We're multiplying top and bottom. So we get the same common denominator. 1 minus square root 5, like that, to the power of n. And then all of this is going to be multiplied by x to the n. And now, continuing further, I'm going to factor out this minus 2 to the power of n out of there. So this equals to 1 over square root 5. So put the negative here. Oops, erase it. Square root 5 times it by the summation up to infinity from n equals to 1. And then we'll factor out the negative 2n. And then this is going to be multiplied this by... And I'll see, just to get different, I'm going to put a bracket like this. Like that. Or actually, I'll just put a giant bracket. Alright, and now we're just going to factor it out. This is going to be 1 plus square root, like this. Yeah, put that bracket inside, power of n. 1 plus square root 5, power of n, minus, and we factor out this negative 2 to the power of n out of there. And this is going to be now 1 minus square root 5 to the power of n. Close that bracket. All divided by, now this one here, this will equal to negative 2 to the power of n times by 2n, and I'll illustrate that in a bit, and then times it by x to the n. And I'll put a note here, note, or put this here, yeah, right here, note, actually, yeah, this takes too much space up, I'll just put a note here. Note that, so if we look at this one here and FOIL it out, we get 1 minus square root 5 to the n times it by 1 plus square root 5 to the n. This equals 2, you could just write this as bracket 1 minus square root 5 times it by 1 plus square root 5, and then this is all to the power of n, like that. And then we could just FOIL this out, so 1 times 1 times plus 5, and then this one here and this one here will cancel as per earlier. So what we're going to get is this equals to 1 just for completeness, so erase this, equals to 1, 1 times 1, and then we're going to have plus square root 5, and that is, 1 times square root 5. And then we're going to have over here negative square root 5 times 1. Yeah, so let's write this. Negative square root 5 times 1 is going to be negative square root 5. And then negative square root 5 times times plus square root 5, that just becomes plus 5. Or negative 5, actually. Yeah, negative 5. The square roots cancel, because that is just squaring it. So then this cancels, and again, this is all to the power of n. I'll put a giant bracket here. Power of n. So this equals to 1 minus 5 to the power of n, which is, I'll just put it for completeness, 1 minus 5 to the power of n, which equals to negative 4 power of n, which equals to, I'll just write this here, so because we want to cancel negative 2n, so this is going to be equals to negative 2 times 2, and this is going to be, or negative 2 times 2, just like that. I'll just put it negative 2 like that, power of n, which equals to negative 2 power of n times by 2n. And this is what we get here. Yeah, so this is this right here. Is this one. I'll just put is this. So that is this. Like that. And then we can do a bunch of cancellations there. So wrote it like that so we can do some cancellations. So this will cancel with this. So all that is to cancel. Alright, so thus, put it all together, we have, so thus, this whole thing, remember, is just equal to x over 1 minus x squared. That's our f of x. So what we get is thus, and bring this down, thus we get x over 1 minus x squared is equal to 1 over square root 5. Yes, 1 over square root 5, like here, times it by the summation from n equals 1 to infinity of this whole thing. That all cancels out. So what we're going to get is, it's just that this is 1 plus square root 5 to the power of n minus 1 minus square root 5 to the power of n, and then divided by 2n. So we just need one bracket like that. 1 plus square root 5 over n minus 1 minus square root 5, like this, power of n. Alright, let's erase this. All over 2n, to the power of n, because we cancel that negative 2n out to the power of n. Divide this by, times it by x to the n. Yeah, so that is what we have here. And this series right here, well, this is just our f of x now. And if we recall how we solved it in part A, so if we scroll all the way to part A, we got it over to here. So we wrote it as a Maclaurin series, and it equals to summation from n equals 1 to infinity of fn times x to the power of n, where fn is the nth Fibonacci number. And again, so if we go back to the question, that's what we had for here. So this one, f of x equals to, is this. So we showed that it's this. And that was just the Maclaurin series. So, so we wrote the Maclaurin series out, we wrote it out. So in other words, this right here is equal to the summation from n equals 0, from n equals 1 to infinity of fn, which is the nth the nth Fibonacci number. And this is from part A. So that's from part A. This is, that's just our f of x. With a better summation symbol. Yeah, so since this series is equal to that from part A, it means that we have an explicit formula of the nth Fibonacci number, or explicit formula for Yeah, for the nth Fibonacci number. And that is actually quite amazing. So hashtag amazing. So now this needs to equal to all of these coefficients there. Yeah, so we'll just have to put this 1 over square root 5 back inside. So then this means that Fn is equal to, and this is going to be all of the inside. So let's write this out. This is going to be 1 plus square root 5 to the power of n minus 1 minus square root 5 to the power of n. All this divided by 2n times by square root 5. To bring this fraction back inside here. And that is our explicit formula for the nth Fibonacci number, which is quite amazing. So this is Fn is equal to this, and we can box this out. Alright, so now that we have this, and now we can do a quick calculation check to make sure it's actually correct. So here's the first 6 Fibonacci numbers. So they are, so you have the 1, so the first one is just 1, second is 1, then you start adding up. Then you have 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, then 5 plus 3 equals to 8, and this is the 6th one. So this is 1, 2, 3, 4, 5, 6. So calculating the 6th Fibonacci number, let's put it like a 6th Fibonacci number yields, so we'll have F6 is equal to, and let's put this all in there. So we have 1 plus square root 5 to the power of 6. So here's this right here, to the power of 6. 1 plus, square root 5 to the power of 6. So in my OneNote calculator, you can just write SQRT, and then subtract this by 1 minus square root 5. So 1 minus square root 5, and then to the power of 6. Then all divided by 2 to the power of 6 times square root 5. And if you plug this in, what we get is, well, let me just delete this. And then press space, automatically calculates. And then here rounds up, calculator rounds during calculation, so this is correct. So this equals to 8. And this is 8.001. So yes, so that's an error. But yeah, so it's 8 is correct, which is quite amazing. Alright, so now this brings us to the second last question of this entire problems series. So problem 25, and this one is says, let u equals to 1 plus x cubed divided by 3 factorial plus x to the 6 divided by 6 factorial plus x to the 9 divided by 9 factorial plus ... And then we're asked then we're given v equals x plus x4 to the divided by 4 factorial plus x7 divided by 7 factorial plus x10 divided by 10 factorial plus ... And then w starts with x squared right here, x squared divided by 2 factorial plus x5 divided by 5 factorial plus x8 divided by 8 factorial, etc. And if you take a look at this pattern here, if I take the derivative of w, we get v. So this 2 goes down, and then the factorial gets out, lose a power. And if I take a derivative of v, we get u. So we can show that they're related by integrals and derivatives. So, and also we're asked to show, so that's what we're given. Then we're asked to show that u to the power of 3 plus v to the power of 3 plus w to the power of 3, and then subtract by 3 times u times w times v equals 1. So in other words, so we can actually do implicit differentiation here, and then also take derivative of this and then make them all related and throw that in there. So that is what it looks like we should be doing. Alright, so now let's take a look at the solution. And again, so we're going to be taking derivatives of this and then do implicit differentiation here. But first, before we do that, we need to be able to, show that we can take derivatives. So let's first use the ratio test, which is a pretty smart way of determining that it is convergent for all values of x there, to show that the series for u, v, and w have positive radii of convergence, i.e., I believe what they're saying is r is greater than 0. So it's not, r is not equal to 0. Otherwise, that would be convergent only at one point, at the power series x equals a. So that we can do term by term differentiation And let's just take a look here. So here's a ratio test. Recall from my earlier video. If so, we have three cases. If the limit n, the limit as n approaches infinity of an plus 1 divided by an is equal to L, which is less than 1, then the series summation from n equals 1 to infinity of an is absolutely convergent and therefore convergent. If that limit is instead equals to L, and this is L is greater than 1, or the limit goes to infinity, then the series is divergent. If, however, the third one is if this equals to 1, the ratio test is inconclusive. That is, no conclusion could be drawn about the convergence or divergence of the summation of an, or the series an. All right, so let's start off with u, and let's write this here. So in our case, we have, let's write a line like here. So u equals to 1 plus x cubed divided by 3 factorial plus x to the 5, actually to the 6. Let's go back up here. So this is x to the 3, then the 6, 9, etc. So it's separated by 3. This is going to be x6 divided by 6 factorial plus the next one x to the 9 divided by 9 factorial plus dot, 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 etc. And here's remove that line, just put this line here. So then we have here, and this goes all the way to, the last one is going to be, well, this is a factor of 3. So these are going to be x to the 3n. When n is 0, it's 1. And well, when n is 0, the whole thing goes to 1. And this is divided by 3n factorial. And yeah, so when n is 1, we'll have 3 times 1 is just 3. And then 3 times 1 is just 3. When n is 2, we'll have 3 times 2 is 6. And the bottom is, 3 times 2 is 6. Factorial. Like this. So let's take the limit. Limit as n approaches infinity of an plus 1 over an, the absolute value of this limit. All right, so this right here, let's fix that up. All right, this equals to the limit as n approaches infinity, and let's plug that inside. So we're going to have absolute value of, and then we're going to have x to the 3n plus 1. So then plus 1 times 3n, times 3 is just going to be 3. Whoops, get rid of that 1 there. 3 right there. Because if this is n plus 1, so 3 times n plus 3 times 3 times 1. So then it'd be 3n plus 3 all over the bottom is 3n times n plus 1. 3 times n plus 1 is just 3n plus 3 factorial. So that's this. And then we're going to be dividing by, in other words, we're going to have this on the opposite side. So we're going to divide by an. All right, let's just write this here. And then the an will be at the bottom. Will be, this is just x to the 3n. And then divided by 3n factorial. 3n factorial. All right, just put absolute value sign there. All right, so now we have this. And notice there's a 3n here minus 3n. So this just becomes x to the 3. So this equals to limit as n approaches infinity of, and then we'll have an x to the 3. And also there's a 3n factorial. I'm going to go x to the 3 times it by 3n factorial. But now this 3n plus 3 factorial is the same thing as writing, well, 3n plus 3 times it by 3n plus 2, and times it by 3n plus 1, and then times it by just 3n factorial. Like that. So we do all that, and this just cancels out with this. Yeah, so then the n cancels out there, so all we're left with is this 3n plus 3, 3n plus n plus 2, etc., 3n plus 1. In other words, this whole thing at the bottom goes to 1 over infinity. So you're going to be dividing x3, whatever x is, divided by infinity. So for all values of x, doesn't matter. This is going to be approaching 0. Doesn't matter what x is, this is going to approach 0 there. So in other words, this limit is equal to 0. And I'll box this in, which is less than 1 for all x. Doesn't matter what x is. For all x. So Yeah, so it's for all x. In other words, this is less than 1, so it's equal to L, less than 1. Then this is absolutely convergent and therefore convergent for all x. So we could write converges for all x. So converges for all x. And this is our u. And I'll just put it down like here. So u, so u converges for all x. Remember this whole thing was u, and we didn't limit the ratio test for this u there. And if we do that for the other ones, it'll be the exact same thing. All right. So u converges for all x. All right. So it converges for all x, and similarly, the ratio test converges for all for v and w for all x. Or I just reworded it to be a bit more grammatically correct. So similarly, the ratio test shows that v and w also converge for all x, because the other ones are doing the exact same thing. So v is this right here. And then you're going to have pretty much the exact same thing. All you're doing is changing this power. Instead of x to the 3n, you're going to have a slightly different, and they're all going to just cancel out because they're pretty much identical in form, just the different powers and factorials by number only. So thus, we can now differentiate each of these series, or each of the series. All right. So what we'll do is we could do term by term differentiation. So let's write u again. U equals to 1 plus x cubed over 3 factorial. Remember, it's factor of 3 everything. All right, this becomes like that. Plus x to the 6. X to the 6 over 6 factorial plus x to the 9. 9 factorial plus dot dot dot. And now du, so du over dx, take the derivative, equals to, well, the first one's going to be 0, the next one's going to be 3 goes down, and we remove a power. There's a 3 factorial, like that. All right, just put a factorial there, and the next one is plus, put the 6 down, 6x to the 5, and this is going to be 6 factorial. Plus the 9 goes down, x to the 8, subtract 1, now we have 9 factorial plus dot dot dot. And then what happens is, well, this cancels with this, we're left with a 2 factorial and so on. Do that with all of the others. So this becomes just x squared over 2 factorial. Plus the next one is, well, similarly, you're going to have this cancels with this, 5 factorial. This becomes x to the 5 over 5 factorial. Plus the next one, this cancels with this, 8 factorial. This becomes x to the 8 over 8 factorial. Then plus dot dot dot. Now if we scroll up to our setup here, so if we go all the way back here, right here, so u is this, and then derivative becomes x squared. So this becomes w. So the number is x squared. So this x cubed, this one goes to 0, this x cubed goes down, subtract the power, get x squared. Then we have this, x squared over 2, and then 2 factorial. Yeah, so there's an x8, 8 factorial, and so on. So it's exactly that. So this is equals to w. This equals to w there. All right, so that's w. So now we could just take the derivative of this one here. So that's w. I'm going to move this down here. And so we're going to do dw over dx. And instead of writing it down again, well, we have it already here. So dw over dx is equal to, bring that 2 down, be 2 over 2 factorial times x to the 1, then plus 5x4 over 5 factorial plus x to the 7. I bring the 8 down, 8 over 8 factorial, and then this is x to the 7, and then plus dot dot dot. So in other words, this becomes x to the 1, those 2 factorial cancels, and then we're left with, here is going to be x to the 4 over 4 factorial. You have a bunch of cancellations there, like this. Then plus x to the 7 over 7 factorial, plus dot dot dot. And now let's take a look at what this one is. So the dw over dx, that's x, and then x to the 4, then we have x to the 7. So that's equals to v. So we have x plus x to the 4 divided by 4 factorial plus x to the 7 divided by 7 factorial. and so on. This keeps going on and on. Yeah, so then that is v. So going back here, this equals to v. Alright, so what I'm gonna do is I'm gonna box this in. So du over dx is equal to w, dw over dx equals to v. And now, so that's v, so let's take the derivative of this one now, and this should be u. So d over, dv over dx, take the derivative of this one, it's already written down, so we don't need to write it again. That's just going to be 1 plus, this one, the 4 goes down. We have x to the 3 over 4 factorial plus 7x6. And bring that, the 7 down, the power down 1. And then over 7 factorial, then plus ... And we keep going on and on. In other words, we get it cancellations. This becomes 1 plus x to the 3 over 3 factorial plus x to the 6. Again, those are factors of 3 now. In other words, we are becoming u. Okay, over 6 factorial, and this plus ... This equals to u. And we can see that that is just our starting point. So that's u right here. So we can keep taking derivative and just cycle through them nonstop. So that's there, and just scroll back up. And yeah, just to show. So u is 1 plus x cubed divided by 3 factorial plus x6 divided by 6 factorial, and so on. Alright, so going back here. So u is x3, yeah, so 1 plus x cubed divided by 3 factorial plus x6 divided by 6 factorial, and so on. Thus, put it all together. Thus, we have u prime, or the derivative, is equal to, u prime is equal to w, equals to w, and then v prime, so we have this, and I'll put v prime is equal to, derivative of v prime is equal to u, so this derivative dv over dx, just write it as u prime, v prime, and then finally, w prime is equal to v. So this one is equal to v. So yes, that is what we have. Box this out. Alright, so now let's differentiate the left-hand side of the desired equation, because now we know all the derivatives and so on. So if we go back to the desired equation, we were asked to show that this right here, u cubed plus v cubed plus w cubed minus 3uvw, or 3uwv, is equal to, is equal to 1. Actually, the way it was written is better this way, uvw, so that's just better order, uvw, and then 3uvw, anyways, equals to 1. So we show that it's equal to 1. So what we'll do is we'll take this and take the derivative, and then see what it equals to. So, thus we can differentiate each of, actually we have one there. So let's differentiate the left-hand side of the desired equation. So what we'll do is d over dx of u cubed plus v cubed plus w cubed minus 3uv. So 3uv right here. uvw equals to, alright, so this equals to, well, let's take derivatives, the 3 goes down, you get u squared, and then we're going to have to multiply by the, using chain rule, again, u prime, the inside, like that. So that's u prime. And then the next one is same thing, 3v squared v prime, and then plus 3w squared w prime. And now the next one is, well, we need to do this one here, so we're going to just make some room, subtracted by 3, I'll just factor that out, and then we're going to use the product rule. So derivative of uvw is equal to u prime, and then vw, plus, now derivative of the other one, so this would be u vw, I know v prime times w, and then plus uw, uv, yeah, so you have to sum up each one derivative separate, then w like that, w prime, like that. And I'll just put a sign here, so recall, this is the product rule, like that. Alright, so now let's plug in all of our variables inside. So this whole thing is equal to I'll make some room here. Actually, we'll have some room here. So so equals to 3u squared times u prime. U prime is w. So we'll have 3u squared w plus, and we can actually just factor out all that 3's there. So yeah, because it has a bunch of 3's everywhere. So let's take this out. So it's going to be 3, and then put a bracket like this. And yeah, we will get 3u. This is u squared w. So u prime is w. And the next one is plus v squared. And then v prime is u. Plus, and then we'll have w squared. And then that's w prime is equal to v. Like that. So that's what we have there. And then minus this setup over here. And yeah, we're going to need some more space here. Alright, move this down here. And this equals to, yeah, so wv. And then we're going to have, we subtract it, yeah, so we factor out the 3 out of there. We're going to have a u prime is w times by v, vw. So what we have, the w is theirs already. So we'll have a v w squared, and then plus u w, and then v prime is u, so we'll have a u squared w, and then now here u v w prime, w prime is v, so we'll have a v squared there, u v squared, like this. So if you take a look at this, what we can cancel, and this is subtracted by, so we have a u squared w, this cancels with this. We have a v squared u, so this is a v squared, u squared v, that's the same thing, those cancel. And then we have a w squared v, w squared v. So those cancel, and the 3 is, 3 multiplied by 0. So in other words, all these cancel, this all equals to 0. Like that. Alright, so if it's equal to 0, that means then the integral, if we take the integral of that, basically what it's saying is, well, this means that u3 plus v squared, u to the 3 plus v cubed, or v to the 3 plus w cubed minus 3u v, this has to equal to c, which is a constant. So we have to have this. Yeah, we have to have this because the derivative is 0. So the only way, if you take the derivative on the left side, has to equal to the derivative on the right side. In other words, the only way is a constant. So make the constant goes to 0. Alright, and to find the value of the constant, we can put x equals 0 into this into the last equation right over here, and get, well, if we look at our u, v, w, so our u is this, our v is this, or if you scroll all the way back up and look at it, so here's our u, here's our v, so if we put in x in all of them, w is equal to 0, v is equal to 0, because all vanished, and all we're left with is u equals to 1. So which is quite remarkable. So let's go back here. So we get 0 and everything. So what we're going to get is u becomes 1. So we'll have 1 cubed plus 0 is v plus 0 is w. We'll put it, just for completeness, u 0 to the power of 3, and then minus 3 times it by 1 times 0 times 0. So in other words, we get, and this is all equal to c. In other words, all this vanishes but 1. So this is all we get. N equals to 1. So 1 cubed is just 1. Thus, we just solved our the question we were asked, because we had to show that it equals to 1. Thus, u cubed plus v cubed plus w cubed, yes, plus w cubed, alright, w cubed minus 3uvw is equal to 1. And there it is. That's what we were asked to solve, and we can see that again. Scroll back up to the question, and there it is. Alright, so yeah, we have just solved problem 25, and now let's go over the last and final question. And in fact, it was the one I had most trouble with, just because it was a bit more abstract, and And yeah, more wordy. So it's a more wordy, less just math. Yeah, more you have to actually understand what they're talking about. It took me a while to actually grasp what they were even saying. So anyways, problem 26 states, prove that if n is greater than 1, the nth partial sum of the harmonic series is not an integer. And remember, the harmonic series, that is just 1 over I. Oh, I mean 1 over n. That's just 1 over n. The summation 1 over n like that, where this is a p series where p equals to 1. Like that. Just remember that. And then we're given a hint here, and it's the hint is bigger than the question. So hint, let 2 to the power of k be the largest power of 2 that is less than or equal to n. In other words, what this means is if n equals to, for example, 7, let's say n equals 7. So for n equals 7, we have 2 to the largest power is going to be 2 to the 2 equals to 4. So it's the largest power of 2 that is less than or equal to n. So you can't go 2 to the 3 because that equals to 8, and that's greater than 7. So we can't do that. Just to give an example there. And then let m, capital M, be the product of all odd integers that are less than or equal to n. So in other words, if n equals to 7, then the m is going to be equal to 1 times 3 times 5 times 7. And yes, that's what we get. All right, and then suppose that s sub n, which is the nth partial sum of the harmonic series, equals to m, an integer. Yeah, so if the nth partial sum is equal to an integer, so just suppose that, and we're going to prove that it's not. But first, if you do assume it is equal to an integer, then this number right here, capital M, which is over here, times it by 2 to the power of k times the Sn equals to m times 2 to the power of k times m, and the right side of this equation is even, and we'll show that soon. And then we're asked to prove that the left side is odd by showing each of its terms as an even integer, except for the last one. So basically they're saying this is even, this is e, and then they're saying show that this is equal to odd number. So then that means this is not this equality is fake. Hence this supposition is wrong. So then the nth partial sum is not an integer. So that's the idea. Alright, so now let's take a look at the solution. And again, we got to prove that this nth partial sum of the harmonic series is not an integer. So solution, the nth partial sum of the harmonic series, where again it's a p series with p equals 1, is, and we can write this as s sub n. So just a summation of, and we're going to go all the way up to n. So I'm going to do a summation. If it's called Sn, summation up to n. So we're summing it up to n, not infinity. Up to n. Starting from, I'm going to call this I equals 1. And this is going to be 1 over I. Alright, so here is the nth partial sum. So now we are asked to prove that for n is greater than 1, so n is greater than 1 here, that the partial sum is not an integer, so the nth partial sum. That is not a whole number such as -1, 0, 4, 99. But in our case, since all the numbers are positive, we don't even need to deal with any negatives like that. So it's just basically a whole number, such as 4, 99, etc. Now let's follow the hint given. So let 2 to the power of k be the largest power of 2 that is less than or equal to n. Let capital M be the product of all the odd positive integers that are less than or equal to n. And suppose that Sn, an integer, then, so again, so we're just following this exact same hint. Now we're going to write this over here. M to the power of 2k Sn equals to m to the power of 2k m. So m times 2 to the power of k Sn equals to m 2k m. Alright, so let's take a look at this hint that we're given, so this equation. So for n is greater than 1, so that's what we're asked to find, the right side of the above equation is an even, not and even, is an even integer. Alright, and we can see this because, well, if n is greater than 1, then well, that means n is greater than or equal to 2. Yeah, so it's going to be 2 is the smallest it can be. Yeah, then what we have is, well, 2k is the largest integer less than or equal to n. So if it's 2, then this equals to, well, it's going to be greater than or equal to 2 to the 1. Yeah, so that's the largest it can be. And yeah, so, well, in other words, it's going to be greater than 2 there if n is greater than or equal to 2. In other words, we have k is greater than or equal to 1. So there's the k there. Yeah. Yeah, so thus what we have is m times, I'll just put if that, thus m times 2ks, or we're only doing the right side, m times 2 to the k times m. Then we have a scenario such as, well, let's look at the first case. Well, first we know that capital lowercase m is an integer. This could be even or odd, doesn't matter. This could be even or odd. Yeah, even or odd. And this one right here is actually odd, but it doesn't matter what it is. And that's odd because we're only looking at the odd numbers. For example, 1 times 3 times 5, this equals to, well, 15. So odd times odd is always odd. So anyway, so that's what we have there. And then this right here is, well, this is going to be 2 to the 1, or 2 to the 2, or 2 to the 3, etc. These are all even. So these are all even. And whenever you have any number times an even number, any number or any integer, yeah, I'll just, so it's all integer. Any number that's an integer times it by even equals even. I.e., if you had 11, that's an odd, times it by 2 equals to 22. Or if you could have 13 times it by 3, or times it by, let's go to 4. This equals 2, well, 2 carry the 1, 4 times 1 is 4, then add 1, 52, like that. Yeah, so it's always an even number, because, well, again, it's a factor of 2. All right, this is an example. So that means this is, you're multiplying by an even number. This could be even or odd, doesn't matter, and this could be odd, this is odd, even if it's even, doesn't matter, because this is even. Thus, this right here is equals to an even number. So this is always even. And whenever you're having all integers, these are all integers, multiplied by each other, you're just gonna get an integer. So yeah, so just leave it as that. So it's even integer. So now we will show that the left side of the equation, this right here, with the partial sum instead of just writing m, this is an odd integer. And yeah, so we will show that the left side of the equation is an odd integer, contradicting the equality, and thus showing that the supposition that Sn is an integer must have been wrong. So if this is not even, then we can't, these aren't equal. In other words, it's not an integer. So if we take a look at the left side, that's m times 2 to the power of k times Sn. So let's write that in. So m times 2 to the power of k Sn, and now this equals 2, and we know what Sn is. Sn is all the way above here. So this Sn equals the summation from I equals 1 up to n of 1 divided by I. In other words, that's the partial sum of the harmonic series. So this equals m times 2k. Now let's make this better, m. Alright, and this can be times it by the summation up to, not infinity, I'm too used to writing infinity a million times, n, and then this I equals 1 over I. And now what we'll do is I'll just move those inside. I'm just going to move this inside the summation there. Again, we could factor that in. It doesn't change anything. Just make it neater. So this is going to be up to n, I equals 1, then m 2k over I. Alright, so multiply that inside like that. Alright, so now that we have this, now let's consider the scenario where I is greater than or equal to 1, but less than or equal to n, and I is odd. So we're basically looking at when I is odd. So I is odd, and it sits between there. Then capital M divided by I is an odd integer, since I is one of the odd integers that were multiplied together to form capital M. In other words, m over I is equal to, well, for example, 1 times 3 times 5 if m goes all the way up to 7, and then times by ... all the way to I. And yeah, this m, it can keep going on times by ... all the way until whatever number it gets, that's going to be less than or equal to n. So in this case, if I is odd, well, this is going to cancel because it's part of that m. And this whole thing's still going to be odd. So it's still going to be odd, and it doesn't change anything, so it's still odd there. Or I'll just be like still odd. Still odd. And thus what we have is nothing changes. Summation from I equals 1 of m over I, or 2k, m 2k over I. This is, well, going to be odd. This is going to be odd times even, a summation of them all. And actually, yeah, this is important to be careful. We're not summing that all up. We're just considering the case where I is odd, because I is going to go from odd, even, whenever you go in 1, 2, 3, 4, because you're incrementing it. So we're only going to consider the m over m2k over I terms that are odd, where I is odd. And then this is going to be, well, it's going to be an odd times by 2k is even. So then odd times even, this is going to still be even. So then these terms are going to be even. Alright, so now that we have this is even when I is odd. Now the next scenario is when I is even. And again, I is between, is greater than or equal to 1 and less than or equal to n. Basically all the terms in the summation there. Then we can write I equals to 2 to the power of r times L, where 2 to the power of r is the largest power dividing I, and thus L is an odd integer. This is because dividing by the largest power of 2 removes all even factors. And basically, well, for example, just to illustrate this, for example, if we take I is equal to, so I'll write, for example, if I is equal to 10, then the highest factor is, well, this is going to be 2, if this equals a 2RL, then the highest factor is, well, 10 divided by 2. You can't, 10 divided by 2 to the power of 1. You can't divide this by 4 because that'll be 2.5, and that's not a whole integer number. So then this is going to be like that. This equals to 5. So in other words, this equals to, well, 2 to the power of 1. So 2 over r is the highest power. So 2 to the power of 1, the highest power dividing I, which is 10, times by 5. And again, this is odd. So you're always, because you're taking out all of the factors of 2 out of there. That's pretty much what that means. And let's do another example. If I is equal to 20, so if I is equal to 20 here, then the highest power, you're going to divide by 2 to the power of 2, which equals to, well, 20 divided by 4, which equals to 5. So again, you have an odd power. So this is 2r, 2 to the 2, equals 2 to the, 2RL, just write this whole thing. 2RL equals to 2 to the 2 times by 5, like that. Again, odd. And then lastly, just do one more where I is equal to 8. Well, then in this case, 8 divided by 2 to the 3. This just equals to, well, 8 over 8, this equals to 1. So in other words, this, if you write this as 2RL, and the highest factor is, again, 2 to the 3, this equals 2 to the 3 times by 1, where, again, this is odd. Alright, so now let's take the look at the scenario where r is less than k. And again, I is even, and we're going to have, let's say, this r is less than k. So what we'll get is, then we're going to have I is equal to 2 to the RL, and put that inside our big equation on the left side was, this is summation up to n, this I equals to 1 of, this was m2k over I, like this. So going back up here, so m over 2k, no, m times 2k divided by I. And again, we're not summing it up now, so we'll just ignore this. So just leave it like this. So I is equal to that, and then we're going to throw that inside. So let's throw this inside. This becomes m over, or m2k over 2RL, 2RL. And now these ones we could subtract the powers and move those in front. So this becomes 2k minus r times it by m over L, like that. And now this is also going to be even. And this is because, well, this right here, because r is less than k, so r is less than k and k is greater than or equal to 1. Yeah, so then this right here is going to be greater than 2 to the 1. Or greater than or equal to 2 to the 1. So in other words, this factor is always going to be even. So this is going to be even. And then this right here is going to be odd over odd, and they're both integers, and this L is included in M because M is every single one. So for example, this 5 right here, and this L is less than I. So then for M will have, actually we'll do this one instead. So in this case, M is going to be M, or let's go M over L equals to 1 times 3 times 5 times 7 times 9 divided by 5. So in other words, these cancel out. So it's going to be an integer. Equals odd integer. Or even, don't even need to write odd integers, just write integer. Like that. Well, or actually just for completeness, let's write odd integer. So yeah, so that's going to be odd, and there's going to be integers, and that's even. And yeah, so it's odd over odd, and it's an odd integer because they cancel out. Yeah, and I'll just put in brackets M contains L. Contains L, and they cancel. Yeah, let's do this. M contains L. Alright, so now the last one to check. So basically this is saying all the terms are M, so M times 2k divided by I is even when I is odd. It's even when I is even, and R is less than k. So this is even. But now let's check when R equals to k. Then if we have this, then L has to equal 1 since, and we'll write if it's not equal to 1. Let's say if L is greater than 1. That means that, well, L is going to be greater than or equal to 2, but we know it's supposed to be odd, so, but anyways, let's just say it's greater than or equal to 2, if it's greater than, yeah, if it's greater than 1. So if it's greater than 1, in other words, not equal to 2, then, yeah, then we'll have I, which equals to 2, RL equals to, yeah, which equals to 2 KL, because they equal, because R equals to K. Then this is going to be greater than or equal to 2k times 2 to the power of 1. Or that's just L is 2. In other words, this equals to 2k plus 1. But we can't have this because, yeah, we can't have this because, well, but 2k is the largest power. Largest power of, I'll just say largest power of 2. Power of 2 less than or equal to n. Yeah, so then basically what this means is that I is greater than it's greater than n, because this is already the one less than, the biggest it can be is n, and now it's saying I is greater than n, but we can't have this because we're summing up to n. So so thus if R equals to k, then L equals to 1, and we get I equals to 2, RL is equal to 2k, and L is 1. Yeah, this one is L is equal to 1, like that. So basically, this equals to 1, equals to I. Let's put that like this. And we already saw this scenario here. That's when we were just showing that L is odd. So if I is equal to 8, yeah, for example, then we have this one, L is equal to 1. So for example, I'll just go for example. And it's basically when when it equals to when 2k equals to n. For example, we'll go with for n equals to 8, then 2k, the largest power, is going to be 2 to the 3. Yeah, so 2k equals 2 to the 3. 2k equals 2 to the 3. It's the largest power. And this is also the largest power. Yeah, this is also equals to, yeah, this is just equals to 8. And this equals to our 2RL that we had, which is 2 to the power of 3 times 1, where this is L. And 2 to 3 is the highest power. So that's exactly this part right here. So yeah, that's pretty interesting stuff. So, yeah, so basically let's put this all together. Thus, for R equals to K, then if we look at that term, for R equals to K, we have that term M 2K over I equals to, well, that just equals to 2K. So equals M 2K over 2K. These cancel. This equals to M, which is a sum of odd is a product of odd integers. This is equals to an odd integer. Yeah, so putting this all together, this means that m times 2 to the power of k divided by I is an even integer for every I, because remember we had it even over here for r is less than k, and this is where I is even number, but r is less than k. And it's even here when I is odd. But when I is even and equals to 2 to the power of k, that is when, well, I mean, that's when r equals to k. Then it's an odd integer. So when I is equal to 2k. This means that m times 2 to the power of k times Sn is an odd integer. And this concludes our proof. Basically, for example, what this means is if you have an even number, even plus odd equals odd. So that's the key thing to realize. For example, 2 plus 1 equals 3. 2 plus, or we can even just pick any random one. Let's go to 12 plus 3. That equals 15. So in other words, you're adding an odd amount of numbers to it. So it's always going to be that. And basically put this all together, we have, thus, I'll just, in summary, I'll just put it in summary, because we already had our proof, this concludes our proof or thus statement. Thus, or in summary, we have, put this as a U, and this what we have in summary, M 2KSN is not equal to M 2KM because this is odd, while this is even. And this basically means that Sn is not equal to M, so Sn is not an integer, not an integer. Write it here. And yeah, this is pretty much all we have for today. I'm just going to box this in, and we are done this epic long video. And yeah, that is all for today. I'm just going to fix this. And I'll scroll all the way back up to the very beginning. And yeah, that is all for today. Hopefully you follow along these epic 27 total questions, 26 problems, and 1 example. And yeah, this problem 26 is the one that's the most abstract or required most wording and so on, most wordy one, and then basically try to convey the message we're trying to show. And also to show that, yeah, so that the sum of the harmonic series is not an integer, which is quite amazing. Anyways, let's scroll all the way back. Yeah, my OneNote is glitching just because it's a giant file, and you can see it over here. Should be being recorded. Yeah, so we're gonna go all the way up. It's gonna be pretty epic. All right, let's scroll all the way up. And again, like always, you can view these exact notes in the link in the description below. I'll make these in PDF format, as well as in article format on the Hive blockchain. All right, let's just keep scrolling and see how long it takes to scroll all the way up. So I'm just scrolling manually. It is taking a while. Yeah, this is actually pretty epic. How long it's gonna go? Let's see. It's gonna be a few minutes of just scrolling. All right. And again, yeah, I put timestamps in all the video in the video description, so you could quickly jump to wherever. And yeah, this is yeah. So this 3D section there on the GeoGebra is pretty amazing. Anyways, let's keep scrolling up. And yeah, so notice how it's glitching. And again, it's a giant file. All right, but yeah, I'm still surprised that OneNote can hold this all. But yeah, and I'm going to put this in Hive on the Hive blockchain, and that can store a whole lot of text. I could put pretty much unlimited. And yeah, I put my last biology video is 48 hours long. I put the entire notes into the Hive blockchain as one article. You can't do that anywhere else that I know of, which is absolutely ridiculous. Anyways, let's keep scrolling. We're almost there to the end. Let's go up and up. All right, this is going and going, and almost there. Where's the problem we're at right now? We are at, we're at the example. So that's the example, yeah, and that is all for today. Hopefully you learned. And yeah, like always, you can download the notes in the link in the description below, and so on. Anyways, thanks for watching, and stay tuned for another Math Easy solution.